Hello and welcome back. And on this lecture, this is going to be pretty quick. I just wanted to kind of finish out this chapter. You know, we've been loosely following my book on and off in different areas, but these sections in chapter 4 are kind of all important one way or another. So we're going to talk about this real quick. So mixing logic families, and we've discussed this a little bit already. So there are many, many logic families now in 2017, 2018, of course. The ones that I'm listing here, you're seeing some of the LS and ALS and F and HC and HCT, so TTL and CMOS technology families. But there are many, many more now, and we're going to take a look at that in a second. But the premise of how you get these things to work together is always the same. So say if you're building something, you're building a project, and you particularly like a certain kind of IC, and maybe that IC only comes in one logic family. If so, and your other logic families of your other ICs are different, you're going to have to interface these things together. Now, there's a few different things that you have to consider. One would be the power supplies, the voltages that the logic families are using. So first, are they using the same voltages? So 3.3, 2.5, 1.8, 5 volt, whatever. That's number one. So first, if they're using the same voltage, that's great. So now you're working with the same voltage rails. Then the second thing is if you're going to mix TTL and CMOS, now remember these technologies are different. TTL is based on transistors, CMOS are based on field effect transistor, FETs. In one case, these are current driving devices. The other case, these are voltage driving devices, and they work, differently. So to mix these families together, you have to look through the data sheets and you have to understand if you want to connect, for example, a TTL to drive a CMOS part or a CMOS to drive a TTL part, you have to understand is it going to be able to do it when you're driving it high and driving it low, those two cases, right? And then how is it going to affect the fan out of the IC, how many ICs it can drive, and so forth. So anyway, I want you to read through this, but in a nutshell, you can take a look at a couple little figures here. So in this figure, we're just showing some CMOS device and it's outputting to a TTL input, right? Now, if we're dealing with a 5-volt system, CMOS typically will output a very high voltage. It'll almost be to the rail. So it'll be like 4.4, 4.5 volts, sometimes even higher if it's a 5-volt system. Now the TTL input, if you remember, the V input high needs to be approximately 2.0 volts, right? 2.0 will be registered as a high. So definitely when we have a CMOS driving a TTL high, that will work. All right. The other problem is when the CMOS is driving it low, right? Uh, the uh, the We need to make sure that low works also in the same way, and the TTL input is going to, remember, it's going to source and it's going to sink current, and those currents are important, and so you have to make sure that the CMOS can sink or source the amount of current required as well, all right? And if it can't, then it's not going to be able to drive it low and it's not going to be able to drive it high because the TTL requires current, not just voltage. So when you're driving it high, current is going to flow into the TTL input. When you're driving it low, current is going to flow out of, right? So the device is going to sink it. So the CMOS has to be able to sink current, all right? So that's when you're doing CMOS to TTL. Now, when you're going the other direction, and again, you can read all this, when you're going the other direction, the TTL, now typically you can just hook a TTL directly up to a CMOS, it'll usually work, but the TTL is not guaranteed to have its output very high. So it's guaranteed to have an output of like 2.4 volts for a 5-volt TTL, but the CMOS input, it's the lowest voltage that it'll register as a 1, depending on the family, right, is a little bit higher than the 2 volts. So if we go back to that chart, we can probably find it. Let's see if we can find it real quick. Let me just scroll up here. Close your eyes if this makes you sick. I know it does with some people. And right about, keep going, keep going, keep going. Oh, let's see, we're almost there. It's here someplace. I think it's right here. So here's just one. So if we look and we see here's our 2.5 CMOS, here's our 5-volt CMOS and TTL, right? So we can see these two things. So if we've got a TTL chip and it's outputting a high, right? So it's guaranteed to put out a 2.4 volt high. But on the 5-volt CMOS, it requires a 3.5 volt to register a high. Now, when you have a real TTL chip, and you output a high, it's usually much higher than 2.4. It'll be up here. It'll be up here, just barely above 3.5 volts, usually sometimes almost 4 volts. So it'll usually be okay outputting that high. But if you start loading it, it won't be. All right, and so it's only guaranteed to be 2.4. All right, so you can kind of look at these two voltage levels, right? For high and for low, and then for high and for low. These have to be matched. So that is what is important, or any two families that you want to match together, right? So that's what the importance is here. So in the case of the let's go back to chapter 4 here where we just were. Okay, so back to the figure we were looking at. So if you have a TTL output and you're driving a CMOS input, what you may have to do is put a pull-up resistor to make sure that you get that high value at the voltage level that you need. So you might put a 1 to 3.3K resistor, or maybe even a little bit higher, up to your 5-volt supply. And that'll guarantee when you output a 1, the CMOS will register a 1, and when you output a 0, you'll get a 0 also on the CMOS input. So anyway, so that's the whole point is, if you're going to mix logic families, you have to pay attention to how these things work. You got to look them up. You got to look up that figure that we just were looking at that shows the different values and how they relate to each other. And then you've got to consider things like current, source current, sinking current, and so forth. And then you can hook these things together. The better approach is don't mix logic families. Try and stick with one logic family and one voltage so that you don't have these problems. One of the biggest problems with playing with Arduinos and Raspberry Pis, especially with Arduinos, 8-bit Arduinos, they're all 5-volt systems, and a lot of ICs these days are 3.3 volts. That's kind of the norm these days for building things, is 3.3 volts. So if you want to interface it, it's difficult. You've got to have what are called level shifters. You have to have multiple voltage supplies, 5 volts and 3.3. Then the other problem is you can just kind of hook these things up and throw caution to the wind, but you may damage an input or an output, and you got to be careful. All right. Now, what I want to show you now is a resource here. So Texas Instruments is one of the biggest semiconductor manufacturers in the world. Texas Instruments, been around for a long time, and this site is just it's an unbelievable potpourri of knowledge and resources, and very, very well written documentation. So if you just go on Google and you look at things on Wikipedia and so forth, remember those are just from people just writing. There's peer review of a sense because other people look at it, but if you look at white papers and application notes that are written by a company like Texas Instruments, that information is very, very, very good. And most of these people writing these things, have masters or PhDs in electrical engineering, so you can really listen to what they're saying and not worry about it. So anyway, what I wanted to do here was I wanted to do this. Let's search for logic family specifications or comparison guides. So you see all these different things that come right up here. So logic family specifications. All right, right in their search. They've got a great search also. It actually works. All right, I'm just scrolling down. See this logic guide, revision AA? And there's countless documents on here. So this is 21 pages. And so this is not bad. So you could read through this. So 21 pages, logic guide, showing you some of the cool things, some wearables, a robot. And then here's what I wanted to show you. So this is TI's logic families. Look at all these logic families here. So there's our old TTL, right? And then where's our old HC? Let's see, HC. Looking for it here. Here it is, number 10. HC, there's our old HC CMOS, then all these other families, a lot of families. There's 16 families, and probably a couple more now that this was written in 2014. So anyway, what's nice about this guide is you could do worse things than just read this, and I really want you to read this link right here. I'll put inside the documentation, but you can just search just like I did. Anyway, you can do worse things than just read through this, just to kind of have an idea of, wow, look at all these different logic families that there are. So, here, for example, it's showing voltage versus speed. So as the voltage increases, the propagation delay decreases, so it gets faster, right? So the higher the voltage, the faster the thing operates, except for this family here. Well, they all have the same trend, but this is pretty slow. The HC is really slow. And then take a look down here, this family right here. So this is like a AUC, right? And so one of the families that I like to use a lot is I'll use LVC, which is kind of this green one right here. This is a good low-cost, high-performance family, LVC or LVA, and LVA is this yellow one right here. So LVC, I use that a lot, and a lot of ICs, logic ICs, come in that family. All right. So anyway, you can look through here, and I really want you to read this. This is a great read, and then here's a modern version of that figure that we saw. So this is a very, very up to date, again showing all the different logic families and how they relate to each other. But yeah, and then take a look at this right here, and there's all those logic families and all the different kinds of ICs that you might see them with. Anyway, and then you can see what all these acronyms are: advanced, ultra low power, and so forth, for if you're going to do wearables and things like that where you're using a battery power. And every one of these logic families, all 20 something of them or whatever there are for different applications, optimized for different applications. So it's a bit overwhelming, but definitely I want you to read through this and kind of look through this, and it's just like a wow. Don't worry about remembering it all, but just go wow and just think, wow, this is amazing. And then they've got thousands of chips for every one of these logic families. Okay, so go through that, and that's going to be very helpful. Then let's say, for example, so we're going to build something, let's say, and we're going to do a lot of these experiments, and we're going to start building things on the bench, right? That's what's going to happen next when we get into the next chapter. But for example, let's say that we wanted to find an inverter, right? So we know an inverter is like a 7404, but if we look for LVC04, all right, so here we go. So 74 LVC04, here we go right here. So 74 LVC04A hex inverter. So we'll click on that. All right, and then what's nice is the way that TI's pages are set up, they've got description and parametrics, online data sheet, all these different things here, how much they are and so forth. They've got kind of a general specifications real quick. You can click view more if you want more of this information. But what I like is this little table right here, the parametric table. And what it does is it shows you the variations of it. So you see here's the 74 LVC04A. A just is like the latest version of it. Then there's also this 54 version, and then there's this other version, EP, and then this Q1 version, which is, see, this is automotive. And see, this is high rel, or which is an enhanced product, right? This is military spec. The 5.4 is mil spec. You've seen that, heard that word before. And then here's just the average ordinary, IC version is this. These versions will usually be a little bit more expensive, but if you're going to build something really robust, then you might want to use the military spec or the high rel or the automotive spec version of the IC. Anyway, let's take a look here. So you see V sub CC is 1.65 volts to 3.6, so it'll work anywhere in this range, which is really, really nice, all right? Then the other thing is, if we look at some of these speeds, this will run up to 100 megahertz. So that's nice, all right? And then it's showing you the amount of current, and then the propagation delays, all right? And then it's showing output drive. So this is important. So see this output drive right here, this minus 24 and 24? So even though this is based on field effect transistors and not transistors, they design these so they can output current, so they can drive things or be driven. And so the minus 24 and 24, those two numbers, they show what the output drive is and the input. So if you're outputting a high or inputting or outputting a low, whether you're going to be driving or driven, it shows how many milliamperes of current, right? And it's also symmetric in this case. So a lot of times it might be minus 12 and 24. That means it can sync 12 and drive 24, but they're not symmetrical. So we'd like symmetrical current drive also. And you can see all of these are symmetrical. Now, let's say that you needed 40 milliamps of current. What could you do? What could you do? Well, you could take two of these inverters and put them in parallel. Then you get 48 milliamps of current. So you can do things like that. And then again, all these different packages here. Now, one interesting thing is in the 74 LVC04A, looking at this, it does not have a dip package. Notice that it has no dip package. All these are surface mount packages. You have to go to the 54, right, to get that dip package. All right, so that's interesting. All right, so anyway, let's go take a look here at the data sheet. Go here and look at the data sheet for it, and it's usually this red link right here. All right, and again, this is a revision A of the IC, and the data sheet's revision T, so a little bit confusing. All right, so you can go through here and read about it. And so this is a great IC. It's very, very fast. But again, this is not going to work if we want to use our 5-volt systems, right? So we could read and say, can it tolerate 5-volt inputs and that kind of thing, but maybe we need to use a different logic family, right? So there are different low voltage logic families that won't output, a 5 volts, but they can tolerate an input of 5 volts, okay? So, and then remember TTL, if you're going to drive TTL, straight TTL, then it requires only 2 volts for a high, and even this 3.3 volt system, low voltage CMOS will output a high enough value to trigger a high on a TTL input. So anyway, LV, LVC, LVA, that's a great family to use, and the majority of anything that you want, you can find in this logic family, and it's really, really fast, and it's very, very low powered. It's a good go-to logic family. So anything LV is a good go-to logic family. All right, and then the other cool thing, let me show you, is see this order now? So we click order now, and there should be, yeah, so with now, so I'm going to tell you this, and this is a big secret. A lot of people don't know this. Most semiconductor companies will give you free samples. In fact, they'll give you lots of free samples. So don't tell everybody, or everyone will get free samples. But you guys, I'm going to tell you guys, so TI, Microchip, Fairchild, Atmel, you name it, all of them will give you free samples. All you got to do is create an account. And it doesn't matter if you're a company or individual, just put whatever you are, make your account, and then what you do is you simply go to the website and you just click request sample. All right, so we request sample, and then here's the different samples here, or the different parts here. So now look, we've got the 74 LVC DRG3, which whatever that package was, it's a surface mount package. But look at the price, is $0. It doesn't cost you anything, and then you just do checkout now. All right, and then we can increase, and then it's saying you must log in when checking out. So I'll update this to 5 here. All right, and we should say up there, updated. Shipping and handling is also 0. So within the United States, they'll definitely send you these, and TI sends these things FedEx for free. It's pretty cool. So and you just so I think you can take up to like 5 different ICs and 5 units of each. So over a period of time, as you're experimenting, go ahead and sample these things from TI and these different companies and build up your parts list so you can experiment with things. Okay. So that's about all I wanted to talk about, is just kind of mixing logic families and using TI as a resource. It's a really good site and has lots of information. And then if we go back, let's just go back here, and we'll go back here to the page, back onto the IC page, and then notice online data sheet, technical documents, support and training. If you go to technical documents, all right, then there's usually a bunch of different little application notes and literature showing how to use these things in interesting ways. So, use of CMOS for unbuffered inverter circuits. So anything that uses this inverter IC or something like it, there may be an article about or an app note or something like that that you can read and kind of figure out what's going on. Here's an interesting thing. So implication of slow or floating CMOS inputs. So whenever you have an IC, if you don't use all those inputs to the IC, what are you supposed to do with them? Well, you need to tie them high or you need to tie them low. You need to do something with them. And this paper right here, if you read this, it'll explain why you need to do that. All right. So anyway, a lot of good information, and just it's a reading is what you got to do. And then here's these logic guides. So little logic guide, logic pocket data book. And many of these things, like I said, they'll actually send you print copies of. They used to. You may be able to find it, but like this little Logic Pocket data book is pretty cool right here. Put up this PDF. And there's probably a place on their site, which I'm not sure of. So this is 800 pages. So that's a pocket data book, right? 800 pages. There's probably a place on the site. You can see this is it had a printed cover, where you can actually order this book. Right, and you can get this and have it right next to you. And I like to do this. It's like if I'm sitting down sometimes, I would have these books around and I would just start paging through them. Just paging through it. I'm not memorizing everything, but it gets in there and you're like, I remember seeing that, and it's just nice to look at it instead of looking at a computer screen all the time. Okay, so anyway, so let's we're going to finish up here, and I will meet you in the next lecture, and we're going to keep working on our digital stuff and start building some things. Okay, so see you then. Bye. Hi there and welcome back. We're on the next lecture, and this is going to be pretty quick. We finished chapter 4, which was kind of the introduction to some digital concepts. And now what we're going to do is we're going to continue with the digital coverage and go deeper into some small scale and medium scale integration ICs that cover kind of a gamut of different things you might need. And then from those building blocks, you can kind of figure other things out. But we're going to actually skip a chapter in the book here, and the book is just a loose guideline, as you know, and we're just using it as something to base things off of, so you have some text material. You know, it's a 1,000-page book I wrote, 919 pages. You might as well read it. Anyway, but chapter 5 talks about hardware construction techniques, and we're going to skip this chapter. But yeah, here we go. We're going to skip this chapter, but honestly, this chapter is probably the most important chapter of the entire book. And it's something that you're not going to find anywhere, at least easily. So there are thousands of books on digital electronics, thousands of books on analog electronics. There's no limit to how many different sources you can find for those things. However, constructing hardware is typically not written about. It's difficult to find. You can find YouTube videos of it. You can find a little tutorial here and there, but it's very hard to find this kind of stuff, especially if you want something that covers all the different kinds of techniques. So you might find a book on PCB design, right? You might find that, but it's going to be very hard to find a book that talks about solderless breadboard design or wire wrap design. So this chapter right here is something that teaches how to do real-world construction using a number of different techniques, which we've already been using. We've been using the solderless breadboard, we've been using the wire wrap and so forth. So I really want you to read through this carefully, actually a couple times, it wouldn't hurt you. And it's got lots of little tidbits of information to make you think. Like, for example, here's a copper density table here that shows you different widths in thousandths of an inch that a circuit board trace might be, and how much current can it support, things like that. Just all kinds of, real world pieces of information that you might pick up over years and years and years are all in this chapter. So please read this. Problems and things that happen, showing the different techniques, breadboards, solderless breadboards. We've seen this, we've been working with this constantly, vector boards that you can solder into, things like that. And then, hey, I want to make a circuit board that plugs into my PC, an ISA board or a PCI board. How do you do that? So it talks about some of that stuff. Tools, soldering techniques. What should the solder look like? Should it look like, should it look like this or this or this? Those kind of things. So anyway, different chips. We've looked at that. All kinds of really good information. Wire wrapping here. The wire wrapping tool very up close to see how to do it. Even though we did this in the video, this is really nice because you can kind of see exactly what's going on. I took the time to sit and photograph this painstakingly so you could see what was going on and kind of how to do it, some different tools, how to make your own PCBs, some examples, some layering, all kinds of stuff. And then this is really, really important. The section here starts to talk about rules of thumb for a circuit board design. So, one of the things I do is I consult for a lot of different companies and on whatever kind of project. And something I do a lot of is I do review of circuit boards for other engineers. And circuit, you can get an electrical engineer degree, you can get a master's in electrical engineering, and you may not have ever made a circuit board the entire time, or something really, really simple. And even if you made it, you probably made it wrong, because very few universities teach circuit board design. Very few universities. Now, you can get it at a trade school. You can learn about how to do circuit board design, and then now with some of these online courses. But it's something that people usually don't take. So anyway, when you design a circuit board, you're going to make all kinds of mistakes, and these mistakes can be avoided. You'll have a better circuit board, more robust, more functional, it'll last longer, etc., if you just follow some rules of thumb, which are derived from the physics, mechanics, and other fields, but they're really simple rules, like, don't make traces 90 degrees, put them at 45 degrees, right? I could tell you why, but you don't really need to know why. So the rule is just do that, and you're going to be okay. Later, you can learn why. All right, so anyway, lots of little rules of thumb with circuit board design. So that's that's worth its weight in gold. Like right here, I see this all the time. You got a trace going into an entry pad, right? And I'll see this coming in sideways or skew. This is horrible, and this creates all kinds of mechanical issues and stresses and a number of different issues. This is what you want the pads to do. You want it to come straight into the pad, nice like that, right? And there are mechanical arguments and there are electrical arguments for both of these things. So anyway, lots of good information. And I'm, just scroll through here. It goes through all kinds of different areas of interest, and it's like a whirlwind tour of kind of fabrication and design when you're building your PCBs and building your projects and different ways to do it. So please, I want you to read chapter 5 once, maybe twice would be really good, and just put it in the back of your mind, all these different things, so that you think about them when you're doing it. And we're going to talk more about this when we go and start doing some printed circuit boards with Circuit Maker at the which is the last part of the course. We'll talk more about that, but I'm not going to go through chapter 5. It's just too big. This chapter is a course in itself, and to do it justice, I'd have to do a whole course. But if you just read this chapter, and that's why I wrote it, a couple times, you're going to have a lot of that information and be able to, do things yourself. All right. So anyway, so that's all we're going to talk about. I'm going to meet you in chapter 6, combinational logic and SSI MSI blocks, which we're going to talk about next, and we're going to dig and dive in deeper to some more digital components and start playing with them more there. All right, so I'll see you in the next chapter. So let's finish up this lecture, and I will see you in the next one. All right, bye. Hello and welcome back. We are on the next chapter, and really now we're going to really start diving into the digital electronics more and more, and we're going to be talking about SSI MSI blocks, which stands for small scale integration and medium scale integration. So this chapter is about basic chips that you might use when you're building something. For glue logic, just maybe around your microcontroller or your larger scale integration. So we're going to learn a lot of different kinds of ICs that have basic functionality more than the simple logic gates that we already looked at, the AND gate, OR gate, NOT gate, XOR, and so forth. We're going to look at chips that have a little more functionality. Right, and hopefully with all of these, we'll cover enough so that you can kind of build anything you want or kind of figure out what you would need to build anything you want. So we're going to jump right into it. And remember, you're supposed to read chapter 5 yourself, hardware construction techniques. Just kind of read that through a couple times. All right. So the plan is, what we're going to do is we're going to go through the material here, kind of skim through it. I want you to read the chapter, of course, so you should always read everything. We're going to skim through it, and as we get to each new interesting kind of class of IC, we're going to maybe do a simulation, and then we're going to go on the bench and build something with it. And we're going to kind of go back and forth like that to keep things with some practical application, and not just do the whole chapter first and then do practical application. All right, so the first part of the chapter is fairly technical. And this is a fairly advanced commentary on logic simplification. So we already kind of talked about the concept of bubble pushing and De Morgan's laws, De Morgan's theorem, which is kind of reviewed here. And the whole idea of the first part of this chapter is this is really going to give you some advanced conceptual material on optimizing circuits and using techniques, and we've done this bubble pushing thing here before, and using techniques that are not in the scope of this course, but you can read them inside of the book here. So what I want to show you here is this down here. All right, so in this table 6.1 here, so when you've got say you're doing some kind of logic function, right? So you have some variables which are all digital, they're ones and zeros, right? Maybe the 3 variables, you're calling them X, Y, and Z. So if you have those 3 variables, the only possible values they can be is 0 and 1 each, right? So if there's 3 of them, that's going to be two different possibilities, times 2 times 2, 2 to the n, 2 to the third is 8. So in this case right here, you see we've got all the different possibilities for the x, y, and z variables, 0 through 7 in binary. And then we have them written down here kind of in their symbolic form with bars over them to represent when they're zeros. And then we have this word called minterm, all right? And then these are the indices, and then these are the minterm symbols. So all this is if you start studying digital electronics more at the theoretical level, this is kind of how we talk about things. This is our notation. And the reason why they're called minterms is because they're multiplicative. So we're multiplying these values, which is equivalent to using an AND gate. So basically, minterm 0 is not x and not y and not z, right? Minterm 6 is x and y and not z. So basically, say if you were building something and you figured out, well, I have these three variables, maybe they're inputs from the user, maybe they're inputs from something else, and when maybe I've got a 0, 0, 1, I want this function to output 1, so that means you need this minterm, all right? And then maybe when it's 1, 1, 1, you want the function to output a 1. So what you would do is you'd have an AND gate, a 3-input AND gate, you'd implement this one, and then I believe I said this one right here, and you would have a 3-input AND gate and with a couple inverters there, and you would invert and then create this minterm right here. Then you would OR them together. So what this is, it's a sum of products you're kind of thinking about. So you see right here, F, it's a sum of products in this case. All right, so each one of these are called minterms because they're multiplicative, which means and. So this is just notation so that you can kind of talk about this in a consistent manner. All right, now let's see here. Anything else? Now, and here's another example. And what I'm doing here is I'm just showing you all the different possibilities for x, y, and z, and then saying we want the output, whatever function we're trying to implement, who knows what it does, but we want it to be high when these two minterms occur, which is M6 and M7. So we would say that this function, this output that we want, is the sum of minterm 6 and 7. Or in other words, we would have to take the minterm 6, which is this minterm here, which happens when x is high, y is high, and z is low, or when x is high, y is high, and z is high, right? So anyway, it's just notation. And then we have max terms here. Max term is the opposite. Instead of a sum of products, it's a product of sums. So here's the sum. So x plus y plus z, and not x plus y. This is a typo right here. This should have been another plus right here. So anyway, it would be a product of sums, all right? So if you look here, they're called max terms because you're doing OR, right? Or you're doing, binary addition. And so each one of these is called max terms. And again, they've got these symbols, they've got these indices, and it's the same kind of thing. So you can work with min terms or max terms. And the whole point of all that is so you can get into this thing called Carnot maps and minimization is one technique for minimizing functions. So what this is when you have all these binary variables, it's very hard for us to see what the optimal function would be, right? We kind of write all this down, but then is there any way to optimize this? And there are graphical techniques, there are table techniques, there are algorithms to do this. One of them is called a K-map, which I'm not going to go into. You can read about it here. But what we do is we carefully put down in this two-dimensional, three-dimensional, even n-dimensional. Of course, we can't work with it after 3 dimensions. It becomes hard. But we put down in this table the different values of the variables and where we want things to be high, right? And then what we start doing is we start actually graphically looping ones. And there's a whole process to this, which is explained in detail in my book here. And this allows you to optimize the function. So in this case right here, we start off with this function here, which says f equals x and y plus not x times y. So if you didn't know how to do optimization, well, what's this going to do? You're going to need an OR gate, you're going to need 2 AND gates, and an inverter here, right? But if you look at this very carefully, and we started doing algebra to it, you can see that both of them have y in common, right? So I could factor the y out. So then I would have y and x plus not x. Well, x plus not x is always just going to be x, right? It's always going to be high because that's 1 plus 0. So all I'm left with is y. So I did that algebraically in my head, but here we did it with this algorithm. We came out with y. So now what do we need for gates for this? Nothing. So we went from 1, 2, 3, 4 gates to no gates. So this is very, very powerful stuff. So this is why this is important to know. So anyway, read through this. It's an interesting read, and can learn about all this stuff and different dimensionalities, and here's larger tables and very cool stuff. All right, and what I want to do now, and then there's another technique, a table technique, a computer can implement called the Quine-McCluskey algorithm for optimization. So anyway, read all that. Where we want to be right now is here. We want to be in this SSI MSI block section. All right, so this is what we want to talk about today and what we want to start doing. Okay, so obviously there are ICs, digital ICs that have varying numbers of gates and transistors and that kind of thing. And they're classified. Now, this is a very loose classification, and of course, every year it kind of changes because what was large-scale integration 10 years ago, right, is now small-scale integration, right, and so forth, because the transistor count, the gate count goes up so much, right? And I want to show you just how much. But as a rough rule of thumb, if it's 10 to 100 gates, we call that small scale integration. If it's 100 to 1,000, medium scale. Large scale is 1,000 to 10,000, and very large scale is 10,000 and up. All right. More or less everything these days that's a microcontroller, that kind of thing, is always VLSI. These things have millions and billions of transistors. It's just crazy. All right, so that kind of gives you an idea of some of these terms: MSI, LSI, SSI, VLSI. All right, now again, we know that I like TI for a great site to look for parts. They have all kinds of different parts. Of course, you can search on DigiKey and whatnot, but there's all kinds of information on TI just from a research and white paper point of view. So keep that in mind. All right. Now, the first thing that we're going to talk about is, and what our goal is here is, it's like, well, where do you even begin with digital electronics? Well, you have a problem. So you have a problem, and you say, okay, I can think of what I want to do here. I have these couple inputs and I want to count, and then when the input is this or when the input is that, or when the count is this and that, and all these different combinations and permutations and so forth, you start to think about all this. Well, how would I do that with electronics? Well, there are building blocks that perform these operations, right? And there are some classic basic building blocks which you can use to kind of build up these more complex digital circuits. And that's what we're going to go through. And we're going to go through a number of these chips. There are hundreds, thousands of different ICs, but they all fall into certain kinds of classes. Counters, flip-flops, registers, drivers, comparators, and so forth. So that's kind of what we want to do. Is we just want to give you enough different kind of ICs where you can kind of have an idea of what to do with them and how to build something. So the first one we're going to mess with is a decoder. But before I do that, I want you to take a look at this. This will blow your mind. If you haven't looked at this or aware of this, it will blow your mind. All right, so we were just talking about transistor count. And just to show you, how far things have come here. So that's a Wikipedia transistor count if you Wikipedia or Google for it. And then this little chart right here. This is pretty crazy to show you this, this curve that we're on here, right? This linear kind of curve. So in 1971, when we kind of had the first microprocessor introduced back in the early 70s here, the Intel 4004, which if you've been doing computers as long as me, you may have even used one of these. All right, so that had roughly 2,000 transistors, and then most everybody's probably heard of 8080s and 6502s and Z80s, kind of in this late 70s era, right, early 80s era, and these things were around 10,000 transistors, right, 10,000 transistors. Then the first IBM PCs, right, were based on the 8080 processor, 8086, 8088. There's the 8080 right here, and so on and so forth as we go up. Here's the first Intel 38646, and on and on and on and on and on. And then here, 2011, this chart is a little bit old, goes up to 2.6 billion transistors. So we went from 2,300, a couple thousand, to 2.6 billion. That's just crazy. And and this whole thing here, this curve here is this Moore's law curve, right? So basically the transistor count is doubling, every couple years, all right? Now, one of the interesting things is if you look at, let me go back here. If you read through this, the current record holder, which is probably not the record holder anymore because it's been a few weeks or months, but the Altera Stratix 10, this IC has 30 billion transistors. 30 billion transistors. That's just mind-numbing. And the Stratix 10 is an FPGA, field programmable gate array, which is a sea of programmable logic. There's a two-dimensional matrix and basically all these logic cells, and then you can connect them together programmatically. So you can actually program the silicon to change what the chip does. That's called a field programmable gate array. All right, and there's also what are called complex programmable logic devices, which are smaller versions of that. And then there are even smaller versions, which are called PALs and GALs, programmable array logic or generic array logic, really small stuff. So anyway, there's a whole class of programmable logic, which we're not going to get into, which is very, very interesting. Anyway, Intel bought Altera a little while ago, and the Stratix 10 is their biggest, baddest FPGA. And so, say for example, you want to design a processor, like something around like an Intel processor level technology. So what you would do is you could design it in the computer and simulate it, but then you could actually build the processor in one of these FPGAs. You may not be able to run it at full speed, right? Because the processor itself may be more advanced than the FPGA, but you can definitely implement it in an FPGA or more than one FPGA and actually run actual hardware. And that's what a lot of design engineers will do. What we'll do is we'll design something virtually in the computer, and then we'll implement it in an FPGA and then run it maybe at slower speed, and then later it would go to an ASIC, an application-specific IC, and actually be turned into a physical IC, which costs hundreds of thousands or millions of dollars or more. Anyway, but the other thing I wanted you to look at is just, again, this is transistor count, if you Wikipedia for transistor count. And just look at some of these things because they just are pretty amazing. So you see some of these early processors, the famous 4004 from Intel, 2300 transistors, 1971, and then you just scroll through here, and then and another interesting thing is the process. So the process when you're talking about semiconductor development is what's the smallest feature you can make, the smallest transistor. So this is 10,000 nanometers, right? So that would be a 10 micrometers, or that would be a 0.01 millimeter, a hundredth of a millimeter. So still really small, right? And then as you go on, Pentium 4, here comes our core duos, our quad cores, our i7s, and down and down. And here's 22 core Xeon Broadwell, and with 10 billion transistors in 2015 from Oracle. And then look at some of these processes down here, 14 nanometers. So call it 10 nanometers. So we went from 10,000 nanometers to 10 nanometers, right? So literally 1,000 times, and also remember it's squared, right? So the area keeps getting smaller by the square, but 1,000 times smaller feature in X and Y, and then the number of elements has gone up to billions instead of thousands. Just incredible, just incredible. So, and then if you go to GPUs obviously these days have more transistors than processors do. So this GP100, it's an NVIDIA. This is what's in their Tesla cards, right? I don't know if you've heard of Tesla cards. Those are their supercomputer cards that you can get. Totally awesome. They're like $5,000 to $10,000 graphics cards, basically, for supercomputer calculations. But 15.3 billion transistors, just awesome. So anyway, super interesting stuff there. All right, let's get back to our little decoder chips, all right? But it all starts here. It all starts here, and you keep building it up. And this is the beauty of digital electronics. Once you have one block, we add more and more and more and more, and then we just go nuts. And then next thing you know, you've got an Intel 7 processor or whatever. Okay, so a decoder, what this does is, one of the functions you need in digital electronics quite often is you have a couple inputs, maybe you have one input, two inputs, three inputs, whatever, and you want to convert those for every possible combination of the inputs. You want to turn an output on. That's all. That's it. And you need that a lot. So if you look at this kind of logical description here, we have these two inputs, S0 and S1. And what I want is all four combinations. So here's 0, 1, 2, and 3, right, in binary. And whenever I get those combinations, the 0 combination, I want to turn on an output called Y0. I get 1. I want to turn on Y1. I get 2. I want to turn on Y2. I get 3. I want to turn on Y3. Just simple as that. That's all there is to it. And it's just like an OR gate or an AND gate or whatever. It's just a very simple logical operation on 2 bits, right? And here it is kind of in logic format, right? And then here's what it would look like. So first, we have our two variables, S0, S1, and then we get inverted versions of them, right? So now over here would be S0 naught and S1 naught. And then we pick off all those different combinations. We just throw them into AND gates. Bang, 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 bang. And then each one of these AND gates is Y0, Y1, Y2, Y3. That's it. That's all. That's what we want. That thing right there, right? So there's a chip for that, right? And uh, because this operation is so common, you can get a 2 to 4 decoder, but the more common decoder you'll see is a 3 to 8 decoder with 3 inputs. And if you don't need all 3 inputs, just tie 1 to 0, right? And then you can only use 4 of the inputs, okay? So that chip right there is called a 74138. And there's many different logic family versions of it. There's LS, HC, LVC, and so forth. All these different logic families you can find usually. All right, so we're going to take a look at that in a second. And this right here is the HC excerpt from a data sheet. So it's just showing you here's the kind of the logical functional diagram of it. So showing here's our inputs, A0, A1, A2, which is like our S0, S1, and now there's an S2. And then here's all our outputs. And then here's something interesting. So in the 238 version, the outputs are active high. See that Y0, 1, 2, that's like ours that we just designed. They're active high. But the 138, which is actually more common, it's active low. They're inverted. Now let me tell you why this is. So two reasons. One reason is a lot of ICs, memories or drivers or things like that, they use active low to assert or select them or enable them. All right, it just is the way it is. It's active low. It could have been active high, but people early on just said when it's low, the chip is going to be turned on, right? That the enable will be low instead of high, right? So it's a little counterintuitive, but the reason is that they just decided to make it that way. Simple as that. Okay, because of that, this IC is typically used. It used to be used a lot for memory addressing. So basically, each one of these went to a different memory, and to turn the memory on or enable the memory, each one of these outputs would be asserted low, right? And then those would go right into the chip selects or the enables of the drivers or the memory chips, and it would work out perfectly. So this became more popular as using active low. So if you have something that you want to assert high, you have to put an inverter, or you have to use this other version, which this 238, you can probably find them, but they don't really make them anymore. The 138, though, you can buy all day long. All right, so anyway, so that's it, and then it just has power, V sub CC and ground, right? And depending on the logic family, it'll be from 2 volts to 6 volts or 5 volts or 3.3 volts, V sub CC. Now there's a few other little lines here. So what are these things all about? So these are enables. And so you're like, well, why do I need 3 different enables? You don't, right? But they just they put them here so that you can have potentially a couple different signals to validate this IC doing what it does. In other words, maybe I've got a signal coming from another part of my circuit. When it's active high, I want to turn this thing on. Well, there's an active high enable. Right? What if I got something that I want active low? Well, there is an active low and another active low. What if I got 2 active lows that I want both of these to be low before I turn this thing on? Well, there you go. It's got 2 of them right there. Right? What if I got one that's active low and one that's active high to turn this thing on? There you go right there. There's a low and there's a high. So you see, so basically what this does is this gives you a few different options to turn this IC on and get it to do what it needs to do. If you don't want to use them, don't use them. Just tie them all so that they're asserted. So we tie E3 high, E1 and E2, we tie both low, and then everything would work, okay? Okay, let's see here. Okay, then the logic table here, right? The truth table, right? And it's showing for the enables, right? So if the enables aren't enabled, then it doesn't matter what address you're doing. It just puts these things all high, right? So until all these enables are enabled properly, I don't care what your A0, A1, A2, or S0, S1, S2 is. I'm just going to put all these outputs high, and I'm not going to turn any of them on. And in this case, on means active low. Now, once you enable this thing properly, and you put the right code on it, which would be HLL, that would be high, low, low. Then, so if you put a low, 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 then we're going to turn on the first output, which is Y0, which turn on means low, right? And the rest will be high. And then if you can see, there's like a diagonal of lows through here. See all those lows going through there? And that's it. So that's all this IC does. That's it, right? That's it. Very, very simple, okay? So and then there's just talking about that. there's kind of what we're talking about, how we would set this thing up, maybe a couple variables. So in this case, say if I wanted to enable it when X was high and Y was low, that's one way I could do that, right? So it just saves you some extra logic, okay? All right, let's not worry about this right now. So let's go here, and what I want to do is, let's go search for this IC. And there's lots of different versions of it, right? So you can find the LS version of it, 74 LS 138. Type that in, the low power Schottky version, and we can find a dip here someplace. I think this is the dip. Is this a dip? No, I think that's still surface mount. There we go. There's one right there. All right, kind of a dip version, and then we can open up the data sheet. And again, you can see these are pretty old. December 1972, the first time it came out, right? So there it is right there. And then, you know, as you go through these things, you'll find different nomenclature for some of these inputs. So here they call it A, B, and C instead of A0, A1, and A2, right? The Y0 through Y6, they still got that. They don't put the little bar over it here, right? And then they're calling the inputs here G2A, G2B, and G1 for the enables, right? But this one's low, and this one's active high, all right? So you got to kind of figure this out and read through it a little bit. And then since it's such an old data sheet, it'll show you the circuit. There it is right there. Very similar to our 2 to 4 decoder, right? And look at this enable. So this enable, just basically a couple gates, right? Then there's your inputs, and then here's where we're buffering and then inverting everything. So we have all possible permutations of A, B, and C, and then we just plug them into each one of these AND gates. That's it. So that's all that is. But if you wanted to build that, that would take a lot of gates, a lot of ICs, right? So that's why this IC is there. All right, that's why someone invented this IC. All right, so that's that one. All right, let's look for 74 HC. We'll look for HC T 138, which means this can be driven by TTL chips. That's what the T is, HCT. Here it is here. All right, and same thing here. All right, and then you can see this a little bit more modern, right? A little bit more modern, last updated 2003, a little bit cleaner, right? A little bit cleaner. Now you can tell this is vectorized and it wasn't hand printed back in the 70s. But the exact same thing, but it's just an HC. It's a CMOS device, all right? Same design here, maybe a couple little changes, all right? And one thing is, though, this thing can drive, let's go right here, V output high, showing, you know, the voltages, V output high 4.4, V output low, and so forth. And then the current drive of this thing, you know, how much current this can drive. And if we go back here, I believe, yeah, so output can drive up to 10 LSTTL loads, all right? And so inputs are TTL voltage compatible, and it can drive TTL loads. And then if we go back to the actual TTL version, which is the LS version here, right, we can look at some of its current and some of its parameters and the electrical parameters here. And so what we're looking for is I output high, all right, so 0.4, minus 0.4 milliamperes when you're outputting high, and that's just, remember the negative is just because of the direction of the current, and then low level output current is 8 milliamperes, all right, and there's two different versions of it. This one only puts out 4, this one puts out 8. So anyway, and then the propagation delays are also important. So from enable, so let's just say the thing's already enabled, and now we're trying to do a selection here, right? So a binary select. So and then let's say we go through the largest delay, which is say 3 levels of logic. So you're looking at, you know, pretty bad, up to 40 nanoseconds, 30 and 40 nanoseconds to get a result out. 30 and 40 nanoseconds because of the architecture. Now, if we go to the HC, and remember, this all matters for your maximum clock speed. If you're going to clock some of this stuff and do some of this stuff and need a result, right? You care about these propagation delays, and that's why you might use different logic families. Here again is the propagation delay. So from inputs, and again, we'll just say enables are enabled. They've been enabled for a while. And then from input ABC, and then if you look at some of this, 54 and 50. So typically the HC technology will be slower than TTL, and that was one of the things. TTL burns a lot of current, but it's a little bit faster, all right? But now the LVC technology is very fast, all right? And it's also compatible. So let me show you that. 74 LVC 138. And that's a low voltage CMOS, right? Now, of course, this runs at 3.3 volts. You can't run it at 5 volts, but it's very fast. I don't think there'll be a dip version of this. There's usually not dip versions of LVC. They're usually all surface mount. All right, so a couple interesting things. Look at the current drive on here, 24 milliamperes. So this thing can really drive a ton of current, right? Very, very powerful, and it's symmetrical. But the voltage range is 1.65 to 3.6. So you know this is typically going to run at 3.3 volts or 1.8 volts. So you cannot put a 5-volt power supply to this, but this will actually drive a 5-volt TTL. So it's this 3.6 is high enough to drive it. All right. Now the other cool thing is the LVC. You can put 5-volt inputs on it. The inputs are tolerant to 5 volts and you won't damage them. So that's one of the cool things about it. Let's go look at this IC here and let's see if there's any architectural changes from our memory here. So if you remember what the other schematics look like. So again, looks almost identical, doesn't it? Looks almost identical. But one of the interesting things here is if we go through here, of course this is very modern, so this is, let's see, when was this updated? In 2016, right? So this looks like a, a modern kind of a document, and it's 37 pages long. If you take a look now, remember, let's go back here, here is the 1972 version, right, of the original LS138. It's 1 2 3 4 5. Let's go down here. Yeah, so the actual IC is 1 2 3 4 5, roughly 6 pages, and the rest of this is just all TI's extra information they throw into these data sheets. But if we look at this one now, so this one's 1 2 3 4 5 6 7 8 9, 10, much more electrical explanation and timing and experimental, 12, 13, 14, 15, 16, showing you how to lay the thing out better and all that. Then we get to TI. So it's, basically twice as big, right? And it shows you all kinds of testing information. Now, what I wanted to look at was the propagation delay. So again, sorry for scrolling if this bugs your eyes, but let's get here to, here we go. So here is the switching characteristics. All right, remember you've got DC, AC characteristics, and sometimes they'll call these things switching characteristics, which is the operation of it. So different things here, switching characteristics of the, we want the 7.4 LVC 138, and here it is here. So from input, these are the different inputs to output. So let's just talk about A or B or C, propagation delay. So you look at these things right here. So if we're running real low voltage, it's pretty slow. But if we pop this thing up to 3.3 volts, we're coming out at about 6.7 nanoseconds, which is nice. So very fast. So if you're running this at 3.3, you're basically anywhere from 5 to 8 times faster than the LS and HC versions of this. All right, so just much faster, much better, and much lower power version of the chip. Okay. All right. So so that's that. So now let's take another look at what this thing looks like here. So all of these things typically have 3 inputs, and they may call them slightly different things, and then they've got 3 enables, and no matter who the manufacturer is, it's always the same. If it's a 74LS138, here's another thing I need to mention. I don't care where you buy this from, TI or NXP or Philips or whatever the company may be. If it's a 74LS138 or 74LS08, or if it's the chip ID is the same, the chip will operate and have the same functionality. It may be faster, it may put out more current, and the pinout will always be the same also. Okay, these pinouts are always identical, but the manufacturers may change what the labeling of the pins are just a little tiny bit. So here it's ABC, it might be A0, B0, C0, it might be S0, S1, S2, etc. So they might change these things a little tiny bit. Typically these always kind of stay Y out, and then here you notice they're calling them all Y out, Y0, Y1, Y2, Y3, and they're not putting bars over them. We can see they're inverted here. These are all NAND gates, right? So we know these things are active low, right? But they're not putting the active low on the outputs, all right? So you got to just read things and be careful and test things out. All right, so here's what the chip looks like, and let's get, there's the dip version of it, all right? So, so there is a dip version of the 74 LVC 138. All right, so let's go ahead and let's go to the simulator and just kind of build something up real quick so you can kind of see this working, see how to hook it up, and then we'll go build it on the bench. All right, so we've basically got our 3 inputs, we've got our enables here, we've got our ground, we've got our power, and we've got our outputs, okay? Here we go. All right, so again, we're using Proteus, all right? And the reason why is because it has simulation. So when we do circuit design and schematic entry and layout later, at the last part of the course, we're going to use Circuit Maker online, but it doesn't have simulation, and we like to use simulation. So remember, if you haven't installed Proteus, you can go get it online. There's a free eval version, but you can't save, but you can definitely use it to look at this stuff. All right, so I've already got a few parts in here. So let's see, here's a 74 LS138. Now, I don't really care about what package it is right now. We're just doing this for simulation, all right? So here we go. So we have the IC. So right off the bat, let's do something where maybe we have 3 input switches, right? And then we just have some LEDs. So as we toggle the switches and we put in different codes on A, B, and C, we just turn on these LEDs, okay? So I'm going to start it off. All right, so first thing is, let's enable the chip. So we got E2 and E3, which both need to be grounded. All right, so let's do it. There's a ground there. There's a ground there. Simple as that. Next thing is let's get a power rail up here. So this will be power. All right, and I'm going to call this 5 VCC. So 5 VCC, which I'm going to hook that to 5 volts at some point. All right, so that's going to be our power. All right, and then let's see what else here. Now, notice you don't see the power on this IC. It's there, right? So the IC has 16 pins here, but you don't see it on here. This is just because it's a representation of it in this tool. So if we were to click on it, if you care, and remember we're not really learning Proteus, you're just kind of following along here, you can see these hidden pins here. It's not showing the pins, and ground goes to ground, and then it says V sub CC goes to V sub CC, and I'm going to say that goes to 5 V sub CC, okay? All right, and so even though you don't see it, those pins are there. I don't personally like that, but that's just the way that this tool works, and we could make a different footprint if we want that showed them, all right? And you can also unhide them. So if we click on this and let's see here, hide all, let me see, I think, let's see, hidden pins. Let's see, we can say Lisa model PCB package. There's a way to get them to show, but I'm not going to worry about it. Okay, so now the next thing that we need is we need to take all these outputs and put them through an LED, all right? So let's get an LED here. So we get an LED, all right? So there's an LED, and we'll need a resistor, right? So we'll get a resistor there. Okay, and then now here's the thing. Remember, these are active low. So when these are asserted, they're going to be 0, right? Which is active low or ground. If I want the LED to turn on, I need to turn its ground side towards the I/O pin. All right, so here we go. I'm just moving stuff around here. All right, so when this is low, right, so we get a low here, which is a 0 volt, all right, so let's just connect that right there. Throw our resistor, current limiting resistor, right, and 10K is too big. We'll make that like 220 ohms. All right, now this end, where does that need to go? That needs to go to our power. That needs to go to our power, so we're just going to hook that to power. All right, so now when Y0 gets asserted, there's going to be a 0 on it, which is 0 volts. That 0 here, right, is going to be ground. So then now this 5 volts will have a path. It'll go through the diode, through the current limiting resistor, and the LED will turn on. Good. Okay, we've got to finish enabling this thing here, right? So we got the lows enabled, but we also need this high. So this has got to be high. So we'll just put it right to the power supply. There we go. So that's good. Now we just have our 3 inputs. So why don't we hook them up to 3 switches? So we get some momentary switches here. So this is a symbol for momentary switch. All right. And we're going to connect it here. And what we're going to do is we're going to make each one of these active. We're going to make them, when the switch is on, it's going to assert a low. But that means there's nothing on it when the switch is off. So we need something to assert a signal when the switch is off. So what we need is a pull-up resistor. Okay, so we're going to put a pull-up resistor right here. And that's going to pull up to our 5 volt supply. There we go. And that pull-up resistor, how big should that be? Anywhere from 1K to 10K. 1K is going to be a very strong pull-up. 10K is going to be a weak pull-up. So we're going to put 10K because we're trying not. We're trying not to waste a lot of current here, so we'll try 10K. And if that didn't work, you drop it down, maybe to 4.7 or 2.2K. Okay, so now what's going to happen here is when we turn this thing on, we're going to get a 1 here, a high, until we press this, then we're going to get a low. Okay, and we're not going to short anything out. So we need to do this for B and C, and then we need to hook up these LEDs for all these outputs right here. All right, and then the final thing that we need to do is if you're ever going to design something, even a simulation, do it correctly. So this right here, we need to show that power, right, would also have a capacitor, a bypass capacitor. Remember, every single IC needs a bypass capacitor, a 0.1 microfarad at very least, and if it's a big IC, it needs a 0.1 microfarad, and then it may be you want to put a source capacitor, a 10 microfarad or greater, to give it charge so it doesn't have to run back to the power supply. All right, so I don't want to waste too much time here doing this. This is tedious, so what I'm going to do is I'm just going to load in a previous version of this. All right, where I've already finished it. So here it is. So here's the entire circuit, right, in its entirety. So basically, we've got all our LEDs. We got all our current limiting resistors. We got everything up to 5. We got our little bypass capacitor there, which we would put by the IC if we actually designed this. We got our 3 pull-ups. We got our 3 switches. We got our enables here, and we're all good to go. So now if I were to run this simulation, we would actually see this thing run. All right, so let's do it. Okay. And of course, simulations here, I'll give it to you. It'll be in the material for the chapter, for the lecture. So here we go, running it. All right, and right now, we've got one LED on here. Now, what LED is on and why? So first, we see that this is a D7, and it's hooked up to Y7. So this Y7 is on, which means the code must be 111. All right. High, high, high. Well, it is. There's 3 pull-ups here. So on A, B, and C, it's high, high, high. So that last LED, D7, is being turned on. That's exactly what it should. And in the simulation, you see the color coding. Red means 0 and blue means 1. All right. So I can zoom in a little bit here for you. All right, so now as I change these and make these different values, we'll see these LEDs turn on, right? So let's back it up here so you can see it all at once. Okay, so here we go. So just as I do this, so see that? I'm changing it. See D6 there, right? Now, but I can only press one button at once in the simulation, right? But the simulation allows me to hold the switch down. So why don't we let's get code 000. So to do that, you press this little icon here, this little icon here, little icon here. Now we got 000, and sure enough, D0, which goes to Y0, is on. That's exactly what we want. Let's do 101, 101, 101. All right, so that means that's off. That one's the switch is on. That would give us a 0, and that one would be off. So we have 1, 0, 1. Yeah, 101, right? And we got 101, which is 5. And there it is. There it is. Y5 is on. So it works. That does exactly what we expect it to do. Okay, so now I know that we simulated it and we could just move on, but let's keep building things, because by building things sometimes I make mistakes, and that helps also because we can see something or maybe learn something from it. But let's actually take a 74LS138. I'm not going to build all of this, it's too much, but let's build the first 4 bits of it here. So we'll do 4 LEDs. And what we'll do is we'll only have the A and B input on 2 little momentary switches, and then we'll just take C and we'll pull that low, all right? So that basically with A and B, we'll be able to get Y0, Y1, Y2, Y3, which is equivalent to our 2 to 4 decoder, which was up here, right there. And basically, we're just going to implement that using the 3 to 8 decoder. So the point is that just because it's 3 to 8 doesn't mean we can't use it for a smaller version, a 2 to 4. And in fact, you could use it for a 1 to 2 also. So it's great because you can do all 3 things with it, okay? All right, so we're going to go onto the bench and do that. Now, before I do that, let's see. Do we want to implementing logic functions with decoders? Yeah, let's talk about this. Let's talk about this real quick. So what's interesting here is each one of these outputs represents a permutation of the input variables, right? So you got A, B, C, or X, Y, Z, whatever you want to call them. And we have all the different versions, 000, 001, 010, 011, 100, and so forth, the 8 different permutations. And whenever one of those 8 permutations is on here, right, we're going to get one of these outputs is going to be asserted low. In other words, this decoder tells us when we have that input. So say if we had a function that we want to know when these 3 inputs are 1, 1, 1, When it's 1, 1, 1, we're going to get 1, 1, 1. We know that Y7 is going to be asserted. All right, so if it's 1, 1, 1, Y7 is going to be asserted. Great. Now say we also want to know when it was 0, 0, 0. Well, when this is 0, 0, 0, Y0 is going to be asserted. So if we take Y0 and Y7 and we put those into an OR gate, right, then we can, and then we'd have to invert them, right? But if we put it into an OR gate, that's basically a sum of products. But the decoder takes care of all the products for us. So the decoder gives us all of these products, all possible products of the 3 input variables. All right, so that's very, very cool, and that's why it says the outputs of the decoder map directly to the minterms, right? It has all 8 minterms, and here they are here. Y0 is there, Y4 is there, Y7 is there, and then we just do a double invert on it so that we can get positive logic version of it. So read about all that. Okay, and then the next thing we're going to talk about is display drivers. Good. So, all right, so let's right now go to the bench and build this circuit right here. Okay, so I will see you in the next lecture, and we're going to go to the bench. All right, bye. All right, so let's assume that this is, we'll assume that this is Y4, and we'll assume that this is Y0. All right. Okay, so when Y0 bar is 0 and Y4 bar is 0, or any of these combinations, all right, that's what we want to kind of figure out here. So when either one of them is 0, we want to output a 1, all right? So when either one of them is 0, we want to output a 1. So what we want is, when either one of them is 0, or they're both 0, but they'll never both be able to be 0 because you can't do 2 different patterns at once, right? So, but that's okay. That would be a don't care state because it's never going to happen, all right? So anyway, if they're both 0, we want to output a 1. If one of them is 0, we want to output a 1. If this one would be another 1, but if they're both 1, we want to output a 0. All right, so the question is, what logic function is this? Now we could bubble push here and do that graphically, but let's kind of do it through a truth table here. All right, so what is this right here? So if we look at this right here, so this is what we're trying to figure out. We're trying to figure out what logic function is this right here. Let's use a different color for that. And if you can already see it, right, then good. But if not, let's work through it. All right, so let's see, what would an AND be? What would an AND be? So 0, 0 would be 0, 0, 1 would be 0, 0, and that would be 1. So that's an AND. So what would a NAND be? Well, if we just invert that, we get 1, 1, 1, 0. 1, 1, 1, 0. Look at that. That's what it is. It's a NAND. All right, and just for kicks, if we do OR, we would get 0, 1, 1, 1, and then NOR would be 1, 0, 0, 0. So what we want is the NAND, all right? So that is the one we want. So all we have to do here is just put a NAND gate here, just like that. All right, and then we're done. So this this output will be high, all right? This output will be high when Y0 is low or Y4 is low, or both are low, okay? So then we can take that high output, we could put that directly into an LED like this. So here would be an LED. We could put another current limiter if we wanted to ground like that, and then we just connect that together. And so this output will be high when Y0 is low or when Y4 is low. All right. So now let's add this to the circuit for fun. All right. So let's add this to the circuit. So 74 LS LS00 is a quad 2-input NAND gate. It's a quad 2-input NAND gate. So we can go take a look over here, back here, and DigiKey, and we'll type in 74 LS00. All right, and here it is right here, and we'll open it up. And sure enough, it says quadruple 2-input positive NAND gate. There's the symbol and the DIP package. If we, let's see, this is it right here. So the very first gate is on pin 1 and pin 2 and pin 3. So input, input, output. So all we need to do is hook power to ground here, V sub CC up here. We'll put another bypass capacitor, and then we're just going to put those 2 terms that we want will be in here, and this will be our output right there. Okay, so that's what we're going to add right now. So let's go ahead and find a 7400, and let's add this to our circuit. All right, so let's go to the bench. Okay, so what I've got done now is I went and found a 74 LS00. In fact, this is a 74 ALS. This is advanced low power Schottky. It's just got some better features than the LS. You can look up the advanced low power Schottky if you like, but nevertheless, it's got the same pinout as the standard 74 LS00 NAND gate. So pin 1 and pin 2 are the inputs, and pin 3 is the output for one of the NAND gates. All right, so everything is kind of the same. What I've done though is, because we had to fit this IC here, I moved over everything here and kind of created some space so everything's on top of each other. Now you can also see I've added these limiting resistors, current limiting resistors now. So why did I do that when it worked just fine? Well, the reason why is, before we were just outputting each one of these directly into the LED, and we really didn't care what we did to the logic level, meaning how much we pulled on it to light the LED. But now we do care about that. So because the LED is a very heavy load, right, we're going to change the logic level of these outputs, right? And we don't want to do that. So we want to put a current limiting resistor in here. So these wires right here, the signals here, a 0 will be a 0 and a high will be, reasonably close to 5 volts. Without that, if we drive directly into these LEDs, when these LEDs turn on, we're going to draw a lot of current, and that's going to mess up the output voltages. So we need to put these resistors in here. All right, then again, we've just got this IC, this NAND gate powered up. We got ground here at pin 7. This is a 14-pin chip, pin 7, and then we've got at pin 14, we've got high and a bypass capacitor. So all we really need to do now is just hook 2 inputs up to our terms that we want to monitor, which we're going to monitor M0 and M4, and then the output to an LED. So here's already an LED right here ready to go. Okay, and remember, this is going to output high, active high, so the LED is going to go to ground. So we've got, this is an active high output from this NAND gate. It's going to ultimately be an active high. Okay, so let's get a output here. Matter of fact, we'll use purple for the output, so that's going to be on pin 3, and we're going to hook it directly up to the LED. Again, if we wanted to take this output and go someplace else, we'd have to put a current limiting resistor, because we're gonna draw too much current. But since it's just one LED and it's just the output, we're gonna go back to no current limiting resistor, so the LED is nice and bright. All right, then we want M0 and M4. So here's M0. This is the M0 output. All right, or when all of these are 0, 0, 0, when ABC is all 0, 0, 0. So that'll go to one of the NAND gate inputs. Then we want M4. And remember, we count by 0 here. So 0, 1, 2, 3, 4. So this is M4 right here. Here it is. And then I'll put that to the other input of the NAND gate. Okay? All right, so there's our circuit. So if I turn this on, it should basically operate the way it did before, except now this will monitor M0 and M4. So when either of those are asserted, this LED will turn on. Okay, so let's see if that's what happens. It's powered up. All right, so normally we get to, remember, we're going to get the M7 out, or Y7, right? And that's because there's always a 1, 1, 1 on here, right? Okay, so now if I press all 3 of these, that'll give me 0, 0, 0. That will turn on M0. M0 is one of the terms we're monitoring, so this LED should turn on. Here we go. Ready? And I'll just kind of move it across, and it did not turn on. So what did we do wrong there? Oops. I did exactly what I didn't want to do. These wires need to go on the other side of the resistors here. All right. And that's good, because every time we make a mistake, and that's why I kind of do these in real time, because if it's perfect, we're not going to learn anything. So remember, these LEDs are going to clamp the voltage at like 2 volts, right? 2, 2.2, 2.3, 2.7, whatever. So we want to be on the other side here of these resistors, all right? So this way we're going to either get a 5 or a 0 volts, and that's what we want. All right, let's try it again. All right, so here we go. We're going to start moving across until we get M0. There we go. Now the LED turned on, all right? And that's what we want. So remember,
when you have these outputs from digital outputs, you got to be careful if you load them, right? So that wherever you're going to take that output and take it to another input of another IC, make sure that the output can go high and go low, right? If you put it in the wrong place, it'll just stay high, or it'll always stay low, or it'll stay someplace in the middle, and we got to be very careful of that, all right? And plus, we're drawing a lot of current here with these LEDs. All right, so now let's try and get M4. So that's M0, 1, 2, 3, 4, right? So let's see. It would be that one. Yeah, so there's M4 right there. So basically when I have these two buttons 0, 0, right, I just get a 1 right there, right? And then there's M4. And then here's M0. So M0 or M4, we'll get it, and then we let go, and that's it. So there's a fairly complicated digital circuit. So we've got a decoder, which is decoding all of these inputs, and then basically we said, hey, when either M0 or M4 is asserted, either of those, right, then I want another circuit to detect that and then give me one output. And so that could be a memory access, that could be a sensor, you know, who knows what these things represent. But that's how you build it. And then be careful if you want to monitor things with LEDs. These things draw a lot of current, so you got to watch out. If we just hook these wires up directly, we would be okay. But if we want to put these LEDs in here, we're drawing a lot of current. So if you do want to put LEDs, say if you're going to build a circuit professionally, a lot of times what you'll do is you won't actually hook these wires directly up to these LEDs because it draws too much current. You'll put what's called a buffer or a driver, and we're going to learn about that in a little while in the next lecture, or couple lectures. And basically what happens is we'll take all these outputs and we'll put them through a driver or buffer, and that'll amplify it and insulate the signals so that we can put, you know, we could put motors on the other end if we wanted to. But that way the current drain of the LEDs won't affect the logic levels, because as we draw more current, we're going to affect that 5 volts, going to drop, 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 right? So anyway, so that's it. So there's a cool little circuit using the decoder, and that's it for this lecture. So let's stop here and let's go back to the text, and we'll go to the next kind of class of IC that does something interesting. So I'll see you there. Bye.
Welcome back, and we're continuing our coverage of digital ICs, and now we're going to be talking about display drivers. Also, one thing to remember, you know, when you design a modern circuit, you're probably not going to use individual discrete ICs anymore. You would use some kind of programmable logic or even a microcontroller, right? However, a microcontroller is still a processor that runs on software, and if that software crashes, then everything crashes. The nice thing about pure hardware is there is no software to run, there is nothing to crash, so the hardware operates in real time. So that's why, you know, we prefer hardware for, you know, mission critical elements of a circuit, right? So these days, though, there are programmable logics, you know, complex programmable logic devices, FPGAs, field programmable gate arrays, all kinds of different technologies, but you know, they're not easy to understand how to use. So still, if you're building something, say you want to add some functionality to something, you know, to do a test for something, a comparison for something, count something, display something, a lot of times it's really easy just to add a couple chips, and that's why we're going over all this information. And also, this is a fundamental, this class is about fundamentals. We're going over all this information, but of course you would use a more modern logic family. You probably wouldn't use an LS logic family. You would use like an LVC or an LV logic family, but still the whole idea is we want to learn a bunch of different kinds of ICs and how we can use them, and then you can always use programmable logic or microcontrollers later. All right, so let's talk about display drivers. So we just talked about decoders, and the whole idea of a decoder was that, looking here on the screen, we had 3 inputs. In this case, it was a 3 to 8 decoder, and on every different permutation of the inputs A, B, and C, the binary input, you would get an output that was active low in this case. So Y0 through Y7, which were active low. And there's an active high version of this as well. There's 2 to 4, there's 4 to 16, there's all kinds of different versions of these decoders. But the 74138 is kind of a common one that everyone uses, all right? So that was a decoder. Now another kind of decoder is a display driver. And the whole idea of a display driver is, so let's say that you're building something and you want to put up just some simple 7-segment displays, right? Maybe you're making a clock, maybe it's some debug information, maybe it's a voltage, maybe you want to make a power supply and you want to display a voltage or a current, don't know. But the whole idea is, how are you going to convert a binary number, some bits that represent a number, into digits that can be viewed by you or a customer or whatever it is that you're doing. So they have these 7-segment displays, and there's all kinds of these. There's thousands of these. If you go search on DigiKey or Alibaba or eBay, you can find countless really cool 7-segment displays. And the reason why they're called 7 segments is if you sit here and count, let's count clockwise, or let's go counterclockwise actually. Let's see here. Yeah, let's actually go, we'll go clockwise because they're labeled and starting from A. So anyway, 1, 2, 3, 4, 5, 6, 7. And they're labeled, you can see the labeling here. There's kind of an industry standard for labeling: A, B, C, D, E, F, and then the center segment is G. All right, so the whole idea here is, say you wanted to put up the number 0. Well, if we want a 0, then we would light F, A, B, G. No, we wouldn't. We would light F, A, B, C, D, E. We wouldn't light G. That would give us a 0. Then if we wanted a 1, we would want these two on, which would be B and C. We could also turn these two on, right? You know, we could turn F and E on. That would be a 1 also. If you wanted a 7, we would want these 3 on right here. So it would be A, B, and C. And you get the point. All right. And then there's variations of them that have two different decimal places. All right, some just have a decimal on the right, some have a decimal on the right and on the left as well, and then some have it on the left. All right, and so anyway, all kinds of different versions of these things, and we're going to take a look at these on the bench. But what we need when we get a 7-segment display are a couple things we have to pay attention to. One, we have to be able to figure out what the pinout is. All right, so this A, B, C, D, E, F, G thing, the display driver that we're going to look at down here. And then here's an example of turning on that 7 we were just talking about. And of course, I want you to read this material here, this display driver section, which is 6312 in the book. Obviously, read this all in detail. But, and sorry for the scrolling. All right, so the display driver we're going to look at is called the 7447. This is a really common, this thing is really old. It's from 1974. And so there's different versions of it. There's LS version, HC version, and so on. You can find different versions of it. Anyway, so here's what this thing does. So if you put in the code 0, 1, 2, 3, 4, 5, it will turn the digits on and make them look like this, all right? And so the code you put in is on 4 bits, A, B, C, D, and the output it enables on the 7 segments that are labeled like this. And so that's important. So you can see A, B, C, D, E, F, G. That's the convention. So whenever you have your 7-segment LED, you have to figure out what goes to what, right? From the data sheet of that particular 7-segment. And if you buy these things off eBay or Alibaba or made in China, a lot of times they won't have any data sheets. So you have to figure it out. And I'm going to show you how to do that. All right. So here's the truth table here that shows how this IC works. And the IC has power, V sub CC, and ground. And then it has 4 digital inputs, and then it has these inputs here. This is lamp test, so when this is low, it turns all the segments on, so you can just test and make sure the segments all work. And then this RBI and BI and RBO, these are blanking inputs, and what these are for is, so like say you're displaying, say you have 4 displays, and it's going to put up a number, and so it's going to count 0, 1, 2, 3, 4, 5. So when you have, say, the number 1, right, the other displays all have zeros on them. So you may want those zeros displayed or not. So it would be 0001, 0002, 0003, then up to 9, then it would be 10. And every time as those digits kept filling up, there would be leading zeros. So you may not want those zeros to display, right? And that's what those blanking inputs are for. So we're going to tie those all high because we're not going to use those. All right. So anyway, and then it shows for any possible input what the outputs will be. Now, the 7447 is designed for a common anode display. Common anode. So that means that when when the code is input on the 4-bit input here, the segments get turned on by outputting lows, zeros. So we're going to hook the display up to a positive voltage, and then the 7447 is going to turn each segment on with a 0 or a negative, a ground. All right, so you got to be very careful. So there's two kinds of displays, common anode and common cathode. Common anode is exactly what it sounds like. So for every one of those segments, they're like 7 different LEDs. They're all connected up to the anode in common. So then you connect the cathode of each to turn each one on. We're going to look at that. If it was common cathode, all of these segments would all be connected to ground. That's the common cathode, and then you connect the anode, all right? And then there's two versions of the IC as well. The 7447 is the common anode version, and then I believe the 48 feature active high outputs for common cathode. Yeah, the 48 and 49 are both for common cathode. All right, but I prefer the 47. All right, so anyway, so that's that. Now let's see what else we have. Look here, and then this is just showing some of these signals again. We're going to look at the data sheet in a moment. All right. Okay, and then here's kind of a simple design, and we're going to look at this as well. So in this case, you can see that we have lamp tests. We've got this RBI, we've got this BI, RBO, and these are, lamp tests, and then these are blanking inputs and blanking outputs. So notice they're all active low. That's what that bubble means, right? The bubble means 0 or invert. So these are all active low. So we're just going to tie those all high with a 1K. Then we've got our 4 inputs, and this is a dip switch. We've seen these before, so this is a nice way to get 4 inputs here. And we're going to put that into A, B, C, D, and A is the low bit, right? So we're going to put those in there, and then we're going to tie those all high with these pull-up resistors up to V sub CC. Then the switch is all going to go low. So whenever we turn the switch on, it's going to put a 0 there. So you got to kind of think a little bit backwards. So when the switches are all off, you're going to get 1, 1, 1, 1, which would be code 15. So if we look up here, what's code 15? You could look here. So here's code 15 right here. So all of these are off, which means they're all they're all zeros, right? So, and here it is right here. There's code 15. All right. So off in this case means they would actually be highs. All right. So nothing would turn on. All right. So anyway, then you can also see we have 0 through 9 is valid, but then 10, 11, 12, 13, 14, 15 are all bizarre symbols. So it's like this C, this backwards C, this little U thing, this kind of 5E thing, and this 6 thing, or upside down F. Now, so why didn't they implement, say, hex in here? They could have made this an A, a B, a C, a D, and an E, and an F, right? And there are display drivers that'll do that as well. But to decode all of those, to decode all these extra values here, that would have taken more logic. And the 7447 is designed for decimal display. It's not designed for hexadecimal display. However, a lot of times we just want to think in hexadecimal. So it's nice if we can just put 4 bits up to one of these display drivers and they get 0 through F. So anyway, in this case you don't. You just get 0 through 9, and then you get these weird symbols. Okay. All right. So let's go ahead and let's take a look at the data sheet for this. So if you type in 74LS47 into DigiKey or Newark or any kind of parts search, we like to use DigiKey, you'll get this part right here. All right, and you can see 4.75 to 5.25 volts. So this is LS logic, right? It's a dip version, and then we'll go to the data sheet here, right? And the data sheet was revised in March 1988. So this is still an active IC. We're going to play with the dip version of it here, all right? Which looks like this. So again, we've got to see where all these pins are. All right, so they're not exactly where they're not in a clean positioning. It would be nice if it was A, B, C, D, and then all that, but they're kind of all over the place. So you got to take a minute to figure that out. All right, so we got that, and then it says what the different versions are: the 7447, the LS47, the 74, the 54, and so forth, and how much current they'll output. And then kind of a symbol here. This is kind of a symbol of it, all right? So, and then here, again, is that table that you saw, something similar to that table, all right? So basically, we just need to hook this up based on this data sheet and get it to work. Now, one cool thing is, you'll notice that if you look if you look here, 74LS47, the outputs are open collector. All right, so that means it's open collector, meaning there's a transistor on every output and it's open collector. So when the output is on, it basically drives the collector to ground, and then you get a ground signal. So you get no high, you just get a ground signal, and it's syncing right to ground. So the other nice thing is, if you look at the amount of current, it'll sync up to 24 milliamperes. This 74LS47 will sync 24 milliamperes here. All right, so that lets you know that. And then the other thing, we can hook these, we can hook the 7-segment directly to the IC. We don't need series resistors in there. All right, we can put on the common anode, we can actually put a current limiter if we want, maybe a 10 ohm just in case, but we don't have to put series resistors. So let's go to a simulation here. So I've already kind of made this, and it's under Crash Course EE 7-segment decoder 01. That'll be in the assets for this lecture. All right, and if you look at this, we've got our 74LS47, and I've got power hooked up to 5 V sub CC. And of course, obviously we're using Proteus again. We use this every time. You can download this for free. You just can't save and manufacture things, but you can surely load and evaluate these things. All right. And so we've got our IC right here, and then the symbolic version of the IC puts all these signals in a nice place. So we got A, B, C, D, we've got all the blanking inputs, we've got the lamp test, then we've got Q, A, B, C, D, E, F, G. Then this 7-segment LED display right here, this is a simulation only. So it's really nice because it's A, B, C, D, E, F, G, and then it just has its power up here. And obviously this is common anode because I've got the anode up to +5 here, all right? Then we've got our pull-up resistors to pull up our 4 bits on our inputs, because when we have nothing on that, they'll just float. All right, so we want to assign them to something specifically. So we put up some weak pull-ups here, 10K. Then we've got our 4-pin, our 4-switch dip switch, so we can get some zeros in there, all connected to ground. And then we have this lamp test, and the other circuit inside of the book had all of these pulled high, but in this case we've only got the blanking inputs pulled high, and we're going to leave lamp test open so that at a push of a switch here we can check if all these segments work. Now remember, this doesn't map to anything in reality. This is just an abstraction, so we're going to have to put an actual 7-segment display, and we're going to have to figure out where A, B, C, D, E, F, G segments are and the common anode by trial and error or a data sheet for that particular part. All right, so anyway, so this is it. And a couple other things. Always put a bypass capacitor on every one of your ICs, at least one. So we put a 0.1 microfarad for noise. That's going to go to this IC right here. And why don't we just rename that U1, huh? We'll rename that U1. Let me save it. And then also, because we're drawing a lot of current out of the power supply to light these LEDs. Now, if you got all 7 of these segments on, that's going to pull a bit of current. So we're going to have a 10 microfarad capacitor right here. And this is going to be a capacitor to source current to the display so that it doesn't have to go all the way back to the power supply. We're not going to put a 0.1 microfarad because there's not going to be much high-speed noise, right? This digital display is going to change in human time, right? So we can see it. So it's not going to be changing at, kilohertz or megahertz or gigahertz or anything like that. But no need to pull on the power supplies. We're just going to put this 10 microfarad here to reduce some noise, all right? So let's go ahead and run the simulation. Okay, and so now you see there's a 0 on there, right? And if we go here to the switch, we can actually turn these things all on and off. So if I turn them all off, or excuse me, if I turn them all on, so 1111, remember if we look at the data sheet 1111, what does that do? Let's see if we can find that. 1111, there it is here. So 1111 turns all the segments off, and then you'll get a blank. And if we go back to the simulation, we sure did. All right, so now let's put the number 1 there, So these would all be zeros, all right, and they're not, sure enough is 1. All right, 2 would be, this one would be on, this one would be off, there's 2. 3 would be, these 2 would be, the lower 2 bits would be on. 4, this one's on and these are off. You see me just toggling through there, there's 4. And then to get an 8, there it is, we would turn that one on, right? And then to get a 9, we would turn that one on, and then there you go. Now, let's put some of these that don't exist. So there's one right there, right? So in this case right here, we've got, what code do we have here? So it's kind of hard with these colorings here. So this is a 0, 0, 0, let's think about this, 0, 0, 1, 0. So this should be, so 0, 0, 1, 0. Let's see here. So this is on, and again, it's like, which way are these things, what color is what here? Well, I'm confusing myself too much there. So anyway, this backwards C, what code is that? Let's make sure, just go look at it. The backwards C is 11. Okay, so the backwards C is 11. So let's go back to the simulation. Yeah, the backwards C is 11. All right, so to get the 11, so we've got, yeah, so 1, 1, 0, 1. Right, so that would be 3 and 8 is 11. All right. So anyway, in this, they could have a better coloring, so you could tell which way is which here. Anyway, so that's that. So that is the display. Now let's try the momentary switch, which is the lamp test. So this is going to override whatever code is on here. So let's put a valid code here first. Let's put something on here. There's a 9 on there. All right. So now the second we hit the switch, all the segments turn on. See that? All the segments turn on, which of course makes an 8. But if there was a decimal point there also, right, ideally that would turn on as well. But remember, there's only 7 segments. To control the decimal, we would need an 8th segment. So say if you did have a decimal, but all you had were 7 447s, right? Then what you might have to do is we would decode what the input is, and then that along with something else, maybe we could then turn on the decimal manually with some extra circuitry. There's another reason why you might need some extra circuitry. All right, so what we're going to do now is we're going to build this circuit over there with a real 7447, but before we do that, we're actually going to take a look at some 7-segment displays and kind of figure out A, B, C, D, E, F, G on them and just kind of show how you would go about doing this so that you have an idea. All right, so I'll meet you on the bench. So what we're doing now is we're going to actually hook up some of these 7-segment displays, and let me get rid of some of this glare here. So you can see I've got them on the little anti-static foam here, and let's get that to focus better. All right, so I've got lots of these displays, and some of them are common anode, some of them are common cathode, but it's not really labeled on them at all. So if you take one of these displays and you look at it, you can typically find a part number someplace, like this right here, LTS 4580AG, and you might be able to Google that and find it. And then you can kind of look around and see what's going on here. So now in this one right here, just looking at it, that might be the common connection where that's going to this pin, maybe not, So anyway, I know that these are green, so these are all green. And that one's got a really big decimal, and these have decimals on both sides. And then I know that these are common anode, these are common cathode, and these are yellow, and that one's obviously red. All right, and same thing. You can just look at it, and you can find the part. This is MAN 4610A. So, as a matter of fact, let's go back on the computer there, and let's look up. Let's look up this one. This one I kind of like better. It's kind of this red. So this one has a part number. Let's see here. Bear with me here as I get it to focus. LTS 312AHR. Let's see if we can find that. So let's go on the computer and take a look. So we're back here on the computer, and just for fun, we're going to actually probe this. But just for fun, let's see if we can find this. All right, so we're going to type in LT and LT S312, S312, all right, and AR datasheet, so that's kind of looks good. Here we go right here on Octopart, it found it. Here's a PDF, and let's see, Light-On, which is a manufacturer of LEDs and optoelectronics, so this is looking positive. So there we go. So this part right here, which is this LTS 3112 AHR AR, we can actually find it here, and so it has the mechanical. And then so you can see that this one is common anode, right? So these are all the anodes, and with the lines, these are the cathodes, of course. All right, so and what it's saying is that both pins 3 and 14 is the common anode, and then the rest of this is these are all the different segments. All right, and then they've got them labeled A, B, C, D, E, F, G, just like we would expect. All right, and then these pins here, 1 through 14. Now, typically, it's the pin out here is going to be as you would expect. So on the top left corner here would be pin 1. So this would be pin 1, pin 1, 2, 3, 4, 5, 6, 7, and then down here would be pin 8, 9, 10, 11, 12, 13, 14. So that's exactly what we kind of expect right there. All right. So we'll keep this on the screen here. So we'll keep this on the screen since we know this is an actual part number that we have. All right. And now one thing though is on this particular part, it's a little bit different here. It's missing some of these pins, so they're not all there. So we have to kind of imagine that they're there. So take a look at the screen again on the zoomed in screen here. So basically this is 14 pins. So it's pin 1 is this top one, pin 1, 2, 3, then 4, 5, and then 6, 7. But 4 and 5 aren't there. They weren't broken off, but they're just not there. And same thing, here is pin 8, 9, 10, 11. There's pin 12, which is not there, 13 and 14. So even though the pins aren't there, we still kind of count them when we're iterating through it. All right. So let's go onto the solderless breadboard. Let's see if we can turn this on based on the data sheet. All right. Okay, so here we are on the bench, and I've just plugged in this 7-segment display, and here's a 7.4 LS47 waiting for us to wire everything up. So what we can do here is, as a matter of fact, we'll leave that there, and we'll bring this just a little bit closer. Okay, so now we know that the common anode is supposed to be pin is supposed to be pin 3 or 14. Now, when we drive this IC from this, we don't have to put any current limiting resistors, but if we're going to drive it without it and just hook it up to the 5-volt rails, we could damage it, so we need to put a current limiting resistor. So what we're going to do is on the anode itself, we're going to put a current limiting resistor to limit power into the circuit. The only problem with that kind of approach is that the current limit from 5 volts is going to go into the common node, and then we're going to limit the current more and more and more as we turn on segments. So we wouldn't want to do that when we're driving the segment, because each segment that gets turned on will get dimmer and dimmer and dimmer. But just to test this, it'll be okay. All right, so first thing is, let's go ahead and turn the power off, and you'll notice a little red light will turn off. Okay. All right, so it says that pin 3 and 14 are common anodes. So here's pin 1 right here. All right, so there's pin 1 right there. All right, so just make sure you kind of remember that. So that's pin 1 right in the corner there. All right, so 1, 2, 3. And what I'm going to do is I'm going to put a 220 ohm resistor there, pin 3, so 220 ohms, so that's it. Now what I'm going to do, and this is what I want you to do when you're trying to figure this out, is now what we're going to do is, here's ground. We're just going to plug a wire into ground. And then we're just going to start probing around and see what's what. So what we'll do is, we already know how this one works. So we're going to play with that one, and then we'll grab a yellow one real quick. We'll play with that one, and then we'll play with a common cathode, which is this green one here, all right? But I just want you to see how you do this, because a lot of people think they don't work, and they're like, what's going wrong? So remember, it can be common anode, common cathode, and then remember, if you're going to test it, put a current limiting resistor in here, you'll damage it. Okay, so let's go ahead, let's zoom in a little bit. Zoom in a little bit so we can see the action. Stop that from shaking. All right, I'm going to turn the power on. All right, so if I'm looking at the data sheet here, looking at the data sheet, segment A is pin 1. All right, so here we go. So A is this segment right here. So it's A, B, what is it? No, it's A, B, C, D, E, F, G, right? That's it. A, B, C, D, E, F, G, I think. All right, so here we go. Pin 1. There it is. So that's A. So this is A. So there's A, and then now I'm just going to go here. Here's pin 2. All right. Pin 3, we don't do that. That would short it. All right, there's pins, let's do 1, 2, 3, pin 4, pin 5. Remember, those aren't even there. Pin 6, oh, that's the decimal place. And then here's pin 7. And then if I look at the data sheet, pin 7 should be E. So pin 7 should be E. And so let's see, A, B, C, D, E, is that right? Which one is getting turned on here? That one. So A, B, C, D, E. All right, so that's correct. And then we'll come over here. All right, so there's that one. There's that other decimal place. All right, remember the decimal places aren't driven by the display driver. All right, now here also it said that pin, what was the other pin that was power? Pin 14. So right here, this is the power pin as well up here. So we could put power up at pin 14. So let's give that a try. All right, so we do that. And then when we do that, again, let's try and see. Yep, and sure enough, things are working as we would expect. All right, so that's working. Okay, so that's good. So this works, and it's exactly what that data sheet says. So that's cool. Now let's put this one in here. And this one, take a look here. So if we look at them, they've got the same. There's 3 and 2, 3 and 2, and I'll turn it like this. They both got 2 decimals. And then there's like 4 and 2. So they're identical. So it should be identical. So I'm going to assume that it's identical. All right, so I'm going to hook power up to pin 14, and then we're just going to go along here. And I'm trying to do this so you can see it so my hands aren't in the way. See, here we go. There we go. There's that pin, that pin, that pin. There we go. Okay, so cool, that worked. All right, and we're going to use this one for the experiment, right? But now here's this one here, right? And we could look this up. We could look this up, right? But let's just try and probe it. Okay, so now the trick here is, let's say that we got this and we just can't find the thing. All right, so what we're going to do is first we're making an assumption if it's common cathode or common anode, and all we would do is we would just try it in both combinations till we figured it out. Now, but I'm not going to tell you where, and I don't know, where the common cathode is. So what we're going to do is we've got power here going to ground. So there's going to be our current limiting path to ground. Then all we're going to do is we're just going to plug this thing in every different way here until we figure this out. So, so that's what we're going to do. So I'm going to start off, and I'm just going to plug it in like this. And then we're going to take, here's the plus, and we're just going to start touching. All right. And okay, so that turned on. All right, so that turned on right there. Okay, so, but nothing else turned on. Well, that did. So we got that one. There it is. Okay, so, well, we were pretty lucky. And I'm going to go over here. Yeah, so there it is right there. So we lucked out on our very first try. So it looks like, so pin 1 here. So pin 1 is ground. So pin 1 is ground. And then here's all the other segments here. So we're going to hook this up to power. And again, I'm always just trying to do this so you can see it. All right, so there's that one. There's that one. There's that one. There's the decimal place. And then there's no pins there. There's that one. There's that one. That one. That one. And then over here, there's nothing there. I don't think there's a pin there. Yeah, no. The first pin is right here. There's pin 1. And then this one had 1, 2, 3, 4, 5. This is a 10 pin. So it's 1, 2, 3, 4, 5, and then straight across 6, 7, 8, 9, 10. So anyway, that's how you do it. You basically just have to probe. You just have to probe it around if you can't look up the data sheet. Now in this one, of course, this says LTS 4580, and you could look it up right now. So LTS 4580 AG. Go ahead and look that up while I'm taking this apart here. All right. So we're going to use this guy right here. And that one is common anode, and the common anode is up at pin 3 or pin 14. So that's what we're going to use, and we're going to basically hook up the circuit that we had inside of the schematic, all right, in Proteus. So let's go take a look at Proteus and see what we're doing. Okay, so we're back here on Proteus. And in a nutshell, we have our 7447, 74LS47 in this case. We've got a capacitor here, bypassing that. We've got a larger capacitor here, bypassing the display. We've got a switch with a pull-up resistor going to our LT. And then we've got our blanking inputs are all getting pulled high. And then we have our 4-bit input with a dip switch with 4 pull-up resistors. So this is kind of what we want to build here. Now the only thing that we care about are the actual pins of this IC, but these are correct. So if we zoom in here, this is pin 7 is A, 1 is B, 2 is C, 6 is, all these are correct. And then power and ground are on the corners. So ground is down here at pin 8. and then power's up there at pin 16. Okay, and then let's confirm that. Let's take a look at the data sheet. Go to the data sheet here, which is right here, and we'll go to the DIP package up here, and sure, there's the DIP package, and then there it is. So V sub CC is 16 and ground is 8. And then like B is 1 and C is 2, and we go back here, B is 1, C is 2, and this is correct. I verified this. And tip, never, ever, ever assume that any footprint inside of any CAD tool is correct. A human being put it in, and they typically put thousands of them in, right? So someone made these models, put them in, and very easily they could make a mistake. So double check it, triple check it, and then check it again. All right, so before you hook anything up and design anything, check, 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 check. It's very easy to make these kind of mistakes, all right? But anyway, this one should be correct. All right, so let's go ahead and let's go back to the bench, and we're just going to hook this thing up, all right? Okay, so we're here on the bench. So what we're going to do is we're going to hook this circuit up, and I'll use some time-lapse speed up here and there as needed so that you don't have to watch everything in real time as I hook this up, but let's go ahead and do it. All right, so we've got our IC here, so let's go ahead and let's hook up ground. And ground is on pin 8, so we're going to take pin 8 here and hook it up to ground. All right, good enough. And remember, these don't have to be perfect. If you're going to build this and use it as a working functional prototype, make these wires all flat and short, but otherwise this will be good. All right, and then here is power is up here at pin 16, and we're going to bypass that. So let's get a 0.1 microfarad bypass capacitor, and we're going to bypass that from power to ground. So that's going to go just like that. Okay, so far so good. All right. Now we want to take the blanking inputs and we want to tie those both high. So the blanking inputs we want to tie high. So what pins are those? The blanking inputs are pin 4 and pin 5. Pin 4 and pin 5. So pin 4 and 5. So 1, 2, 3, 4. 1, 2, 3, 4. That's going to go here. All right, and then pin 5 right next to it. Okay, looks good. All right, and then the other interesting thing we're going to do is we're going to control that lamp test. And that lamp test pin is on pin 3, and we're going to actually hook up a button to do that. So on pin 3, we're going to hook a button up. So this is going to give us a ground here. So there's our ground. Matter of fact, we'll put it right here. All right, so there's our ground, and we're going to hook that up to pin 3. Right, we're going to hook that up to pin 3, 1, 2, 3, and it's going to go right here. Making sure we got that. But also, we need to pull that high. So we're going to pull that high with like a 10K, right? 10K brown, black, what? Brown, black, remember? Brown, black, what? Orange. Brown, black, orange is 10K, and brown, black, red is 1K. So we're going to hook this up here. All right, so far so good. So take a look what we got. So it's always going to have a high on it and then a weak high, and then when I push this, it'll assert a low, and that's on pin 3, which again, check, check, check. Yep, that's our lamp test. All right, so that looks good. So now if I turn this on, this would actually work and not do much, right? Because we don't have our display on there. So now let's go ahead and let's hook a dip switch up. All right, now if you look, I've got some dip switches here. So here's a dip switch, but it's only got 3 switches. Here's another dip switch. This one's nice. It's only got 3. It's low profile, though. I really like these. They're very low profile, but you got to have kind of a tip of a pen or something to switch them. And then here is what we're going to use, because I can't find a 4-pin dip switch anywhere. I only can find these 8s or bigger. So we can use any 4 of these. So we'll use the 4 closest ones, which will be these right here. And they're on when they're up, all right? So we're just going to pop this in here. Just going to pop this in here, just like that. All right, so now what we're going to do is we're going to have to ground 5, 6, 7, and 8. So all those are going to go to ground. Then the outputs are going to go to A, B, C, D, and then we're also going to put pull-ups up here, right? So that's what we're going to do there, right? So I'm just going to do that and kind of fast forward so you don't have to watch all that painstaking connection. So again, we're just going to ground 5, 6, 7, 8, and then we're going to pull up all of these, pull them all up, and then we're going to take wires and connect each one of those. Okay, so let's do that now. Okay, so we got those all those wires, we got all the resistors, and now so this will give us our weak pull-ups, and this will give us our zeros or our grounds when we turn the switches on. Now we're just going to hook A, B, C, D to these bits, A, B, C, D, which are going to go to 7126. 7126. All right, so I'm going to do that now. Okay, so let's check that. So we should be going 7126. 7126 is A, B, C, D. Okay, so here is 7. All right, and the next one is this one. That's pin 1. Okay, 7, 1. And then the next one, C, is 2. Here's pin 2 right there. That's good. And then the last one is pin 6. So, again, double, triple, quadruple check. Check things, and check them again. All right. So, so that's our inputs there. All right, and then now we got to do all our outputs, all right, to our 7-segment display. So now we got to do our 7-segment display. So I'm going to pop this one in right here. And then remember, we had pin 3 or 14 is power. Now what I'm going to do is I'm just going to put a teeny tiny current limiting resistor in here. We'll put a 10 ohm in here just in case, just the 10 ohm, because I never want to damage these because I only have so many of them. So we're going to put a 10 ohm right here. And I'm going to have to turn this just a little bit so I can see it. There we go. All right, so that's where power's coming in right there. Okay, so that's where power's coming in right there. Good. All right, and then again, we're going to put a bypass capacitor, but this is more for current sourcing than noise, and we're going to put a 10 microfarad. All right, so we're going to put a 10 microfarad right here to ground. Okay, so the capacitor, we got the capacitor here, the bypass capacitor, which again is just for charge storage, not so much for noise. All right, and then now we've got to hook up all of our outputs, our 7-segment outputs from our driver into our little display, all right, into our 7-segment display. So let's go back to the computer real quick and kind of figure out where things are, and then we'll just start hooking them up, right? All right, so we're back here on the computer, and you can see we've got the 7447 data sheet here. So segment A, B, C, D, E starts at pin 13, and then the last two, F and G, are 15 and 14. All right, so just kind of remember this. So starting at pin 13 is A, B, C, D, E, and then F, G is right above it. So we know that pin 13 is kind of where A is. Now, where do we want to hook those? Here is the actual display we're using. So here are the segments A, B, C, D, E, F, G, and then here are the actual pins on the IC, or on the 7-segment display. So pin 1, pin 7, pin 8, and pin 14. All right, so pin 1, pin 7, pin 8, and pin 14. All right, so a little bit tricky, So we're going to kind of look at this, and we're going to kind of look at this. So the first thing that we're going to do is we know that A is on pin 13. So A is on pin 13, we're going to go from there. All right, so let's go to the bench and start trying to hook this thing up, and I'll switch back and forth off camera so I can see what's going on, all right? Okay, so the first thing is we know that pin output A is on pin 13. So output A is on pin 13, so let's just go get that. All right, so again, let's make sure we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So here's pin 13. All right, so that's A. So this is A right here. Let the camera focus. So that's A. That needs to go to segment A. And then if I go back and look here, A is on pin 1. So that is convenient. So there's pin 1. All right, and we can probably use a shorter wire. Let me see, maybe I can use a little bit shorter wire here. And again, these are kind of going to get in the way, so just bear with it. All right, now, so B is the next one. So B is the next one, and it just goes down. So we know that that's B. Now, where is B over here? That's on pin 13. All right, so this is pin 14 up here with power. So pin 13 is right here. So there's pin 13 right there. All right, let's do the next one. Okay, we're going to do C, which is, where's C? C is pin 10, so this will be a little bit trickier. So pin 10. All right, so pin 10, and this is supposed to be pin 8 right here, is the corner pin. So again, trying to make sure, so that's pin 8, so 8, 9, 10. All right, so that would be 10 right there. So that's supposedly goes to C. All right, the next one we're doing is D. So let's do D. So this will be D right here. All right, so that's D. And D goes to pin 8, which is supposed to be in the corner here. All right, and then this is, this is how you do this. I mean, it's just kind of a pain. A, B, C, D, and then E goes to pin 7, which would be this corner here. And let me make sure I'm going to pick it up a little bit to make sure the pin's there. Yep, all right. Okay, and then remember our last two, so it's A, B, C, D, E, and then F and G are the last two. So here's F, which is pin 15, and that's the wire is a little bit short, so I'm going to pull it out just a little bit. There we go. All right, so here's F, and then I look on the chip on the 7 segment, that's pin 2. All right, so that's going to go here, pin 1, 2, and then last but not least, G, which should be the cross member. G is the cross member, and that's pin 11. Pin 11. All right, pin 11. So we can count down here. So that's 14, 13, 12, 11. 14, 13, 12, 11. All right. Okay, so that is it. So everything is hooked up. So I'm going to go ahead and turn the power on. All right, so I just turned the power on and we see nothing on the display. Now, currently we have all of these are off. These are 4 bits, A, B, C, D. They're all off so that we will have just a bunch of ones. Remember, all ones blanks the display. So let's try the light test, lamp test button and see if the whole thing turns on. Here we go. All right, so that worked. So we crossed our fingers. All right. Now let's put in let's put all zeros here. So I'm going to turn these all 0. So that's all zeros, and look, we get 0. Let's do a 1. Sure enough, we get a 1. Let's do a 2. Sure enough, we get a 2. There's the 2, right? Matter of fact, yeah, you know what? Let's do this. Let's do this. Let's not look at this sideways and all crazy. Let me bring it in just a little bit. Okay, so there's the 2. I can count in binary vertically. There's 2. Here would be our 3. Here would be our 4, our 5, our 6, our 7, and then here would be our 8. There would be our 8. There would be our 9. And then once I hit 10, of course, we start getting these symbols. So there's 10, there's 11, right? And then take these back like that, the next symbol, and so forth. Put this one here, and then we can get all these other crazy symbols that kind of come in here. There's 5. So anyway, so it totally works. So there, again, if we want to reset it completely, put it 0, and then if we wanted 1, 1, 2, 1, 3, and so forth. There would be 5. All right, so that works. So now, so what cool things could we do here? Well, what we could do, and we'll learn to do, is so now we've got this basically this display. So we could make a couple of these to display a number or whatever, right? We could make a clock, right? And so, but now what we need is something to kind of automate this. So maybe we want to put a counter here. So instead of having a bunch of dip switches, we could do a 4-bit counter, and we're going to learn about counters shortly. Then we could take the output from the 4-bit counter through the display driver, and then it would sit here and count. All right, and then what we could do is we could put a couple counters, and we could make it count every second, right? And then every time it hit 10 seconds, then we could increment the other counter, which would then go to the other display, and then that would basically count seconds. And then every time that hit 60 seconds, we could have another counter and another display, and that could count minutes and hours, and you're seeing where I'm going with this. That's how you make a clock. So one of the first circuits I made when I was a little kid, I don't know, it was about 10 or 12 with TTL chips, is I made a little clock. Once I figured out how to do this, right, display numbers and with a display driver and use a counter and all that, then you can make a clock, all right? And where can we get our clock source? We can use the 555 timer and put it real slow. It won't be very accurate, but that would work. So anyway, so that's it, and so let's get back to the lecture, and we'll go on to the next kind of integrated circuit and see what that is. All right, so I'll meet you back in lecture. Bye. Hello and welcome back. We are on the next lecture, and we're just continuing with the material, talking about different ICs that are in large categories. So we're in the multiplexers section here, which is chapter 6.3.2. So I want you to follow along. Make sure you read the entire section here. Now, previously we just did decoders. All right, and the thing to remember about decoders, let's take a look here. This was the 7-segment decoder. Which we did with the LED and all that. All right, so the whole idea of the decoder is we input some data, either 1-bit, 2-bit, 3-bit, etc. And then what it does is it outputs a pattern. And this is very important. So people get decoders and multiplexers a little bit confused. And so let's try and figure out kind of what the difference is here. So the decoder, we select an output with an input. So here's the input, and it could be 1-bit, 2-bit, 3-bit, 4-bit, could be many bits, but typically it's 2, 3, 4 bits, and it selects an output. Now in the 74138 example, when we select an output with one of these input patterns, there's 3 different bits here, so there's a total of 8 different patterns or 8 different bit patterns. So we can select up to 8 different things, right? 0 through 7. When we select one of those things, in this case, this decoder simply outputs one single bit at a time. So all of these are normally high, and then the bit pattern that you select, the output goes low, all right, because it's inverted logic. So the whole point is only 1 bit changes. So we put in a pattern. This one happens to be 3 bits, and we happen to get out just a single bit output, and there's 8 total outputs here, all right? But now on the display driver, this is a different kind of decoder. Now the interesting thing about the display driver is that and let me see if I can find, yeah, here we go. So we have, in this case, we have 4 inputs, right? A, B, C, D kind of thing. And instead of only outputting a single bit, it outputs 7 bits, and those 7 bits then are the segments of these different digits right here. So the whole point is that even though we input 4 bits, we're not interested in turning on a single bit every time, having 16 different single bit outputs, but instead we're saying when we put in this input pattern, say we put in 7, then I want this output. And what that really means is I want you to turn on these various segments. So a decoder, what it does is it basically is a mapping. It's like you could think of it as a lookup table, a ROM lookup table, read-only memory lookup. For some set of inputs, there will be a set of outputs. The outputs and the inputs don't necessarily have to have any relationship, right? So in other words, there could be say 3 inputs. That would give us 8 different things we could decode, 8 different things. But those 8 different things don't necessarily have to have any fixed number of bits. So they might have 1 bit, as in the 74138, or they might have 7 bits, as in the display driver, or they might have 1,000 bits, right? So each one of those 8 inputs, say if you had 3 bits as an input, each one of those 8 inputs could select 1,000 different things, a pattern of 1,000 different bits, right? So that's what a decoder does. So it decodes an input to an output, all right? Okay. What a multiplexer does, let's get down to the multiplexer here. And again, I'm always sorry when I scroll, I know it bugs some people. All right, so on a multiplexer, this is a different kind of thing. And it's best to look at it here in this picture. So, so here are 2 inputs, and these are called selects. So this is S0 and S1, all right? And then you can see what I've done here is I've got the two signals, and then I've got the inverted version of the signals. And then what I'm doing is I'm taking all possible permutations or combinations of these inputs, 0, 0, 0, 1, 1, 0, and 1, 1, and then I'm gating them into an AND gate, all right, gating them into an AND gate so that it turns on the AND gate. So when all the inputs of the AND gate is 1, you'll get a 1 on the output, right? So when S0 and S1 are 0, 0, these two inverters, these would be 1, 1. So wherever these two signals go, right, so we kind of follow them down here and figure out which one would get turned on. So this one goes in here, this one goes in here, so it's that one. So that means that D0 would be selected. So now this is a 3-input AND gate. So right now, if S0 and S1 are both 0, that means on the right side after these inverters, we'll have a 1 and a 1. So we'll have a 1, a 1. Then whatever D0 is, the AND gate will reflect that. In other words, if D0 is 0, we'll get a 0 out here. If D0 is 1, we'll get a 1 out here. So the AND gate gates this information. So it acts as a switch. So the AND gate acts as a switch, and whatever is digitally on D0 will get pushed through here. Same thing with D1, same thing with D2, same thing with D3 as each one of these are turned on. So we can think of the selects as turning on each one of these gates, or they're kind of like switches. And then whatever the data is, so this could be a stream of data from a serial port or a video port or who knows, 4 different streams of data can be selected and then multiplexed. And then the output goes into this OR gate. So the OR gate basically sums this all up. So only one of these will be on at once. So basically, the OR gate isn't going to allow, it would allow the data from all of these to be superimposed or to be ORed together. But since only one of them will ever be streaming data out or be gated because of these selects, this is how we digitally OR the information together so we can get a final output Z. So this is what a multiplexer does. Now this is a 2 to 4 multiplexer. All right, so you have 2 inputs and then you can select from 4 or 2 selects, and we can select from 4 different inputs. The input goes to the output. All right. Now this is a digital multiplexer. There are also analog multiplexers, and in that case, instead of using AND gates, we use FET transistors so that the information can flow in both directions. And we're going to look at that in a second. So we could think of those really as switches. So instead of AND gates, they would actually be switches, but FET switches or MOSFET switches, so that data could flow in both directions. All right. So now, in that case, and we'll talk about it in a minute. Right now, data always flows from left to right. So it flows from D0, D1, D2, D3 through these AND gates into this OR gate. So it's flowing from left to right. But if we have an analog switch, the data can also flow from right to left. So that's why it's called a multiplexer demultiplexer, you'll hear. So this is a multiplexer, but if it goes in the opposite direction, so in other words, say we had 4 different sinks. So we wanted to sync data at 4 different places from one single source, we would use a multiplexer demultiplexer, but a demultiplexer mode, but it would have to be bidirectional so that the data could come through here. There wouldn't be really an OR gate, there would be a different kind of mechanism, and then data would flow through whichever one of these were selected by the selects. But right now this is just digital, all right? Now if you look at the truth table here, depending on what is selected, you will see the output D0, D1, D2, D3, and if those are static, then you would just see D0, D1, D2, D3, and if they were dynamic signals, then you would see their digital versions, all right? Okay, so if you go through DigiKey or Octopart or whatever you want, there are many, many, many dozens, maybe hundreds of multiplexers and demultiplexers. So the HC151, for example, is an 8-to-1 multiplexer. So in this case right here, this was a 4-to-1, right? So an 8-to-1 just means you have 3 selects and you have 8 different data sources. The HC151 is just an 8-to-1 multiplexer. There's the truth table for it. You can look it up on DigiKey. And but it's digital, so it's a digital multiplexer, all right? And then here, this is just an excerpt from its page. And again, there's all variations of these things. There's HC, there's LV, there's LVC, many, many variations. And so you can see that this is digital, and you can see that its design is almost identical to what my little abstract design. You have the signals coming in here. You've got the inverted and then non-inverted, so it doubly inverts. that gives you back the signal. And then it just picks off each permutation of it, right? And then they go into AND gates, and then all those go into an OR gate, and then in this case it's a NOR gate, then inverted again, so you get both the output and the not of the output. So it's just a more flexible chip. If you're going to make a multiplexer, you might as well make it pretty flexible. And then here's the block diagram. So S0, S1, S2, and then all the inputs, and then the output and the output inverted, which is represented here. And then there's just this little enable. So this enable has to be low to enable these AND gates. So to turn on the final output, it has to be enabled. It's not tri-state though. So this is not a tri-state output. It'll still put a logic 0 or a logic 1, depending if it's enabled or disabled. So tri-state would be different. That would have infinite impedance. So these lines would actually detach because their impedance would become infinite or close to infinite. All right, so that's just one chip. And if you need a multiplexer, so if you want to have a bunch of different digital sources of data and you want to output them to a single source and be able to select it, that's when you need a multiplexer. Okay. All right. So let's see here. And what's this? Yeah, so this is just showing a little organ. So this is generating. So here's a 555, or this is just a crystal. Yeah, crystal, and then using some dividers, some counters here to divide the numbers. And we haven't learned about counters yet, but this is a counter and another counter. So this takes the signal and basically divides, by 2, 4, 8, 16, and 32, 64, 120. It does a bunch of different divisions. And then here are 3 switches, and then these select the signals. So basically we've got, just think of it like this, we've got a clock signal. We take that clock signal and we create that clock signal divided by 2, divided by 4, divided by 8, etc., etc. We all 8 different divisions of that. We put those into the inputs of our 74HC151 IC. Those are the signals, and then we select them with A, B, and C with 3 little switches, and then the output just goes into a speaker so you could hear the different tones. All right, so this would be like a little a note selector, right? A real crude organ. So that's all that is right there. Okay. All right, so this next section is talking about shift registers. So now let's go and let's take a look at some data sheets for these ICs. Then we're going to build something. All right, so let's go here, and I've already done a couple searches. All right, so the first data sheet I want you to take a look at, this is the 74HC4051. Now, what this is a little bit different. There's many, many variations of this IC. There's an LV version, LVC version, many, many, many versions. But I want you to pay attention to this. Analog, multiplexer, demultiplexer. See this analog? That changes everything. So if this is analog, what it does is it allows the IC to signal in both directions, which is really, really cool. So we can use this analog version just like the digital version and just ignore that it's analog. All right. So here, take a look at this block diagram right here. And so we got all this happening here. And then here are all those our inputs, right? So we had all those inputs, A0, A1, up to A7. And then here's the common, this would be the common output. But in this case, these are inputs and outputs, and this is input and output. So it's just, it's basically, N to 1. All right, so it's N to 1. So basically, we can have the signal flow in this direction, or the signal can flow in this direction. So we can use it as a multiplexer, taking one of these N signals and then outputting it to the common node, or as a demultiplexer, taking this common data signal and routing it back to one of these and use them as an output. All right, so that's why these are super cool. So basically anything with a 4051, HC, LV, HCT, LS, etc. There's many, many versions of this, not LS, versions of this that you can use that are this 8-to-1 multiplexer, demultiplexer, analog based. All right. Now we can also go to, let's see, what's this one? Yeah, so this is an LV version of it, which has some other properties, and this one's more modern. 2015, this was updated. Same kind of thing, mixed voltage, and there again is this kind of schematic, and you can see there's a selection logic stays roughly the same. This is what's turning everything on, but then they have these little boxes. These boxes are actually analog switches. So notice they're not gates anymore. They're not gates. So like if we look at, let's just go here and we'll say 74HC151. 74HC151. We'll find a Texas Instrument version of this IC. So this is the digital version that we were just looking at in the book. All right, here's the digital version. Now notice it says data selector multiplexer. It doesn't say demultiplexer, and it says data selector. All right, and notice that it's the design of this is completely digital, all right, completely digital. Whereas the design of this has these boxes, and these are these analog switches that can go in both directions, and that's why they're useful. All right, so what we're going to do is, so let's take a quick look here. I just want to make sure that this makes sense. So let's just go on the blackboard here, or the virtual blackboard as it would be, and so here's kind of what we're going to do. So let's imagine that we have, and I just want to make super certain we have this. So say we have, you know, A0, A1, A2, and A3, all right? And then we have this thing called S0 and S1. Let's put it like this. All right, so the whole idea is that each one of these signals, A0, A1, A2, A3, they could have anything on them, right? Any kind of signal. Of course, we're still talking digital here, right? Talking digital. Any signal on there at all. And now we're just going to black box this. So we've got this right here, this black box. And now we take this S1 and we take this S0. And these are inputs into here. And these are all inputs. Let's make sure we got that. These are inputs. And now on the output here, here's the output. This S0, S1, it has 4 different permutations, right? There it is, okay? And so this would be 0, 1, 2, and 3. And A0, 1, 2, 3 would map to these right here. So these things right here map to these things right here. So then the whole idea would be, if we have 0, 0 on S0, S1, then I select A0. So then A0 comes out on here, all right? Same thing, if I go ahead and I select 1, 1, right, that's going to select the A3. So then we're going to get A3 out here. All right, so that's going to get routed like that. So the whole point is that these 2 selectors right here route that one, this one, or this one to the output. That's a pretty horrible arrow, huh? To the output, okay? And that's how that works. Now, the analog version though, all right, let's erase a little bit here, see if we can erase some of these arrows. All right, so the analog version works a little bit differently. So first, these signals can be anything, all right? And let's see here. So these signals can be anything. So they could be, you know, a sine wave, could be a triangle wave, could be a sawtooth wave. Oops, that's a bad one. Could be a sawtooth wave, and so forth. All right, so they could be anything. And the other thing is that these signals now can be bidirectional. All right. So when we're talking about the analog version, all right, which is the 4051 version, now what happens is all of these are not inputs only, they're inputs or outputs. And this is not an output anymore only, it's also an input. So again, both of these become bidirectional. Again, this still selects things as it would, 0, 0, 0, 1, 1, 0, 1, 1. So if we select, say, 1, 0, that would be a 2, so that's this one here. So what it does is it basically connects this to this. But data can flow in either direction. So data can flow from either direction. So if we put a signal here, we'll see that signal here, all right? If we put a signal here, we'll see the signal here on this A2. That's the point. So it's basically bidirectional. So if you just forget about that and just only put signals on these inputs here, then you'll always see the signal out here. But if you want to use it in both directions as a demultiplexer, and that's where that demultiplexer. So basically it takes the information and sends it this way. That's the demultiplexer, all right? Whereas the multiplexer sends the information this way, all right? But the multiplexer only is with the digital version. You just get multiplexing, but with the analog version, right, you get both multiplexing and demultiplexing, or demux, it's called. Okay? All right, so let's go ahead and let's do this. What we're going to do is we are going to take a look at, let's go back to that 40, let's go back to the 4051. Let's find the HC version of it, this one right here. All right, so I've got one of these on the board, on a solderless breadboard. All right, and let's go take a look at the pinout of it here. Here we go, there's a pinout. And I want to show you this. So, so basically, here's ground, like it always is. So we've got a 16-pin IC. Here's ground. Here's V sub CC. All right, here are our inputs, right? All these A's. And notice how they're called in-outs, 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 right? So A0, A1, A2, and then A3. All right, all these are here. So there's a total of 8 of them, right? A0 through A7. All right, and then here are selects, S0, S1, S2. So that selects which one of these channels gets connected from the input to the output. And remember, data can flow in both directions. We're going to be using the analog, this version right here, which is analog. Then there's this V sub EE. And so what is this about? This is the negative power supply. So this ground is the digital power supply, all right, ground. And this V sub EE, this is the analog, right? So if you look here, this negative power input. All right, so we're just going to hook that to ground, but if you wanted to have it go more negative, you can, because this is an analog system, an analog switch. All right, and then here's this enable, which is digital. So this is active low. So that means to enable this thing and enable these outputs, this has to be active low. So what we're going to do is just going to tie that to low, and we'll put a little switch to disable it, a little button, push button. All right, so all we're going to do something kind of interesting. We're going to prove that this is an analog switch. We're going to take 4 signals. We're going to take ground, we're going to take +5, and then we're going to take 2 different analog signals, maybe a sine wave and a square wave, and 1 kilohertz and 10 kilohertz or something. We'll generate them from the signal generator. We're going to hook those up to 4 of these inputs. We're only going to use 4 of them. The rest we're just going to ignore. And we're only going to care about 2 of these switch selectors. And then with these 2 switches, we'll be able to select signal 0, 1, 2, or 3. As we do that, we'll see ground, +5, analog signal 1, analog signal 2, which if I had enough, I could set this up, but it would be kind of a pain. But we could get 4 different audio sources. So I guess what I could do is, I do have many, many iPads and iPhones and Androids. I could get 4 of them. So this might be something later. Maybe we'll do this. So we'll put a pin in this. We could get 4 different Androids or iPhones, get them playing music, take their audio output, 4 different audio outputs, and then we'll stream it into the multiplexer, and then select which one by the press of a button and be able to switch through all of them. All right, so that might be a fun little thing to do, or for you to do. So if I don't do it, you can do that, but we'll try and remember to do that. But for now, we're going to just look at this at a more lower level on the bench, all right? So let's go ahead on the bench with solderless breadboard, and let's build this idea that we're talking about to look at 4 different signals and be able to select between the 4 of them, okay? So I'll meet you on the bench. All right, so we're going to go on the bench and work on the multiplexer circuit. But before we did that, I thought we should put something up on the screen of kind of what we're going to make, even though I'm going to go over it as we do it on the solderless breadboard. So one thing to keep in mind is we're going to be hooking up this IC right here. And so this is the 4051. And it doesn't matter which version here it is, they've always got the same pinout here. All right, so and this pinout is the standard pinout, but when you come over to the tool, for example, this footprint here puts the pins in kind of a nice format, or the signals in a nice format, and then you can see the pins are all out of order, right? So always remember that what you see in kind of your CAD tool, whether it be this is Proteus or Circuit Maker or Altium or EagleCAD or whatever, the footprints many times have the signals in a nice order, but the pins are going to be all messed up, and it's not going to look like what it's going to look like in real life. So don't let that ever confuse you. All right, so anyway, and then again, see these are called X0 through X7, but if we look back at the IC, they call them A0 through A7. So sometimes you have to do a little bit of mapping and figure out, you kind of read the data sheet, what the signals are, and then kind of figure them out. See, like this E here, this is the enable channels, it's active low, right? So E is active low, and that's the enable. But if we go here, we see that this pin 6 is called inhibit. So it's inhibit is active high. So if you want to inhibit it, you assert a high. If it's low, then it wouldn't be inhibited, so it would be enabled. So you see how they switch the logic there? It's the same thing, pin 6, inhibit, but if you go to the data sheet, pin 6, they call it enable. So be very careful with these signals and make sure you read them always, because depending on who you are, and what data sheet you're looking at and what tool you're looking at, signals will get confused and they'll get inverted, and the meaning of them will be backwards and all that. So very, very careful. All right, so no matter what, I've checked this pin out against the IC here, and this is all correct. So all we want to do is this. We just want to hook this thing up, and we're going to put on 4 of its inputs, A0 through A3, or here it's called X0 through X3. We're going to put ground, 5 volts, and a 1 kilohertz signal and a 10 kilohertz signal. Then we're going to use the input selects A, B, and C. We're only going to need 2 of them, A and B. And we're going to connect those to a dip switch, and as we flip through those, we will select different signals which will come on the output here, or which will be seen on the output. All right, so I've just kind of started here a little bit. This is a course in Proteus, Lab Center Proteus. It's called Crash Course EE Multiplexer HC4051_01, and we're going to finish it off and save it and then go over to the bench here. All right, so let's do this real quick. All right, so here's our switch, and first thing that we're going to do here is we are going to connect our dip switch. We'll just connect 3 of these pins right here. Okay. To A, B, and C. We do not need the last one, so we're just going to let that one kind of dangle. So when we turn the switch on in this example, we're going to actually get a high out of here. So what we're going to do is we're going to put weak lows on here, okay? And typically, most of the time, you're going to see the opposite of this, and that's what we normally do. We put a weak high, and then we assert a low. But usually that's kind of backwards to how you want things. It's a little bit better. You should put a weak high on a signal and then pull it all the way to ground rather than barely pulling it to ground. That's a little tricky if you kind of barely pull things to ground, and you can get into some problems. So that's why typically instead you'll see things pulled high with high pull-ups, and then the switch or whatever that asserts it with a hard low right to ground. But we're going to do it the opposite way because it's makes a little bit more sense. So all we're going to do is we're going to tie each one of these lines here. All right. And remember, you don't need to learn Proteus. You should, because it's a great tool, but it is expensive. And but it's great for simulation. And if you just want to play with it as a simulator and not be able to save, you can use it in that way. But Circuit Maker, which we're going to use for the last part of the course, does not have simulation as of yet. So that's why we're using this when we want to do these simulations. Okay, so that's hooked up. That's great. Now we've got this inhibit situation. So if it's high, it's inhibited. If it's low, it's enabled. All right, so let's bring this little switch over here. And as a matter of fact, I'll do this. I'll kind of push this over here a little bit. All right, and then we will bring this in here. Okay, so here's our low. So we're always going to have that low, and then when we press this switch, we would get a high, and then that would inhibit it if we wanted to use that functionality. All right, and then we're almost done here. So the last thing that we're going to do is we're not even really going to care about this, but I'm going to put it here anyway, just to do it. So on these 4 inputs, we are going to label them. And in the simulation, they're not going to connect to anything, so they're not going to really do much. But nevertheless, just so we can see them. So this one right here, we're going to actually connect that to ground. All right, and this one right here, we're going to connect that to 5 V sub CC. And then this one right here, we're going to connect this to like a 1 kilohertz signal. So we're just going to label it 1 kilohertz, and we're going to label this one 10 kilohertz. All right. So those are, and might as well do that. Okay, so those are signals, and then here is going to be our output right here. So this will be our output. And then what we're going to do is we're going to take the output, and because this is an analog switch, it kind of helps to have a little bit of a load on it, or weird things can happen. So we'll put just 100K right there as a load, and then we'll put a little output label here. All right, like that, and we will just call this output. Okay, and then I'm going to save that. All right, And then you can see we've got our little bypass capacitor here, 0.1 microfarad. And remember, you don't see me connecting it to anything. We just put it there kind of as a separate component. And then when you actually lay the circuit board out, you know to put that near the IC, near the power pin. And also, this has no power pins on it. You can't see them. There are 16 pins, but it doesn't show them on the package because they're hidden pins. So if we click hidden pin here with this particular tool, so V sub DD, that's going to go to V sub 5, V sub CC, and then this V sub EE, this is going to go to ground, and then this V sub SS is going to go to ground as well. All right, okay, and that's about it. All right, we save that again. Now, if I were to run this simulation, because there's no signals here, this may not run. Let's see what happens. It's actually doing it, so that's okay. So, but no matter what, we're not going to be able to really see anything out of here because these other signals don't have anything. But the ground and 5 V sub CC, we might be able to see. So let's go here and let's switch. Let's see, I think these off, off, off. I think red means off. So if that's off, that's going to select. Okay, so blue means off. Blue means off. All right, so hold on here. These dip switches are graphically hard to figure out. Okay, so blue means, yeah, so you can see blue here means ground. All right, so we've got all of these disabled, so they're actually off, which means that we're getting these ground signals here, which are going into A, B, and C, and then that means we're selecting X0. So we're selecting X0 is being selected right now, and X0 has a ground on it, right? And at the output here, that's what we would be seeing. Now, again, because the simulation is not complete, it's kind of acting weird, not doing much. Let's try and assert 1. Yeah, and so you can see we're getting the 1 there, that's correct, but we're not seeing a 5 V sub CC here. So this simulation won't actually simulate unless we actually put real signals here. So for now, we're not going to do that. I just wanted to have a circuit that we're going to build. All right, so this is exactly what we're going to build over on the bench. So let's go over on the bench right now and do it. All right, so here we are on the bench, and so this is going to be kind of cool. So the IC that we have here is the 74HC4051E. And you may or may not be able to see that on the camera, but that's what it is. And just like in the data sheet, I've kind of hooked it up already here, just to speed things up. So let's take a look at what's going on. So the first thing is, let's see here. So the output is at pin 3, and so at pin 3, I've got that going to an output pin here, which we're going to put onto the oscilloscope. And we've got 100K going to ground, just to give a little teeny tiny bit of the load, because these analog switches, if they're completely open on both ends and have infinite impedance, weird things will happen. So we will put a little bit of load on there. Then here's our enable, or our inhibit. So we'll just call it enable low. So on pin 1, 2, 3, 4, 5, pin 6, so this is on pin 6 on the IC. So I've got that going to ground through a 10K pull down. So there's our 10K pull down. And then here this blue switch goes directly to +5 here. So if I press that, that will actually inhibit and then the output would be disabled. All right, but we're not really going to use that functionality. All right, then we've got a ground here. All right, so we've got pin 7 going to ground. That's our ground pin. And then here's that V sub EE, which is the negative power supply, which also is going to ground here because it's an analog device. You can make this more negative than the digital supply, but in this case, we're just making it ground. Then up here, we've got our V sub CC line, which are going to +5. All right, and we're going to, of course, power this from over here from our digital benchtop power supply. And then I've got my bypass capacitor, my 0.1 microfarad capacitor right there. Okay, now the next thing is our 3 selects here. So here are our 3 select pins, and then you can see we've got these all pulled down through 10K resistors. So those are pins, 9, 10, and 11? 9, 10, and 11, is that right? Yeah, 9, 10, and 11. So those are the selection pins A, B, and C. So we've got them pulled down. Then we've got our dip switch over here, all right? And that dip switch is going right. So I've got it kind of sideways in here a little bit. It's going into the plus rail, and then we've connected our 3 wires right here. So this gives us our 3, ones when we want them, all right? And then again, these it's very small. So let me get a little. So I'm going to turn these all off. So off is down. All right, and I just pulled it out. There we go. And these are a little bit tricky. Okay, so they're all off, 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 so we should get 0, 0, 0 in there. All right, so we'll get 0, 0, 0 in there. Okay, so that'll select the first signal. Now, where are our signals? So here are our signals, and then if you look on the data sheet, the signals, the first signals, which would be A0, A1, A2, and A3, is 13, 14, 15, and 12. So 13, 14, 15. So 13, 14, 15, and 12. So this is the 0th input, the 1, the 2, and the 3rd. So A0, A1, A2, and A3 going here. So I've got these as a bus here, kind of floating up in the air here. Now, of course, we would want these nice and flat. We want everything flat if we cared about making this into a functional prototype and put it in a box and put it on the space shuttle. All right. So a little kind of funny little side note here. So I watch a lot of sci-fi movies. I'm sure you do too. And there's one called The Core, and the core is about the core of the Earth is going to stop and stop spinning, and so they have to drill down, and they go in this kind of craft they've made down to the core of the Earth, and they're going to detonate a bunch of nuclear weapons in a certain pattern that's going to get the core to start spinning again. Without the core, there's no magnetic field, and it's the end of the Earth. Anyway, so they're in this $10 billion kind of craft, this kind of drilling machine, and it's like Journey to the Center of the Earth. Anyway, during one of the scenes, they open up a panel, and inside of the panel is a solderless breadboard with this kind of stuff on it. And I'm just like, oh boy. So, you know, they could have at least wire wrapped it, but it was a solderless breadboard. So check out the movie The Core and look for that. All right, so we got our 4 inputs right here, and what we're going to do is we're going to put ground on one of them, we're going to put +5 on another, then we're going to put 1 kilohertz and 10 kilohertz signals on these other. They could be anything, but I just want to have some analog signals. So we're going to use over here, which is off screen, we're going to use the signal generator. All right, and I'll set that up. You've seen it set up many, many times, so we're not doing an experiment with that, so I'm not going to show it to you, but you can just trust me that I'm going to set it up correctly with 1 kilohertz at 5 volts and 10 kilohertz at 5 volts, and I'm actually going to change the waveforms and make 1 square and 1 sine wave. All right, so let's go ahead and let's hook the rest of this up. So we want a ground on this input here. All right, so that's going to be a ground there. All right, and so that one is A0. So when we select 0, 0, 0, we're going to get A0. We better get a ground. All right, and then the next one, I'm going to connect that to the 5-volt rail. Okay, so now we're connected to the 5-volt rail. Okay, and then here is channel 1 of the signal generator. So I'm going to get a ground connected here, and then here's channel 1. So whatever's on that is going to go into that channel, A0, A1, that's A2. And then here's channel 2 of the signal generator, and we have to connect its common ground here. All right, there we go. Okay, so now we've got channel 2. All right, and then now we need our oscilloscope. So I'm going to hook the oscilloscope up, and these cables are horrible, and as you start to play with this stuff, you're going to, you hook everything up, and then you pull your hand away and you grab it with your elbow or your sleeve, and then everything gets pulled off the table. It's just horrible. All right, so there we go. Okay, so we got everything hooked up, and we should be good to go. So now let's take a look at the oscilloscope. All right, so as you can see, we've got the oscilloscope here, and then let's take a look at some of our settings. So here's the vertical position. I've got the scale set at 1 volt per division, so 1, 2, 3, 4, 5. So if we put it right here, and we got 5 volts input, 1, 2, 3, 4, that would go all the way to the top. So let's put it down just a little bit. Okay, so that's that. And then right now I'm sweeping it at 400 microseconds per division, 400 microseconds per division. That'll allow us to see the signal, the 1 kilohertz and the 10 kilohertz, and we'll just adjust this in real time as we need to. Okay, so that is good to go. So let's see here. Back on the overhead camera, let's move these wires a little bit so you can see what's going on here with the dip switch. Okay, so you can see it's 0, 0, 0 right now. So when these are down, it's 0, 0, 0. All right, so let's remember that. So now what I'm going to do is I'm going to turn on both of the outputs of the signal generator, and I'm going to turn on the power. All right, so now everything is turned on. Okay, so that's all good. and now, so what do we have? We've got 0, this is always going to be 0, so let's just forget about that. So 0, 0 should select the first channel, which is ground. All right, so let's look at the oscilloscope. And sure enough, we've got a ground there, all right? So nothing changed, so it's ground. So just stay on the oscilloscope, and I'm going to switch. So now I'm going to go switch here, and well, actually, let's look back. So look back here on the overhead camera. So I'm going to switch this first one up, and that should now select channel 1, which will be this channel, which should have 5 volts on it. All right, so here we go. I'm going to switch it. Oops. Do it again. There we go. Okay, now look at the oscilloscope. So you see now it's at 5. So now I'm going to do it with you not looking at the solderless breadboard so you can see this happen. So now it's selecting A0 and now it's selecting A1. That's exactly what it should do, okay? Now I'm going to select A2 and watch what happens. Look at that. And so take a look down here. There's the 1 kilohertz signal, just as it should be. All right, so now I'll turn that back off and go back to 0, 0, 0. All right, and now I will select the third channel, or A3, which is the 4th input, all right, by putting both of those, and then there we go. Now take a look now. So now what do we have? We've got a sine wave. So we had a square wave on the first analog channel, then we had a sine wave. So now here is the point. So what I want to, bring your attention to, we've got a sine wave, we've got an analog signal. This is an analog device. If this is a digital device, these would be squared up, all right? So it's an analog device, and that's why it's cool. So these could be any kind of signals. It could be audio, they could be video, if there was enough bandwidth in the IC to stream the video signal and its frequency. Now watch, I'll change it to let's change it to let's go to, let's see your channel 2 here. Okay, so right now it's a sine wave, so watch this. I'll change it to a square wave. I'll change it to that, all right, which is a ramp wave. Stop this from shaking. Go back to a sine wave, square wave, all right. So no matter what the signal is, it just passes it exactly. Now, let's speed it up. So let's go back to sine, and let me go to frequency. And it's at 10 kilohertz. Notice it's at 10 kilohertz right here. All right, so we were selecting the last channel at 10 kilohertz. So let's speed this thing up. All right, so now if you look at it, what does it say? It says 100 kilohertz, 100.002, and that's exactly what it says. It says 100 kilohertz on the signal generator, so it's a little bit inaccurate. But look at that, passes 100 kilohertz, no problem. All right, so now let's see, 200 kilohertz, 300 kilohertz, 400, 500 kilohertz. Let's put it to a megahertz. So we're at 1 megahertz, and we've still got this signal passing very, very nice. Let's put it into a square wave. That looks very good. Let's put it into a ramp, looks good. So as you can see, it passed a megahertz. Now, if we look at the data sheet, so basically this is a pair of transistors that allow signal to flow in both directions, all right? So signals can flow in both directions, either from these inputs to this output or from this output to this input. Remember, this is a multiplexer, demultiplexer, works in both directions. But it's got a finite amount of bandwidth, and then also whatever the capacitances and inductances on these inputs and outputs are going to ultimately dictate where we start getting attenuation. But we should be able to go, pretty far. So let's go to 2, 3, 4, 5, 6. Here's 10 megahertz. So there's a 10 megahertz sine wave. Looks beautiful. Look at that. Very nice. All right. So that is well beyond, a baseband video. So you definitely could, send a video signal through here, no problem. Okay, and let's switch it back to a square wave. All right, and then the ramp wave. Now, notice the square wave. Let's back this out here so we can see it. So we're starting to get a little bit of ringing up top here, a little bit of overshoot, right? A little bit of noise. But so far so good for this messy circuit, right here. So anyway, that is the use of a multiplexer. All right, and this is an analog multiplexer, and let's take it off that channel. So we've got a, and let's put it back to 10 megahertz here. We've got this 10 megahertz signal going through here. All right, that channel, and now if we switch channels, so take a look here. I'm going to switch channels. There's our 5-volt channel. It looks good. There's our ground channel. Looks good. And here is our, we got to slow this thing way down. There we go. There's our, give it a second, our 1 kilohertz channel. So everything is still fine. And now instantly I can switch it to the other channel here, which is the 10 megahertz channel, and there it is right there. And just it's having a little trouble locking right now. But anyway, so that's it. And so that's the multiplexer, analog multiplexer. And then last thing before I go, so here, if I can get it to, yeah. So this was a surface mount. This is an LV4051. Now again, once you go to the LV and LVC technology, the ICs typically are not in DIP packages anymore, dual inline packages. They're only in these surface mount. And this is actually a large surface mount. This is a small outline IC, SOIC, and typically I would never use this in an actual design. I'd use even way smaller, all right, package. But this one you can solder and mess with, and then I've of course put it into this DIP package, so we could put it into this board if we wanted to. And this is just an LV version, has some better properties than the HC version in some categories. Okay, so that's it. And so now we're going to move on. I think we're moving on to shift registers. I'm not sure. I'd have to look again. But I'll see you in the next lecture, and we'll figure it out. Bye. All right, welcome back. We are on the next lecture. We're just continuing with the coverage of various ICs that you would use when you design different circuits and whatnot. And these ICs are just kind of major classes of ICs. So if you've been skipping around, we're on shift registers now, and we're going to talk about that. We're going to talk about a couple different kinds of shift registers, and then what we're going to do is we're going to go to the bench and we're going to build something kind of cool, and we're also going to do some simulation. All right, so let's just jump right into this. So I'm sure that you can program in some kind of C or C++ type language, PHP, JavaScript, they're all C-based. Anyway, the line that we have right here is this says the variable x equals y shifted 2 times to the left. All right, so that's a common operation, and that shift 2 times to the left would be the same as multiplying it by 4, right? Because every bit position is scaled by 2, right? So we shift things a lot when we program for division or multiplication, or just to position bits to get them to do what we need them to do. Now, shift registers in hardware design typically are used to take a parallel piece of information. It might be a few bits, 8 bits, 16 bits, whatever, and we want to serialize it. Or go in the opposite direction. We might have a serial stream that maybe is 8 bits or 16 or 32 or who knows, and we want to bring those bits in serially and then grab them in parallel and put them out on a bus. Or we might want to capture a packet that's serial and then put that out on a bus. Or we might want to take a packet that's a parallel packet and then output it serially. So anyway, shifting is very important, and then of course it just has its mathematical operations, multiplication and division, which shifting gets you when you're dealing with binary numbers. So as a matter, let me just prove that to you real quick. So a lot of programmers don't deal with binary that much because you don't have to, especially if you're a web type programmer. You probably never deal with binary. Maybe you'll do some colors, right? FF for something like white, or doing color encoding, but you probably don't do a lot of bit operations. So let's take a look. Say we had an 8-bit number, right? Let's say we had this 00001001, all right? And say this is in binary, so it's in base 2. So this is the ones place, the 2, the 4, the 8, and so forth. So we've got 1, 2, 4, 8. So this is equivalent to 9, all right? So that's equivalent to 9. Now, let's take a look at something that's interesting. If I were to take this and shift it, so let's put a little barrier here in a different color. So let's put a little barrier here, all right? And then we'll imagine that we've got some extra bits here, right? 4 bits, right? And now let's imagine that we're going to take this number and we're going to shift it 1 bit to the left, 1 bit to the left, okay? So 1 bit to left, that's what we're going to do. All right, so that's going to be down here. All right, so let's go ahead and let's do it. And so we're going to get 0, 0, 0, 0, 1, 0, 0, 1. And then what we're going to do here is we're going to shift in a 0 into that position right there, all right? So now, if we take a look at this number right here, what do we have? We've got 0, 1, 0, 0, 1, 0, 0, 0, and then we have the 0 over here. Let's just ignore that. So let's break this into 4-bit little nibbles here. So again, let's figure out what the powers of 2 here are. So let me just erase this little 2 here so it doesn't confuse anyone. That was just the power. All right, and matter of fact, let me make this 0. Let me put it right under here. So it's just a little bit cleaner. All right, so there we go. All right, so now the question is, what is this bottom number here, right? So again, this is the 1's place, the 2, the 4, the 8, the 16. So 1, 2, 4, 8, 16, so it's 2 plus 16, right, which is 18, equals 18. And sure enough, 9 times 2 is equal to 18. So by shifting it to the left, we multiplied by 2. So that's kind of cool. And if you keep shifting every time, it'll be another multiplication by 2. Now let's shift it to the right and see what happens, all right? So again, we'll start off with the top number, which is 9, and we're going to shift that to the right once, all right? So if we shift it to the right, what we can do is we can just think of this bit as just getting thrown away, right? So that bit just gets thrown away. And then we can kind of put a little barrier up here, right? And then we'll put a barrier here, or we'll actually put some dots there. And then right here, we'll say that we're going to shift in a 0. So we'll shift in a 0. All right, so now our new number is 0, 0, 1, 0, 0, 0, 0, 0. All right, so if we were just to look at that and imagine just putting this little barrier up and shifting it, or we could, I guess we could go back and do it the way that we just did also. We could shift this whole thing over. Let's do that. Let's do that. All right, so we're going to shift this whole thing over. All right, and so we're going to get, if we look at this 1 right here, I'm just going to kind of go down here and put a little arrow there. All right, so we'll have a 0 here. So the 0 will move here, right? That'll move there, that'll move there, that'll move there, that'll move there, and so on. All right, so we'll have a 0 there. We'll have a 0 here. And then we'll have a 1 here, and then we'll have a 0, and then we'll have 1, 2, 3, 4, and of course we'll shift in another 0 when we do this. So we'll always add zeros at both ends. So now let's look at our number here. So we had the number 9 before, so now what number do we have? Okay, let's take a look. So this first bit, this is the 1 bit, the 2 bit, the 4 bit, the 8 bit, and again, let's put a little nibble barrier here so we can kind of figure numbers out a little bit easier if you break them into 4 bits. So 1, 2, 4, 8, 1, 2, 4, so it's just 4, all right? And that is exactly 9 divided by 2, right? If it's just an integer, would be 4, right? That would be the integer part, so you know it's 4.5, but we can't represent the 0.5, so it's just 4, all right? So, or the whole part, okay? Okay, so basically shifting to the left is multiplying by 2, shifting to the right is dividing by 2, and that's all there is to it. So that's why shifting is important mathematically to be able to do that. And we can do that in software, but how is that being implemented? It's actually being implemented with, you know, shift registers or, you know, shifting logic inside of the processor. But this is also very useful for the other examples I said about serialization and deserialization. So we need to know how to use shift registers. And these are, you know, very important when you're doing digital design. All right, so let's go to the text. Where is the text? All right. So here's the text here, and so we got shift registers, and this is section 6.33 in my book. Please read all of this carefully. All right, and typically shift registers, no matter how they're designed, are based on what are called flip-flops. We've mentioned these before, flip-flops, and a flip-flop is just a collection of gates that basically can switch state, either clocked or unclocked. We'll be talking about clocked flip-flops. And there's a number of different flip-flops. There's the SR or set reset flip-flop. There's the T, which is the toggle. And then there's the two that we're kind of interested in, which are clocked, and they're called the D flip-flop and the JK flip-flop. All right. And so I'll show you the JK in just a moment. But the D flip-flop basically is a clocked flip-flop, and you could think of it as a one-bit memory. And it's just a bunch of cross-coupled gates. And as you apply a signal to these and then apply a clock signal, it will remember through feedback, right? So the circuit is a feedback circuit, so it stays in either a 1 state or a 0 state, depending on how you program it. So it's a one-bit memory. It's a very big one-bit memory now. So like say dynamic RAM. Dynamic RAMs use little capacitors to store charge. That charge is a 1 or a 0, very tiny. So you can have hugely dense memories with dynamic RAMs because they're based on capacitors. Static RAMs are based on, unfortunately, flip-flops or types of flip-flops, and they're very big. So static RAMs are going to be much more expensive and much less dense. So you have smaller static RAMs, okay? But static RAMs are simpler because you don't need to refresh them because they're static. And the refresh operation is fairly complex, especially with modern, DDR3, DDR4, DDR5, DDR6, all that, very complicated. Anyway, so each flip-flop is a 1-bit memory. And so here's kind of an abstract of a flip-flop. So it's got an input which is called D, and you can put a 1 or a 0 on here. All right, and then it has two outputs, Q and not Q. Q is follows D, and then not Q is the opposite of Q. So Q follows D, and so what that means is, say if you put a 1 on D, and then you pulse the clock, what will happen is that 1 will then get transferred to Q, and then Q will now be a 1, not Q will be a 0. If you put a 0 on D, and then you pulse the clock, that 0 will get transferred to Q, which will be 0, and the not Q will be 1. This timing diagram shows those examples. And the transfer of the data from D to Q only happens on the clock. And depending on the flip-flop architecture, it could happen on the rising edge, it can happen on the falling edge, all right? So most flip-flops operate on the rising edge. So on the rising edge of the clock, that's when the transition will happen. All right, so if you kind of look through here, you can see we've just got kind of D coming in at a random time, right? And then we have the clock, and then you can see each one of these vertical dotted lines, they coincide with the rising edge of the clock, and that's where the actual sampling of D is going to happen, and then Q is going to follow it after that, all right? Then also on these flip-flops, and of course there's going to be some propagation delay, so if you have a 1 on D, and then you pulse the clock, this doesn't happen instantaneously, right? So on the rising edge, this transfer occurs, then there is a propagation delay until Q follows that D input, right? Okay, which is not really shown here. Let's see. Clear, yeah, so a lot of these flip-flops, they'll have a clear, and all clear does is exactly that. It just clears out the flip-flop, and that's it. And it's asynchronous, so no matter what's going on with the clock or D, if you assert clear, it just clears out the flip-flop, and that way you don't have to clock or wait for a clock to clear it, okay? So that's a flip-flop. All right, so going back to our example here, let's say that we wanted to implement a shift register, right? Say a 4-bit shift register. All right, so a 4-bit shift register. All right, so say if we wanted to implement something like that, so what would we do? Well, we would go get 4 D-type flip-flops, and I'm only going to put D and Q on each one, and clock, which I'm just going to call CK. So I can, you know what? Let me make this a little bit bigger. Let's not get cheap. All right, there's 1, there's 2, there's 3, and there's 4. All right, so what do we have? We've got, and let's be colorful. All right, so we got D, we got Q, we've got Q naught or Q bar, or not Q, Q, not Q, D, Q, not Q, D, Q, not Q. All right, and then we have our clock signal. So we'll put our clock here, clock here, clock here, clock here. All right, and then we'll have a clear, and with a bar over it, that means it's active low or asserted when it's low, clear. clear. Now let's go ahead and let's tie all those clears together. Tie all those clears together. So again, we don't know exactly what's in a flip-flop right now, right? I'll show you in a little bit, but let's assume we're going to figure that out. So clear is asserted low, so let's say that we put a little momentary switch here, right there, to ground. Now we don't want this thing to get asserted when there's no signal on it, so we need to pull this up, right? So what we're going to do here is we will, and we could do this anywhere, but we'll just put a little resistor here, and we'll pull this up to +5 or V sub CC, whatever it is, and we'll just make this a 10K ohm, okay? So that'll keep this so that it's not cleared unless we hit this little button here, which we're just going to call reset. Now watch how cool this is. So now, and we'll just use little red lines for this. So now, if we want to basically shift data from bit to bit, all right. So, and we can call this whatever we want to call this. So we'll call this bit 0. We'll call this bit 1. We'll call this bit 2. We'll call this bit 3. So all we do is we literally connect Q to D, Q to D, Q to D, like that. And then here's our output right here. And then here's this output right here. And then here's this output right here. And then here's this output right here. Those are each one of our bit outputs, right? And now what's another thing we got to do here? We got to tie these clocks together. So be careful. The clocks all have to be tied together. All right, so there's the clock. And then we're just going to tie these clocks together carefully. All right, and we're going to tie these clocks. Put a little dot there to make sure we know that that's connected. All righty. And here's our clock in. All right. Okay, and then our final input right here. So this input, right, this is serial in. So that's serial in. What's this? Well, that's serial out. Serial out. So here's the thing. So let's say that these things all start off when we push the reset button. So now what are we going to have here? We're going to have 0, 0, 0, 0, right? 0, 0, 0, 0, 0, 0, 0, 0. So that's what we would have. Now, let's say that on serial in, we put a 1 there, and then we went clock, 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 3 clocks. We pulse 3 clocks. So then what would happen is we would push 1s into these 3 positions. So as these bits, so now remember what happens is each bit goes over to the next flip-flop, and then this one goes out, right? So each one does that. So if we put a 1 on the input there and then did 3 clocks, clock, 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 we would have this. Then if we did 1 more clock, then what would happen? This one would go here, this one would go here, this one would go here, and then whatever was on the serial in would go to the input. If it was another 1, then we would have 4 1s here, right? Okay. So that is all a shift register is, okay? That's it. And then another cool thing is what we can do is we can take the output here, right? We could take the output here, and we could, if we want, bring it all the way around and bring it back into here. So we could do something like that. We could recirculate the output back to the input. Now we have to be careful that we don't have a bus contingency on this serial in, so we would have to disconnect serial in. So but this is how we would recirculate the data if we just wanted to shift through here. So that's what a shift register is, okay? So that's it in a nutshell with a D-type flip-flop, all right? Now, let's go ahead and take a quick look on Wikipedia here. If you type in a flip-flop and you search for flip-flop on Wikipedia, this has got a really good graphical depiction of how these things work. So, I wouldn't mind you reading this. It's not too long. It's about, I don't know, 5 or 10 pages. I wouldn't mind you reading it. And but what I like about it is, this is interesting, some of the first schematics from the patent filed in 1918. So just how crazy does that make you feel? This was 100 years ago. 100 years ago, right? They were doing electronics and flip-flops back then. Isn't that amazing, right? 100 years ago. So anyway, we're still doing the same kind of things these days. All right, so what's nice about this is it actually shows you how this data is flowing here graphically and these little animated GIFs. And then, so all flip-flops start off with a couple of cross-coupled NAND gates or NOR gates. And so here you see these are NOR gates, and you just cross-couple them. And then what happens is, depending on what you do with R and S, which is reset and set, and this is called an SR latch, all right, the output Q and Q, not Q will stabilize, all right, and so you can set it and reset it, and because of this feedback, it locks into a value, so it can be set and reset. So it's basically a memory, all right, and then this is showing what's going on here, and then they can get more complicated, all right, and let's come down to here. And then this is a gated latch, so then there's another AND gate so that the R and S is not asserted unless this enable is here, right? And then so you're building up the complexity to make this gate more useful, right? And then we have this gated D latch, all right? And then you keep, and then again it shows you how this thing works, all right? And then moving down, moving down, moving down, and then finally we have this flip-flop, and then here is the flip-flop, all right? And in this case, this one has a set and a reset, and then this is the clock input, right? That's just kind of the symbol for the clock. And then it shows you here, clock on the rising edge. If you've got a 0, then Q next, and that's what it's called. Q next will be 0. If you've got a 1 on D, then Q next will be 1, all right? And then moving on, there's another kind, and then there's what we just did right there, right? That little schematic right there is exactly what we just did right here, right? Did something just like that. All right, and then getting more complex. A T-type flip-flop is a special case. It's a toggle flip-flop. This is the other flip-flop that's really useful. It's called the JK flip-flop. And the JK is really cool because it can act like a D flip-flop, it can act like a toggle flip-flop. So it's got two inputs, J and K, and you don't need to use them both. You can hold J as 1 or 0, you can hold K as 1 or 0, you can tie J and K together, you can do all kinds of different things. But what's interesting here is I want you to take a look here at the what's called the characteristic and excitation table. And so if we have J and K here, and then this is, you know, when this is, assume there's a clock that happens, right? The clock is not shown. So if J and K are both 0, this is called the hold state. So no matter what the value of the Q was, it's just itself again. So that holds it. So when you put a 0 and 0 on J and K, it holds the state. Now, if you've got J as 0 and you've got K as 1, that's the reset state. So no matter what the current Q was, it resets to 0. Then the set state, if J is 1 and K is 0, that's called the set state. No matter what the current Q was, Q next is 1. And then here's the interesting state, is the 1, 1 state. And if J and K are both 1, that's the toggle state, all right? And that means whatever Q was, Q next is Q bar, or the opposite of it. So it's useful in counting. So when you make counting circuits, you want to toggle, all right? Or if you just want to blink back and forth, right? Just on, off, right? So anyway, so take a look at this, read through this. You could do worse things. And then this is very important right here, metastability, which just talks about how the flip-flop can get into a position where it's not stable. It's to make an analogy is this little image right here is kind of used. So imagine you have a hill, you got a little ball on the hill, and it's just perfectly balanced right there at the tip, at the tippy top of the hill. It's going to go this way, it's going to go this way, we're not quite sure. This is metastability, and electronics can have this if you're not careful. So anyway, that's what that term talks about. All right, so now let's dig into some of the actual ICs. All right, so the first one that I want to talk about is, so now in this case right here, this is what we just drew, right? We just drew this thing. All right, and here you see serial in and parallel out, and also serial out. So serial in, parallel out, right? Serial in, parallel out. All right, and that's exactly what this looks like. So we have a serial in, and it just gets shifted, 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 shifted. We can take the data out, and we can also get the serial out. The clears are all connected in parallel, and so are the clocks. All right, so serial in, parallel out. That's one form of a shift register, and they can have different bits. 4-bit, I mean, they could have 2-bit, 2-bit, 4-bit, 8-bit, 16-bit. You're not going to see them more than usually like 16, maybe 32-bit if you look around. All right, now. This 74HC166 is a parallel in, serial out, a shift register, right? So this one is the opposite. So if you take a look here, this is parallel in and serial out, right? So here's the parallel inputs. All right, so and this one also does serial in. You could also serialize the data in. But what's nice about this is you can load a whole byte value into it, or a nibble value, whatever you want, and then you could shift it all out, so you could serialize it. So that's what this 74HC166. And again, these ICs I'm showing you, these are very old, right? But they're classic, and they're the root of many ICs that are relative to it. So if you start looking around the 74HC166 and you look for parallel in, serial out, you'll find many, many variations and many, many different kinds of logic families. But this is kind of the root. All right, so that's what this guy is. All right, and let's see here. And then so this is the whole idea of parallel in, serial out. All right, that's that 166. And on this particular IC, let's go to a data sheet here. And this one, so this one is parallel out, and we don't want that one. We want parallel in. So here's that 166 that we're just looking at. All right, so if you can see right here, so pin 1 is called serial. So this is this serial line, right? And then we've got clock inhibit, we've got clock, we've got ground, we've got clear, and then we've got shift and load, and then we have A, B, C, D, E, F, G, H, and then we have this QH here, right? So now if we go back to, we go back here, all right, we go back here, then we take a look at, so this is kind of this older school version of it, right? And some of these signals are a little bit clearer to understand. So CP is the clock pulse signal, so that's the clock. And then CE is the chip enable. And then MR is the master reset. And then Q7 is the serial out. And then PE is the parallel load enable, right? So this particular IC, the 74HC166, when compared to this version right here, right, from this is a different manufacturer. That's all. They just call these things differently, all right? Now, here's where we can kind of figure out what's going on, right? So you look at that and you're like, oh boy, I have no idea what's going on here. So let's take a look at this logic diagram and figure it out. All right, so first, let's start off. So here's this serial line here. So this is a serial in line. So this is where you can bring serial in to the system. So if you don't want to use the parallel loading functionality of it, then you don't need to. You can just put serial data here and start shifting it in. All right, so it would come into the first stage, then see how the first stage goes into the second stage, and see how the second stage goes into this stage and this stage. See that? So that's its shifting down. Now notice we can't access the output. So this is not parallel out, but it is parallel in. See A, B, C, D, E, F, G, H. Those are the parallel inputs, but notice each one of these outputs here, right, we can't get to. So the outputs of it we can't get to. They're right here, by the way, and they're not labeled. So that's the output, and that's the output, and this is the output, and so on. They're not labeled, but these are Q outputs, but we can't get to them. All right, now let's move on. So here's this QH, all right. And so what QH is this is the output of the very last stage. So here's serial in. So this would be better to call it serial in, and this would be better to call it serial out. Now, take a look here. What's this little triangle? That's a buffer. And what's that buffer for? It's just to buffer the output stage and give it some current, right? Give it some current drive so it's buffered and you don't load it too bad, all right? Okay, what else do we have? We've got our clear line, and notice they're all connected in parallel to this R, which is this reset of this abstract flip-flop. So clear is active low or asserted low, okay? And then now look what we have here. We have this clock, and then we have this clock inhibit. So what's going on here? All right, so notice here we have this OR gate. And so we have this OR gate right here. So if clock inhibit is ever high, this OR gate will just be high. Right, and then these clocks, these flip-flops only clock on a rising edge. So if you turn clock inhibit on and you assert it high, the clock just goes high. So no matter what you do with the second clock line, because it's an OR, you can never get the clock to go back low again. It'll just sit high. So clock inhibit basically inhibits clocking. All right, so it's just an extra line, so you don't have to add a flip-flop, or you don't have to add an OR gate or an AND gate. And a lot of times it's all about functionality. If you don't want to use it, don't use it. Tie it low and ignore it, all right? And then pin 7 here is the clock, all right? Now, what's this little funny guy? So this is shift and load, all right? So this is shift and load. So in this case, if you assert it high, it'll just shift serially. It'll take what's ever here on the serial line and shift it. If you assert it low, all right, and then do the clock, it will load the data on A, B, C, D, E, F, G into each one of the flip-flops. All right, so shift and load controls how the shift register works. So if shift is high, it'll just shift every time it gets a clock. If this line is low, it will try and load whatever's on A, B, C, D, E, F, G, H. All right, and that's it. That's all there is to it. So, and again, you can just look right here. We know how to do this. We know how all this stuff works, and that's it. All right. So now let's go ahead and let's take a look at. Let's go back to the text here, and see parallel in, serial out. Yep. And the next, okay, serial in, parallel out. So we're going to not mess with that right now, and we're going to go here. All right. So what I've done is the 166 that we were just looking at, which is this IC right here. All right, which is the HC166. So I've created a little simulation in Proteus again, Lab Center Proteus. You can get Proteus and download it for free, free eval version that'll run the simulator. You just can't save and build circuit boards with it. All right, but anyway, so let's see what we got here. So we've got our 166 IC. And then notice in this tool, again, we've got a different labeling going on here. So they call it D0 through D7. Then they call it serial in, which I like, SI. And then they call it serial out for that QH line. That's the output. All right. And then the clock, we've got our clock here. We've got our inhibit. We've got our shift and load. And we've got our master reset, which is active low. All right. So let's go through and see what I'm doing here. So the first thing is, let's deal with all the easy stuff. So there's that inhibit on pin 6. So I've just tied that low. I'm not using it. I don't need to inhibit it, so I'm just tying it low. Great. Now, here's my clock line. And what I'm going to do is I'm hooking this up in the simulation to a switch, a momentary switch. So I'm going to actually pulse the clock. Now, remember, in the real world, if you ever did this, you would get a lot of noise. You'd get a lot of debouncing, because the second you hit that button, it bounces a bunch of times, right? So we can mitigate this a little bit by putting a capacitor here and trying to smooth it. This would be a hardware debounce or deglitch, and a little small capacitor will help with this. So that's one approach to do. And then because it's a simulation, it actually will work pretty good. And then the other thing is I'm pulling it low, and then so when I hit the switch, it goes high. So this gives me a rising edge when I hit that switch, all right? That and pulse it. So we'll be able to pulse it manually. Now, what else do we have over here? Here is this shift and load. So I've got this shift and load to a momentary switch again, but you can hold these down if you want. If you press this little icon here, you can hold it down. So this lets me put it in which mode I want. Do I want to use serial shifting, or do I want to do a parallel load of data? Okay, so when the switch is down, I get a ground, I get a 0, and that gives me the load mode. So now if I were to pulse the clock, whatever's on the input data bus is going to get loaded into the shift register. What's it going to get loaded into? Just going to get loaded into these flip-flops. Okay? All right. Where did we just go? Okay. Now, let's see what else we have here. All right, we've got master reset. I'm not using it in this right here, so I've just got that tied up high through a pull-up resistor. And you can just tie these high directly to V sub CC if you like. You don't necessarily have to use a pull-up resistor. Let me tell you why I use a pull-up resistor. These inputs, if they're CMOS inputs, if this is a CMOS chip, there's very little current. There's almost no current, right? They're voltage devices, but there is some leakage current. And because of that, if you put a little resistor, it minimizes that leakage current. Now, if it's an LS device, there is a current, right? And I don't want to give it the maximum amount of current it can draw. I just want enough current to pull the thing high or pull the thing low. So that's why you want to put a resistor here, a 1 to 10K, to minimize that current. You don't need to burn all that current if you don't want to. But in CMOS, you can definitely just tie these directly high if you like, if you want to do a pull up or a pull down, high or low. Definitely, if it's if you're pulling it low, just always connect it directly to ground. And Texas Instrument has a lot of white papers on this and kind of gives arguments for it and shows you why you kind of think like that. All right, what else do we have? So the other thing is, on the IC here, you don't see the power. All right, if I double click it and I should say hidden pins, and again, you don't need to know how this tool works, but you're probably learning it along the way. It doesn't hurt. And you can see I've got it to ground and 5 V sub CC, and that doesn't show the pins in this tool for power and ground. They're hidden in this footprint. That's all. You could make a footprint that shows them. All right, here's my capacitor here, my little bypass capacitor, always showing that next to the IC. And then over here, I just have an inverter IC. I have one of 6. So this is a 74 HC04. It's a 6 inverter package, right? And I'm just showing one of them. And then here's the capacitor that would go with that IC. And this is just for some other fun stuff, right? Then I take the output and I feed it right back to the input, okay? And then I take that also through a 220 and an LED so we can see what is being shifted out of here serially, because we can't see it in parallel. All right, so we're almost done. Now, what do we have? We have this dip switch here, and this dip switch allows us to put a bit pattern, an 8-bit bit pattern, on the input that we're going to load. Now, this might come from a bus, from a microcontroller, or whatever. Who knows where it came from? It might come from a radio. It might come from a Bluetooth packet. Have no idea. All I know is there's 8 bits. I want to load them in here, and we're going to do it with a switch. All right. And remember, we've kind of wrestled with this. Wherever the black part is, that is where the switch is. So this is on, and then it's off, 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 off. All right. So in this case, now also notice on all these inputs I've got pull down resistors, not pull up, but pull down. So all of them are weakly pulled down to ground, so I'll get zeros on there initially. And then when I assert any of these dip switches, then I'll get ones on there. It's a little easier to think about because off and on means on and off and all that. So now on means on means 1, okay? Okay, so I think that's about it. All right, so let's just run the simulation. There's the run simulation. And blue means 0 and red means 1. All right, so you can kind of visualize and see what's going on there. And let's do some stuff here. Okay, so we haven't there's no clocking, so there's nothing shifting right now. All right, so the first thing I want to do is let's load a value into the shift register. All right, so right here I've got the value 11110000. 1111. Let's do that again. 11110000. So 4 ones and then 4 zeros. Okay. So now what I'm going to do is I'm going to load this in parallel. So how do we do that? Okay, well, we need to have the shift load correctly asserted. So to load in parallel, it's active low. All right, so if I go over here, I'm going to put this low. So I do, and you can see the little blue dot means there's a low on that. So that's good. Now I'm going to pulse the clock signal. As I pulse the clock, the data on that data bus is going to get loaded into all of the flip-flops. Here we go. And that's it. It's been loaded in. Now we can't see anything because all we can see is the very last bit. The very last bit is a 0. We've got 11110000, right? But now what we're going to do is instead of doing a shift load and doing a load, we're going to put this into shift mode. So we're just going to undo this flip-flop, this switch here. Okay, so now we're in shift mode. Now, when I start clocking, we're going to see these bits come out here. So we're going to see, now be careful, look at the order they're in. So here's this D7. So this will be the first one that goes out, right? So right now there's 0, 0, 0, 0, 1, 1, 1, 1. Now remember, they've already been loaded in here. So it doesn't matter what I do to this now. So for example, I could turn this all to zeros. It's being ignored at this point. This is all ignored, all right? So I could turn this to all, that's all zeros right there. So wherever the black is, so they're all off, okay? So now we've already loaded 11110000 into the shift register. So now let's shift it out. So what we should see is, we should see 00001111 because it's going to shift out, the last bit first. All right, so here we go. All right, so ready? Keep your eye on this. So 0, 0, 0, 0. Oh, here's the 1. So this is the first one. There was already 0 there. So there's the first one. 1, 1, 1, and then 0. And that's it. So it shifted it all out. And so that's it. That's all it does. Okay, so that is the parallel to serial, and it recirculates also. So now, because we have the output going back to the input, right? If we have the output going back to the input, now that data keeps circulating. So as I keep clocking it, there it is. There it's going through the shift register, and then there, and then here it comes again. See, for 4 clocks, it'll be there. All right, because we've got this recirculation. We've got the output going to the input. So once we load it in there, it'll just sit and recirculate it. So for example, say it was a bunch of LEDs that you wanted lit up in a certain pattern, or you just wanted to, it could be just a pattern. And maybe that pattern is a pattern of ones and zeros. For example, there's something called a pulse density modulation, right? Where say if you had 100 bits and you wanted to have a signal that had a 50% power level, every other bit would be 1 and 0, 1 and 0, right? Now, if you wanted to have 25%, every 4th bit would be a 1, right? So it's like the density of those ones dictates the overall energy level of the signal, right? So we could basically do something like that, right? So there's all kinds of things. There's countless things you can do with shift registers, but by taking the output and feeding it back in, you can obviously recirculate it forever. Now, what's this inverter here for? So what the inverter is for is if you take the output and put it through the inverter, and we can do that. So if we take this output and then we put it through the inverter here, let me just move this over a little bit, and I'll just connect it. So here's the inverter, bring it in here, there we go. Okay, all right, so now the interesting thing is, no matter what is in the memory here, right, no matter what's in the memory, if it's zeros, they're going to get turned to 1, and then those ones are going to get turned to 0. So this thing is going to basically go 1, 1, 1, 1, 1, 1, 0, 0, 0, 0, 0, 1, 1, 1. So it's going to oscillate kind of, right? So let's give it a try. So it's in shift. We're not going to load anything into it. So we're just going to start the simulation, and we're going to start clocking it. And then watch this LED. Okay, clock, 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 and we did 8. Now all those 8 bits got inverted and got sent back in to the other side of the shift register. So they came out here, got inverted, and got put right back in. So now I got a bunch of ones in here, right? Got a bunch of ones. So now watch this. 1, 1, 1, 1, 1, 1, 1, 1, and then back to 0. 0, 0, 0, 0, 0, 0, 0, 0, and then back to 1, 1, 1, 1, 1. There you go. Right? So how cool is that? Right, and that could be a useful behavior that you might want. Okay, so let's undo that and just put it back to the way it was. Okay, so that's it. So the file name of this is, of course, Crash Course EE Serial 16601, and it'll be inside the materials for this lecture. And so that's about it. So we're going to come back in the next lecture. Where are we here? We're going to come back in the next, and we'll talk about serial in parallel out registers. Which is kind of the opposite of this, and we can have some fun with this actually and do something kind of cool with it, all right? So I will see you in the next lecture, and we're going to talk about this. Bye. All right, welcome back, and we're on the next lecture. And let's see here, what are we doing? We are continuing our discussion of shift registers. So we already talked about the parallel in and serial out. So now we're going to talk about serial in, parallel out shift registers. So they're just, kind of complements of each other. So again, read the material here, 6332 inside of the book. And it talks about the X Game Station a little bit. It's just obviously, if you've been reading the book, you know it's an embedded system that the book refers to just as a model of things. Anyway, so let's jump right in here. So the chip we're going to look at is the 74 HC164. And of course, there's different family versions of this and so forth, but the 164 is a good representation of this kind of serial in, parallel out shift register. So the case that you would want this kind of shift register is where you're basically taking a serial stream and deserializing it. So something has been sent serially. Say it could be, for example, let's say that we did RS-232 communications, right? So what we might have, so let's take a look. This is a kind of a good example here. So here's our stuff we had last time. So let's just get that off the screen. So let's say that we have one computer over here, all right, or embedded system, right? So we'll call this PC1 or embedded system 1, right? And then over here, let's say that we have PC2, all right? And then we want to communicate between these two, all right? So one way to do that is serially, with a serial connection, a simple serial connection. And now we have, USB serial. So we've got USB, and then in the USB kind of various things that can be supported is, of course, a serial stream. But even simpler than that is what's called an RS-232 serial, RS-232A serial. And it's composed of a TX line, an RX line, then over here, this becomes RX, and then this becomes TX. So this is transmitting out, this is receiving in, this is transmitting out, and this is receiving in. And then they both have a common ground. And that's all you need. So 3 lines and you can communicate between 2 different systems. So you can do it pretty fast also. Now, these days you won't find a lot of our serial ports or RS-232 ports on modern PCs. In fact, you won't find them at all. But if you want to add one, you can. Or if you have an industrial PC, that's say an embedded system kind of PC, it will definitely have an RS-232 port or more. And you can always get a card. And then when we're developing microcontrollers, many times we'll use a serial communication scheme. But the point is that this is exactly a case where this serialization and deserialization and shift registers come into play. All right, so inside of this PC or embedded system, right, we have some bytes of data, right? So let's just kind of bring this down here, and let's bring this down here a little bit. The world's horriblest arrows. There we go. All right, and so let's say that we want to send a byte. So we have this byte here. 1, 2, 3, 4, 5, 6, 7, 8. All right, so here's B0, here's B7. So here's our byte, and what we want to do is we want to send that serially. So what we would do is we would have some kind of shift register. So we would have this byte right here would literally be connected in the hardware somehow to a shift register. All right, so this would be shift. And this would have the serial outline right here. So now these bits that are in here, 0, 1, 1, 1, 0, 0, 0, 1, they get shifted out here serially. So the first bit we would see is the 0 bit, then we would see the 1, then we'd see the 1, then the other one, then the 0, 0, 1, and these would go along their way on this line. All right, so then we have this, this line here, which then goes to this receiver. So this would be kind of like the TX, and then over here we would have the RX, one example. So now, so this is basically serialization, all right? So that's where we're serializing the data. So we're going from parallel, obviously this is parallel data right here, to serial data out. So now on this end, we have kind of the opposite. We have a shift register. Again, that shifts the data in, but then what we want is we want to output the data in parallel. All right, back so the computer or embedded system can then work with it. 1, 2, 3, 4, 5, 6, 7, 8, and put our little boxes here. All right. 1, 2, 3, 4, 5, 6, 7, 8. All right, so in this case, now as this data flows through here, so it's been serialized and now it gets deserialized, and then as these ones and zeros make it to the shift register input, so that's serial out, so this is serial in, then they get placed into the proper position. So we just copy them over here. All right, and then this is again, this is a parallel. This is a parallel read over here, and we would be, reading it back into the computer. So over here we have this, deserialization, right? So that's why we have these, shift registers. So the shift register, the 166, the HC 166, right? That is the one for going from parallel to serial, right? And then this 164 here that we're looking at, we might use this HC 164, then can go from serial to parallel, right? Can go from serial to parallel. And that's one case that we could use it in, all right? So let's take a look at this data sheet here. So this one was revised in 2003. We'll look on DigiKey for kind of a later version of it. So the IC, again, has these Q outputs, so Q0 through Q7. Then it's got these DS1, DS2, ground, power. This is probably clock pulse, this pin 8 here, CP. And then this is master reset. So let's now, you can kind of read through here. So DS1 and DS2, these are the serial inputs. CP is the clock pulse, MR is the master reset, and here are the data outputs, okay? So now what I'd like to do is let's actually go to the data sheet here. So here is the kind of modern data sheet, and this one was updated in 2015. This is from DigiKey. And then this shows you the diagram so that it's a little more clear what's going on here. So let's go through this and figure it out. So now remember, we're going serial to parallel this time. In the previous one, everything's always here in parallel, but you can't access it. Here you can access it. So notice is the first, we've got this clear hook connected to all these reset lines, all right? So there's our clear, it's an active low, there's a bar over it. Then we have our clock. Notice we have our clock buffered. That's what that triangle means, because it's going to drive 8 different devices here. So we buffer it for 2 reasons. 1, to drive the 8 devices internally, and 2, to not put a lot of load on it. So we don't want to draw a lot of current from this, all right? And that's what that buffer is for internally. They're showing you that, all right? And then you see this little triangle on these inputs. That triangle usually, that means it's an edge triggered. And we know that this is rising edge triggered unless otherwise stated. Okay, and let's see here. And then here's all the D's in the output. So a little bit tricky. The output is not labeled here, right? It just says 1D, 1D, and then, that would be 1Q, right? That is the output. So here's the input, there's the output, goes the input, goes the output, and so on and so forth. Just chains right along the way. And then each one of the outputs, QA, QB, QC, are taken from each one of the flip-flops. And then notice one thing here. There's a circle here and a circle here, 2 inversions. Again, there's a circle here and a circle here. And those are just showing that the gates are implemented with inverting logic. So there's 2 inversions, which then just neutralizes it, and you just get out the same signal. That's all that is, all right? So here's the parallel outputs. Here are our 2 serial inputs. Forget the 2 inversions there. So the bottom line is A and B both have to be high if you want to shift in a 1. So again, these AND gates on the inputs to serial devices are used to gate the input. So if you bring one of those low, then basically no 1s will ever come out of the AND gate, right? Because you need both inputs to be 1. So that's how you can control if 1s flow or not. So it's called gating, right? And use an AND gate to do this. So when you want data to flow, pull B or A high, or you can tie both A and B to the same signal. Then when it's 0, you get 0 out. When it's 1, you get a 1 out, right? Either way. Okay, so very simple. When you look at this, then it becomes very clear what's going on here, right? We just have these 2 inputs. We got clock, we got clear, and we got our 8 outputs. That's all there is to it. That's all there is to it. Now, since we got this data sheet open, let's go take a look at some of the electrical specifications of it. All right, here's the pin out here. A little cleaner naming here. So this is called A and B. That makes a little bit more sense to me. And then QA through QH, and then clear, and then clock, and then ground. And then if you look at this version of the data sheet up here, and this is also by Texas Instruments, right? It's just a little bit more cryptic. So you got DS1, DS2, you got Q0 through Q7. I like that actually. I like numbers better than letters. And then MR, master reset. These days it's kind of called clear. They kind of updated that a little bit. And then CP, clock is a better word to use. So this is nice. Okay. Anyway, again, it just tells you what all the inputs and outputs are. Another package right here. What's that? This is this LCCC package here. All right, so this is leaded chip carrier. I can't remember, but anyway, another package just showing. All right, here's where I wanted to get to. Let's see here, electrical characteristics, V out high, V out low. We already know what those things are, don't care. In this, I want to get to, here we go. So here's the timing requirements at 25 degrees Celsius, all right, which is, 70 something. You can do a conversion real quick and figure that out, Fahrenheit. So the clock frequency is what I wanted you to take a look at. So on this IC, depending on what voltage you run this at, 2 or 4.5 or 6 volts, here are the maximum clock frequencies that you can clock this thing at: 6, 31, or 36 megahertz. So it's not too fast. It's not a fast chip. This version of it, right? This version, which is this HC version, right? If we come up here, we're dealing with an HC version. These are not the fastest things in the world. So keep that in mind. So if you're interfacing to, say, 100 megahertz or a 200 megahertz microcontroller, and you want to do some manual shifting, right? You want to serialize or deserialize something, be aware that you're going to have to use a different family of faster shift register, all right? Okay, so now what I'd like to do is let's go to the simulator, the Proteus simulator, and let's build up a couple fun circuits, they're already built, and play with those a minute. And then what we're going to do is we're going to go over to the bench and we're going to see what we just built working, which will be kind of cool, all right? So let's go to Proteus now. Okay, so here we are in Proteus. And once again, if you're skipping around all over the place, Proteus is a CAD tool, a PCB and schematic layout tool, but it also has a simulator. And at the end of the class, we're going to do circuit maker PCBs. We're going to do some circuit maker PCBs, some examples, but it doesn't have a simulator, so I can't use it for this stuff, so I'd prefer to use Proteus. Plus, Proteus is very advanced. It's got a very robust and mature simulator, so even if Circuit Maker did have a simulator, I probably wouldn't trust it. Moreover, Proteus not just is a SPICE simulator, a simple analog simulator and digital simulator, it's a full processor level simulator. So you can get processor models, which are right in here, for the AVAR, for the PIC, for ARM Cortexes, and simulate the entire processor. Just pop it down and it'll work, and you can load software. So super cool. So that's why we keep using this. All right. So what do we got? So so one of the cool things is that I used to like to do when I was a little kid, when I was like 10 or 12 learning electronics, is I like to do anything with LEDs. And back then, a long time ago, there was a TV show, a couple cool TV shows. One was called Battlestar Galactica. I'm sure you've heard of that one. There's a new Battlestar Galactica, but there was the old Battlestar Galactica, and the Cylons had a little eye that would go back and forth, right? And then there was Knight Rider, which was about an artificially intelligent car with David Hasselhoff, if you know who that is. If you're from a different country, you may not, but he's kind of a funny guy. Anyway, and his car, which was a black Trans Am, was an AI, and it had a little red light that went back and forth. You can Google it and take a look. Anyway, so one of the first things I wanted to learn to do when I was really young was try and simulate that eye going back and forth, the Cylon eye or the Knight Rider. Now, I didn't do it right here because it's more complicated, require more hardware to do, but this is the beginnings of it. And how I did it was with shift registers, right? So what I've got here is this. I've got the 74HC164, which is a serial to parallel shift register. Then I've got a bunch of LEDs here. This is a bar graph, and you can get LED bar graphs, which are really cool. And in this one, this one has 10 inputs, and then these are all the grounds. All right. So you just hook them up here, and then there you go. And then, so what else do we have? Here's the master reset. I've got it pulled high normally, and then with a switch, I can pull it low and reset the whole thing. I've got A tied high always, so I've got one of the serial inputs tied high, so that means it's gated always, it's gated on. And then we have our bypass capacitor. Don't forget those bypass capacitors, right? The chips won't work, all right? Get those bypass capacitors in there, all right? And then what else do we have here? Then B, which is the serial in, what I did here was I've taken a momentary switch, hooked it up high, give it a pull down, a weak pull down, so it's always got a 0 on it, and then we can inject ones by tapping this switch in real time. Then we've got a little capacitor here, a 100 puff, 100 picofarad. You'll hear engineers call them puff for picofarad or puff. just to clean out this signal a little bit so it doesn't bounce, all right? And then finally, we need a clock source. And so here I've just manually inserted a signal generator. So let me click on this. And if you can see this, I've called it serial clock. It goes from 0 to 5 volts, and we're going to change the frequency. Right now I've got it at 5 hertz, okay? 5 hertz in a 50% duty cycle, so it's a beautiful square wave, all right? Okay, so what do you think is going to happen when I turn this thing on? So what do you think is going to happen? So let's get down and dirty. If this is the real world, all right, and the simulation usually is pretty close to the real world, but if it was the real world, when you power this thing up, so the flip-flops of the shift register, right, may or may not have random data on it, right? So it's possible there could be some random data, and inside of that, right when you power this thing up, all right, depending on what's going on. Now, if it's all completely discharged, then typically it won't, so it should boot up with nothing. So there should be nothing there. Now, the clock is always ticking at 5 hertz. Click, 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 click. So it's shifting the data. All right, so let's go ahead and let's turn the simulation on. Nothing happened. That's exactly what we expect. So if it starts up clean, then nothing happens. However, very important when you design digital systems, you have to take into consideration when something starts up, it may have garbage in it, bits may be on and all that, so you need to have a reset cycle, or as part of the startup sequence, after the hardware turns on, a reset circuit comes along maybe 10, 20, 50 milliseconds later and then pulls the reset lines on everything. So electronically, we might pull this reset down. So now let's reset it. Okay, now we know it's reset, right? And of course, we don't see anything here on the outputs. And each one of these outputs is connected to each one of the bits of the shift register. So we're going to see what's in the shift register in real time. Now, also look here. You see that little red and blue blinking, 1 and 0, 1 and 0, 1 and 0, right? And remember, red is 1 and blue is 0. So the heartbeat is beating, right? So the clock is clocking. Okay, so let's stuff some 1s in here. So here's the switch that's going to allow us, we're just going to tap it, and we can get a 1 in here. Ready? Here we go. There we go. I held it down, I got a couple 1s in there, right? I'll do it again. There, I got just 1. Right? I'll do it again, and then hit it again. See? And I can hold it, and I can fill it up with bits, and then that's it. That's all it does, right? That's the beginning of the little Cylon thing, right? So now, what's something we can do here? So one thing we can do is we can take the output and circulate it back into the input. So that way it would at least circulate around. To get it to go back and forth, that's a whole other story, and that's a good project, right? We can talk about that later. But right now, why don't we say let's circulate the data so we don't lose it, all right? So let's go to another simulation. So we stop the simulation, and let's load another one, this one. All right, and this one, the first one, of course, is Crash Course EE serial 164 _ 01, and this one's 02. Of course, this will be in the materials for the lecture, like always, so don't worry about that. Okay, so what do we have here? So we got a little bit different things going on here. So the first is, you notice I've got these resistors in the output. Now before, I just drove the LEDs directly with the outputs here because the outputs themselves can't drive enough current to burn out or damage the LEDs, so we can just kind of do that. But if we want to pick a signal off, we need to have these resistors here. Otherwise, the LEDs will clamp the voltage. Remember that LEDs clamp voltages at about 2.5 or 3 volts, whatever, right, when they're forward biased. And we need these resistors in here so that we can see what these signals are and get a clean sensing of the signal. So we put these resistors in here. They're all set at 100 ohms. It's a virtual instrument, so we're not going to really see any different brightness. Anyway, now we've got that output. Now we could take it and directly put it back in to this input right here and just tie it here. But what's the problem? That creates a bus conflict, because if there's a 1 coming back, right, here's a 0. So there's a weak 0, right? And then also when I inject a 1, I'm stuffing that back here, right? Because that's also going in this direction. So we don't want to do that. So what we want to do is a clean design. So notice I've added another gate. I've added a 74HC32, okay, an OR gate. So that allows me to send my normal signal here through this channel. And then also, if there's a 1 coming back, I'll get it through this channel. It'll OR them together, and the results will go into this B. Okay, now, there's one mistake here. Not a mistake, an omission. So this will work. Is there anything missing? Anything missing on this? Anything missing? What's missing? Our bypass capacitor. So remember this 74HC32 is an IC. And then we only see one package of it, right? Here, but there's actually 4 packages, and the way that this tool works is you don't see them unless you lay them down, right? But we need another bypass capacitor. So let's just go take this, select it, copy it, and we'll put it right there. Good. And then we'll just go ahead and save this again. All right. 16402. Now we know there's a bypass capacitor that needs to be by this package here. Okay. All right, so let's go ahead and we got the same setup. Everything's the same. We got the reset. We got our data in. We got our clock here. Let's see how fast our clock is going. 3 hertz. Okay. Let's go ahead and run the simulation. And again, what are we expecting? We're expecting nothing to be in here. All right. I'm trying to just get it all on the screen for you. There you go. All right. So here we see the heartbeat running. The clock is running at 3 hertz. There's no bits here, so it started up okay. Let's just do a reset. Okay, good. Okay, now, as I hit this switch, keep an eye on these bits here, and then this very last one is going to get recirculated through here. So kind of try and keep your eye on all these things at once, all right? So let's put a bit in. All right, I missed it. So I didn't hold it long enough because it's at 3 hertz. It's kind of slow. Let me hold a little bit longer. A little bit longer. There we go. So now I injected a 1 into the system. And look, it's circulating. Let's inject another 1 into the system right about now. There we go. And we'll do one more. Ah, no, I don't want to do that. Let's do it again. All right, so here's a 1. There's a 1. And there's a 1. There's a 1. I'm trying to get 3 in here. I'm trying to get them equispaced. So anyway, there's 1. There's 1. Oh, no. It's a lot harder than it looks. There we go. Anyway, I'm getting them on top of each other. So you see how it's circulating. So now it's just constantly circulating. All right. And that's it. And then we could, let's do this. Let's change the clock frequency. Just go in here, double click this. Let's put this to 5 hertz. Speed it up a little bit. Let's run the simulation. Clear it out. Good. And let's put a 1 in there. Put another. There you go. And there it is, and just circulates. That's it. That's the beginning of that Cylon eye. All right, so that's kind of a cool thing. And then there's one more. I think I did something else. If there's another, yeah, 164.3. And yes, we want to save the changes here. Did I do anything else to this? No, no. So forget this one, 164.3. We'll just go back to 164.2. Here we go here. And that's it. Let's just run it again. And forgive the zooming in and zooming out. This tool does not have a smooth kind of a zoom, and you got to use the scrub wheel to do this. Kind of annoying. There we go. So anyway, that's that. So what we're going to do is we're going to actually build this exact circuit, right, with the 74HC164, with the 74HC32, and the LED bars and the reset and all this stuff. We're going to build it over on the bench, all right? So that's what we're going to go do right now. So let's stop here, and I'll meet you on the workbench, and let's build this thing, okay? Bye. Okay, everybody, welcome back, and we're here on the bench. And what do we got here? So you can see here, I've already hooked this up. This one's fairly complicated, so I could have done a time-lapse photography and sped up the camera, but it's basically the same kind of thing that we've been doing. So let's just look at what's going on here. So you can reference the data sheet on your computer to kind of follow along, but we've got the HC164 here, and then we've got the OR gate here. So let's just take this one step at a time. So the first thing is on the HC, let's talk about the outputs. So we've got the outputs QA, QB, or Q0, Q1, Q2, Q3, Q4, etc. And here they are here. So there's 1, 2, 3, 4 of them here, and then the other 4 are here on these pins. So what do I have going on here is if we move this down, and we can zoom in just a little bit, I think, for you, and maintain, there we go. So we have each one of these serial outputs from the flip-flops, or these are the parallel outputs from the flip-flops for the serial register, and we got them going through these 100 ohm resistors. These are LED bars. There's 4 LEDs in each one of these bars, and I believe these ones are yellow LEDs. They're not very bright, but I don't have 2 of the same color. So I've got red, I've got green, I've got yellow, 2 yellows, but I don't have 2 red or 2 green. I probably do someplace, but I don't want to hunt too far. And then here's all the grounds going up to ground, all right? So these are simply the parallel outputs, and I just did them in 2 different colors to show they're 4 bits at a time. Here's the first 4 bits, there's the other 4 bits. Super simple, right? Okay, what else do we need? We need our ground. There's our ground on pin 7. 1, 2, 3, 4, 5, 6, 7. There's our ground, all right? Let's see, we've got our power up here. There's our power up on pin 14, right? And you can see we got that bypass capacitor in there, right? Right next to it, there's that bypass going to ground, so that's good. Okay, what else do we have? On pin 1 and pin 2, those are the 2 serial inputs. And on one of those inputs, see pin 1 here, I've got it pulled up through a 10K to the positive rail, which we're putting in 5 volts here. So that keeps it always gated. Now here's the other input. There's the other input, and where's that going? That's going over here. So let's take a look over here. So here's that OR gate. So here's our OR gate. So the output of the OR gate, which is at pin 3, the first OR gate, remember there's 4 of them in here, 1, 2, 3, 4, they're in those 4 positions. So pin 1 and 2 are the inputs to the first OR gate, pin 3 is the output, it goes right here, and that's that. So the inputs to the OR gate, one of those inputs is the output of the last bit of the serial register, right? There it is. So that's that white line, there it is. This is the very last bit, Q7 or QH, right? And that comes back in to pin 1. Now in pin 2, what do we have? Here's where we have our button where we inject the 1s and 0s, right? So normally we have a pull down on it, so we got a 10K pull down, that gives us our 0. And then if we touch the button, that'll give us our 1, which is right here. Okay, so that's the OR gate. Again, here's power, there's that pin 7 to ground, right? And then here's our V sub CC and our bypass capacitor up here, right? To pin 14, right? Always get that in there, don't forget that. All right, now, so this is our button that injects 1s and 0s. Now, what's this? This white button right here, let's follow this back, and it's going to pin 8, pin 9. So if you go look at the data sheet, which I'll go look at it with you, that is the clear line. Pin 9 is clear, and it's active low. So that means I need to pull this thing up high normally, and there's a resistor kind of hiding here, a 10K pull up high, and then I bring this wire over here, and then the switch brings it low if we press it. Okay, that's our reset. That's our system reset. Okay, let's move on. What else are we missing here? We got an LED here, all right, and this LED has a resistor, a 100 ohm to ground. The other end of the LED, the anode, so the anode is going to this red line, and this brown line goes to ground. What's this red line? These 2 lines are coming from the signal generator. Take a look here on the other camera. So here's our signal generator. We're going to use channel 1 here. Where are we? Channel 1. We're going to output. And then you notice I've got this set up for 3 hertz and 5 volts square wave. All right. And I can change the frequency very easily. Right. So that's that. Normally I don't show you the signal generator. We've seen it so many times. But in this case, I wanted to, because we're, kind of using it as a clock. All right. Let's get back to this. Now, what else are we missing here? So let's see here. Anything else? Oh, and of course the clock signal itself is going into pin 8. So the clock is going into pin 8, and off of that we're driving an LED, and we're loading it a little bit, but it'll be okay. It'll be enough to clock the chip, and we'll be able to see this LED reflect the heartbeat of the system or the clock of the system. And that's it. That's the whole circuit. All right, so that's all there is to it. So let me back out of this a little bit. Okay, so when I turn this thing on, it should start to work. So first what I'm going to do is I'm going to turn the clock on. So over here at the signal generator, here we go. We're going to turn the clock on. All right. And then coming back to the main screen here, we can see this LED is blinking. Then we see some other weird stuff is going on here. We got this LED is kind of turning on and off, and we can see the displays are turning on and off a little bit. What's going on here? This is really important. I want you guys to follow this. So what's happening is this. This clock signal, right, is a clock. It's a 5-volt clock. But because the whole system is powered down, these main rails are not powered up right now. What's happening is this clock is going into this input pin of this IC, and it's finding its way because now the IC is off. It's not powered up. So the IC is like a passive network of resistors and transistors. It's finding its way to power the board up a little bit. So it's kind of powering the board up. So this is why you got to be careful when you have various things sending clock signals or data or serial communications or whatever, they can actually partially power the board up. And here's even worse, they can keep the board powered in a quasi state even when you turn the main power down, and then they can cause bits to stay ones and zeros. So you think you turn the power off, then you turn the power back on, and you don't get a reset. And the reason why is because you still had some other power coming in here. So be careful. Power can find its way through circuits no matter what. Now, let's turn the main power on. This thing will come on. There we go. All right. Notice now this is on solid. These bits are all ones. Wow, not too surprising because there's a bunch of garbage in there. So let's reset the whole thing. I'm going to press this button. That's our reset. All right, so now we reset the whole thing. That hit that clear line on pin what, 9? Pin 9, yep, pin 9. All right, which is this line right here going there. All right, now we're going to inject some ones here. Now take a look at the signal generator. We got a 3 hertz signal, 3 hertz, so it's pretty slow, all right? So here we go, and I'm going to just put a 1 in here. There we go, there's a 1. Get another one. I put 2 on top of each other. There we go. And there we go. Look at that. Now on the camera, I think this kind of looks green, but it's yellow. And there's no, now let me fill it up. So now I filled it up, right? Let me reset it. Now just put 1 in here, just 1. There we go. There's just 1. And right when it hits the middle, I'm going to try and add another one. Right there. Ah, missed it. Right there. You can make a game out of this. There we go. Right now they're not cycling in each half. They're just, since there's 2 bits and they're equidistant, it looks like it, but they're going all the way around and cycling all the way around. Now in real time, let's change the frequency. All right, so it's at 3 hertz. Here we go. Watch. 4, 5, 6, 7, 8, 9, 10. There's 10 hertz. All right. Now let's just put 1 bit in here. There we go. There's 1 bit. So you can see we've almost got that Cylon eye. We just needed to go back and forth, right? So I'll kind of leave that as an exercise how you would do that. Okay, now while this thing is running hot, let's switch the LEDs out, okay? Let's throw caution to the wind here. I promise I won't break it. So I'm going to grab some little pliers. I don't want to short anything. So I'm just going to pull this out real carefully. There we go. And we'll put this one in. Put this one in right here, which is red. Okay, that's cool. There's a red one. All right, let's pop that one out. The other one. And don't want to damage it. And I think, yep, here's a green one. There's a green one. There we go. Here we go. So pretty cool. So that's it. So that is a shift register. That is a shift register. There it is right there. So you can see right off the bat, this is fun to play with. It's, you know, anything with LEDs I like. And then now you got this one shift register and you're shifting this way. So then how could you get it to go back and go for, you know, back and forth, back and forth? Lots of different ways to do it, but you may need more shift registers, right? You may need 16 bits, right, to go back this way and then back this way, because how would you get the data to shift backwards, right? Or is there something you could do with the output to make it look like it's shifting backwards? Maybe inverting the output and doing something to it, it would look like it's going backwards, right? So anyway, I'll leave that to you for now to kind of figure out. So that's it, and we'll just speed this up a little bit. We'll speed it up to 15 hertz. There's 15 hertz. Now it's getting smooth. See that? It's getting pretty smooth. 30 hertz. Here comes 30, and at 30 we won't be able to see it. Now it's you know, blurring, right? Now if we go to 60 hertz, let's go to 60, 40, 50, 60. There it is, it's solid. There's a TV set. So now we know that there's only a couple pixels on, isn't there? But it looks like they're always on because we're moving it so fast we can't see it. Let's slow it back down, right? Our eyes can see there's about 30 hertz, right? There's 30 hertz right there. Okay, still, you know, and we've filled the bit. So what's happened here is we've filled the bits up. There we go. Okay. There we go. So there's 60 hertz again. So the other one, some extra bits got filled, and that's why it looked solid. So that might be strobing with the camera, right? Making some interesting pattern. But anyway, that's it. All right. So hopefully you had a little fun there, a little building stuff. And so I will see you in the next lecture, which I think we're talking about buffers, which are important things for amplification and to keep signals strong. All right. Oh, and you see what's happening there? So what's happening is it's getting filled up, and so what's happening is there's noise, and because the signal is driving this LED and all this, we're actually getting some extra 1 bits here that we don't want to get, and it's filling up. So that's actually why you got to be careful when you build these boards on the solderless breadboard. Okay. Okay, that's it. See you in the next lecture. Bye. All right, welcome back, and we're on the next section here of the book. We've been going through various kinds of ICs of different kinds of classes that have fundamental operations or features that kind of cover all the different aspects of digital electronics and things that you would do. So the next section we're on here is buffers. We're going to do buffers and drivers today in this lecture. So in the book here, we're in section 634, and we're going to start off with buffers and talk about buffers and drivers and what those things are. And again, as you're reading through here, there's a lot of references to the XGS or X Game Station. That's just an embedded system that this book refers to as a model, so that there's just something to talk about. So anyway, before I start, so I have a little 2-year-old girl, and she steals my calculators. And she thinks they're phones, so she puts them up to her head and she thinks they're phones. Anyway, I have these two here. This is a Casio FX 115, Casio FX 115W, good little calculator, and then another one is the FX 300W, and these are both good calculators. The FX 115W I liked because it had logic, so it could do decimal and binary and hexadecimal. And then the 300W has some other features that I liked also. But since these were lost, they disappeared, I had to get a couple new calculators. Now, of course, I've got, a big heavy-duty TI-83. So anybody who knows anything about calculators knows about the TI-83. This is hardcore, serious stuff, and but it's a little overkill just if you want to multiply numbers. So anyway, for 15, 20 bucks on Amazon, I got this new FX 300ES. This is a really cool calculator. It comes in blue, red, and black, I think. So I got the blue one. Really, really nice, very light. And the other one that I got here is another Casio. And this is an FX 991ES, and this has the logic functions, decimal, hexadecimal, binary, octal, and all that. But it also does, you can do integrals with it and things like that. So it's very, very cool. It does fractions. So anyway, you can never have too many calculators. And when you're doing this work, it's always good to have a calculator with you so you can kind of, punch that out and check your calculations and stuff. So I always like to have those with me. So anyway, okay, let's talk about buffers. All right, so whenever you're designing any kind of digital system, if you've got parts of a system that communicate information to other parts of a system, they either communicate the information serial or in parallel. Either way, a lot of times these signals need to be buffered, and all that simply means they just need to be amplified. So we learned that with LS type technology or low voltage TTL technology or HC CMOS technology, no matter what, there's a fan out of these ICs. In other words, how many other ICs can these signals drive before they deteriorate? So what we want to do as we're designing something is we don't want to, load these signals so much that they may still work, but we may slow down the signal, we may add noise, all kinds of different things. So a lot of times what you'll do is you want to keep those signals really strong, just like a phone signal or whatever, and you'll buffer them. And all the buffer is really an amplifier. And many times it doesn't do anything to the signal other than amplify it. And by amplify it, we mean amplify the current drive of it, and or square the signal back up. We're talking about digital signals here, not analog signals, all right? So buffers, all right, so basically there's a couple different kinds of buffers. Some of them are latching, which means they may store information, and then some are pass through. They just amplify the information, all right? So we're going to take a look at a couple different ICs here. So first there's this 74HC244, or just called a 244, and there's variations of this IC, so and different kinds of logic families, right? So this is just showing the HC version of it here. And this is an octal buffer line driver 3-state. All right, so there's a lot of words there. So octal obviously means 8, and you're going to find that common theme. Obviously with digital electronics, things are going to be in 4s or 8s because bytes obviously have 8 bits and nibbles have 4 bits. All right, and so octal buffer line driver, and this particular IC is also 3-state, so it's tri-statable, which is nice. So we can go here and take a look at the different diagrams, and so the pin configuration, a little cryptic, not quite sure what that is talking about yet, and then this is this IEC logic symbol. This is a kind of an industry consortium that you draw logic symbols in a certain way. I've never liked that. I just ignore that. I like this logic symbol that shows the actual gates. So let's take a look here. Matter of fact, let's zoom in just a teeny tiny bit. There we go. All right, and so what we see here is we've got, so this is broken into 2 different 4-bit nibbles here. And we've got an input and output, input, output, input, output, input, output. Then we've got an enable here. And this enable basically turns every one of these amplifiers or these buffers on and turns the output on. If it's off, then they go tri-state. So the reason that we have this tri-state ability is that we might have more than one output tied to the same physical wire. So we might have one bus, say we might have multiple data buses. So in a system, say that we're trying to save space or we only have so much space. So maybe we have one data bus, and that data bus, let's just say, is 8 signals. It's got 8 signals, right? And it's representing bytes of data in parallel. But let's say that we have 3 or 4 or 5 different sources that want to talk to that data bus, right? So what we would do is we would put one of these buffers, so we have these 5 different sources of data, and then we buffer them, but also they're tri-stated so that only each one of these sources that are on at one time will drive the bus, okay? So that's completely confusing, I know. Let's go look at it. All right, so let's say that we have 4 or 5, whatever, different microcontrollers, something like that, okay? And I'm just going to represent them here. All right, so we'll call this, MPU 0, we'll call this MPU 1, and then we'll call this MPU N, all right? And each one of these is some kind of microcontroller. And then let's imagine that we have some kind of system-wide bus that information is going to travel on, right? So that bus is going to have 8 lines on it. 1, 2, 3, 4, 5, 6, 7, 8. So imagine there's 8 lines on this bus, okay? So it's got 8 signal lines, all right? So now what I'd like to do is, since we know that it's got 8 lines, I would just like to abstract that and just use 1 line, okay? So let's just erase all this. All right, and then we're just gonna draw this like this. And a lot of times what you'll see on schematics is a bus will kind of be a thickened line, something like that, and kind of filled in to differentiate it from a normal line. So I'm just kind of dotting it in here, kind of filling it in a little bit. All right, so that's our bus right there. Okay, and now we've got each one of these MPUs. And let's say that we want to connect every one of them to this bus. All right, and maybe the bus is going to be used bidirectional, so information may flow in both directions. Okay, like that. Maybe it's so that we can communicate, between these things, something like that. Maybe it's so that we can communicate out here. Maybe it's over here. Don't really know. But what I do know is that if we wanted to do that, here would be the problem. So let's say that MPU 0 wants to send data this way. All right, so let's say that MPU wants to send data this way. Let's say that MPU1 also wants to send data this way. All right, and then maybe later we could say that MPU N wants to receive data. Okay, So now here is the problem. So MPU N here is receiving data, so that means its bus, its internal bus is acting as inputs, all right? So let's just hold off on that for a second. But MPU 0 and MPU 1, if both of these things are physically connected to this bus, and remember this wire really represents, 8 lines here, right? 8 lines here. If both of these try to drive this bus at the same time, and there's, and say the pattern here is a bunch of ones, and over here it's a bunch of zeros, right? What's going to happen is we're going to have a conflict. So we're going to have short circuits and all that, all right? So what we need is we need a way to first isolate the buses from the processors to this main physical bus here, all right? So we want to isolate these things. So what we're going to do is we're going to put these buffer ICs here, like this. And now these ICs that we're talking about right now, this 244 that we're talking about, is one directional, right? We could use it for 2 directions. It's got 8 different bits, and it's got two banks of 4 bits. But if we want to use all 8 bits, we only can get it to go in one direction. So let's say that it only can go in this direction right now. Okay, it only goes in this direction. And again, this one only goes in this direction. All right. So now we connect these buses here and here like this. So there's that bus connected. Here's this bus connected. And by connected, I mean all 8 wires, all 8 outputs of each one of these 244 ICs, right? And each one of these is a 244, 244, 244. Then we connect it to the 8 bits on the processor output. Maybe this is an actual data bus. Maybe it's a GPIO, general purpose IO pins. Don't know, but we've got all those. And then another notation is you can see like this. You'll see like a little slash through the lines, 8. That means there's 8 bits, right? 8 bits of data. That's another little notation you might see that just means there's 8 bits there. Okay, now. So here's the cool part. So say MPU wants to talk to this bus, all right? Here's the situation. So each one of these has this output enable pin, all right? Output enable. And it's low here, output enable, output enable. All right, and then we take all 3 of those pins and we collect them. So I'm going to just bring this down here, bring this down here, and bring this down here. We're going to collect them all together, like this. And then this right here is control. This is a control, all right? This is a control bus. All right, so now what happens is this. So let's say that all of these output enables are off. So all these are high right now because this is output enable asserted low. So all these are high. So what that means is I don't care what this processor is doing on this end of the buffer, on the top end here, right? If it's driving these IO bits, doesn't really matter because it's not going to get through each one of these buffers because the output enable is disabled. That's where that tri-state comes into play. Now, let's say that we turn this one on right here. So we turn this one on, so we turn output enable, and then we assert it low. Okay? And then this output enable here is high, and then this output enable here is also high. Okay, so these are off. So this one's got a 0 on it, this one's got a 1 on it, and this one's got a 1 on it. Okay, so in this case, this one would be on, and then so what's going to happen is we're going to get data, and let's see, what color will we? What color is data? Let's see. How about let's make data white. So now data will be able to flow through here. So here's this white data, and then get into this bus. All right, so it'll be able to flow, and now we'll be able to drive the bus. Now, 2 good things. One, because this is a tri-state IC, all these are off, so we know they're not driving the bus currently at the same time because our control bus here only is going to enable one of these at once. That's number 1. Number 2 is we've got this driver IC here, and it's driving this bus. Well, this is a physical object. It could be rather large. It could be inches. It could even be, feet long. Who knows? It could be a cable for all we know, right? And we want a lot of drive. So these driver ICs, like the 244, are designed to drive heavier loads than just the standard little I/O pin on an IC or a little microcontroller. So they're designed to drive things, all right? And they're also designed to be protected so they can't get damaged. So here's another thing. Let's say that something bad happens, something bad happens here, and to this bus, all right? Something happens here to this bus, bad, whatever. And then now what's going to happen is whatever that bad thing is, an overvoltage, a spike, something like that, the ICs are going to protect everything above these ICs here, so the processors don't get damaged. So not only does it drive the bus, it allows different devices to drive the bus independently. Also, if there's something that happens to this bus down here, this green bus, an overvoltage, a spike, a lightning event, whatever, it'll damage the IC here, but not get back into the processor or whatever's driving the buses. So again, it's also protection. So it drives, it allows you to drive larger loads, it allows you to detach, and each one of these different buffers can communicate independently to the bus, and then of course protect each one of these devices. That's what a buffer does. So a buffer driver does this. It basically drives things and allows you to amplify signals. And then another case would be like this. So here's another simplified case. Let's just say that we have, one output here. So we've got one device. Again, maybe this is an MPU. Maybe it's an Arduino, right? Maybe it's a Raspberry Pi. And maybe we've got some outputs here. Maybe we got 4 I/O pins. Maybe we got 4 GPIO pins, right? That we want to use for something. All right. So we got these 4 pins right here. And now, what we look at the data sheet, and each one of these says it can, drive so much current. But I want to drive, like, say, 20 different devices with this. I want to drive them all simultaneously. So 1, 2, 3, ... down here. So here is, the 0th, the 1, the 2, and then down here is the 19th. So there's like 20 different devices. All right, 20 different devices, and the fan out of each one of these is maybe 5 or 10 loads. So we can't do this. So what are we going to do? We just put a buffer here. All right, a buffer driver like a 244. Put a 244 right there, and now we can take that and we can take that bus and we can connect it in parallel to every single one of these things. All right, and now that 244 buffers the signal. It also protects it from all of these things and then allows us to drive all this. What's the downside? Well, cost, right? You got to add the buffer. All right, that's one thing. Also propagation delay. So now there's some propagation delay here, right? PD. So time, a delta t. So as we output these signals here, there's going to be another anywhere from 1 to 10 nanoseconds, depending on what the model is of this buffer. Is it a 244? Is it something else? It's at high speed, whatever. 1 to 10 nanoseconds that it's going to take the signal to propagate through here. So as we put a pulse through here, it's got to go through here, then it's got to go up here, right? And then of course in parallel it goes to all these other guys, right? So there's a propagation delay. So there's some timing penalty. So in other words, if you build a system and then say over here, you might put another buffer. Say there's another buffer right here, right? And then this one could fan out, right? And so again, we're going to get another propagation delay here, and so on and so forth. So when we send the signal out here, right, we have to be careful of one thing, is that say that we take any of these signals right here. Say I take this signal here, and I take this version of the signal here. So I'm just going to call this X. And then the version of the signal that comes through here, I'll call this X primed. So X leads X primed by PD nanoseconds, right? So if we look at this, let's make a little timing diagram here, So here's time right here, all right? And there's signal voltage, and we'll just call this high up here, right? Which is like V sub CC. All right, and then we'll draw 2 different graphs here. So there's high V sub CC, and then here's another high V sub CC, kind of these little 2 marks right here. All right, so now let's say that we have the signal, this last signal right here, right, which I'm calling X. So here's X. So here comes X, All right, and there's X right there. Looks like that. Okay, that's X. What does X prime look like? Well, there's a little bit of propagation delay, so X primed is going to look like this. Okay, so you can see there's some difference in there, right? And this is X primed here. There's some difference in here, and let's use red here. So if we kind of mark down here like this, carefully, this little delta right here, so if I look inside there, that little delta, that's that PD. So that's that shift. So this right here is, called skew. All right, and if they're clocks or signals, it's called signal skew, clock skew, this or that, whatever. And so what can happen is if you buffer certain signals, you don't buffer all of the signals can get desynchronized. Now, if the skew is 1% or 10% of the clock rate of the system or whatever, it's not going to be a big deal. But as you get close to 25% or 50%, if that skew can basically take a signal and push it into another clock cycle, that is bad. So you got to be careful when you buffer things that you buffer them the same amount so that the delays are consistent. Okay? All right, so let's go back to our document here. So here was the 244, all right? And so this is just talking about that, just a couple figures here. And of course, I want you to read this, all right? And then this is just drilling down into the inputs. So 1A0 through 1A3 are the inputs for bank 1, and then 2A0 through 2A3 are the inputs for bank 2. It's just got two 4-bit buffers. You can tie them both together and just use them as 8 bits, and you would just tie and then here are the outputs. In that case, you just tie the two control inputs together. If you want to use them separately, then you can keep these separate. So basically you can use this as a 8-bit buffer unidirectional, or so like this, you can have the bits going that way, or you could have two 4-bit buffers and put them like this in different directions, right? Put them in different directions, going in different directions. All right. So anyway, that is the 244. So just a very common good worker chip that you're going to use a lot. And then here's actually what we just did, right? We just did that kind of graphic. We had a couple different buses here, and we're showing the buses, and then they both share a common bus going to some device, and then we select them with either 0 or 1. And you can see in this case, we got the select line. We take it directly into this first one, but then we invert it into the second one. So when the select is either 0 or 1, it mutually exclusively selects either this buffer or this buffer, so we don't have a bus contingency. And that's when bus contingency is when you have two or more things on the bus at the same time. All right. Okay. Now, so the next thing let's talk about are latches. So latches are a little bit different. Okay. So before we go into that, let's go ahead and we'll go here and let's type in 74LVC244, for example. All right, and this is the low voltage CMOS version of the IC we just been talking about here. So I'm just going to grab one from let's see, Texas Instruments. Grab one of these guys. They're all the same, roughly, just different packages. So this is the 74LVC244A. All right. So this is a modern IC, and you can see this is a 2016 date for this data sheet. So very, very new IC. All right, and so this, these ICs have been around since the 70s. So this is something, that's why I call it a worker IC. It's not going anywhere anytime soon. People love it. Very simple. All right, so again, here's our logic diagram. Notice that it's broken into two 4-bit banks, and again, you can just use them all as one 8-bit bank or two separate banks. It just gives you a little bit of flexibility to make it either a bidirectional 4-bit bus or a unidirectional 8-bit bus. All right, and again, the labelings are all the same: 1A1, 1A2, 1A3, 1A4, and the outputs are Ys, and then bank 2. All right, and then the output enables, which go from trice. Now, very, very subtle little thing here. These are not gating these outputs. They are not gating the outputs. In other words, when I deassert this line and I make it high, I don't get zeros out of these outputs. I get nothing out of these outputs. They go tri-state. Their impedance goes to many millions of ohms or infinity. So be very careful with that. When we had the clock inputs on these shift registers, they were gated. So when we deasserted one of those clock inputs, we didn't get a tri-state output, we just got a 0. We actually got logic 0. There is no logic zeros here. When you deassert this, you're not getting zeros out of here, you're getting nothing out of here. They are in tri-state mode, so be careful with that. All right. Anyway, so this is showing this logic diagram, which is exactly what we thought. And then there's all these cool different packages here, right? Here's a BGA package, very hard, ball grid array, not fun to solder. But what I want to show you is the speeds. So let's get down to the speeds here. Electrical characteristics. We're looking for switching characteristics. Here we go. All right. So at different voltage levels, and this is what's beautiful about the LV technology, low voltage CMOS, we can run this down to 1.5 volts, really save some power, or up to 3.3 volts. All right. And then based on these different voltages, we have these different switching times here. Look at some of these times. So in the range that we're talking about here at 25 degrees Celsius, that's kind of the average ambient. We're looking here at typical switching speeds at 3.3 of 3.9 nanoseconds. 3.9 nanoseconds. So let's get my new calculator, and we're going to do 3.9 nanoseconds. Let's figure out the frequency, right? So 3.9 nanoseconds here, and to the minus ninth, and then we're going to invert that. And I'm looking for it on my new calculator. Here it is here, and then we'll put that in engineering mode. So that's 256, can you see that? 256 megahertz. 256 megahertz. 256, of course, should be a number you like and love. 256, 2 to the 8th. So this will go to 256 megahertz. So this is not a slow IC, very fast. And so this IC, this LVC, could take care of most of your driving and buffering situations on most of your microcontrollers, right? Very few microcontrollers go over 100 megahertz, 200 megahertz, unless they're Cortex processors or ARM processors, but typically they're going to be sub 100 megahertz. So this buffer will be more than ample for you to be able to signal at those rates, since it can go so fast. All right. Okay, so let's keep going here. Let's see. All right. So the next thing that we're going to talk about is a latch. Now, a latch is a little bit different. So if we look back, at the architecture of the buffer, it's passive. It's just basically a bunch of amplifiers. All right. So these are all non-inverting amplifiers. Okay. So there's no memory there. So you have to drive the amplifier to get an output. If you don't drive it, the input will just float to something, and then whatever it floats to, you'll get that as the output, right? But there's no memory here, no memory. Okay, now, when we're talking about latches, notice it says octal transparent D-type latch with 3-state outputs. Okay, so this is a Cadillac of these buffer chips. So not only is it a buffer, not only is it tri-state outputs, it's got a 3-state output, and I didn't explicitly say why it's 3-state. Well, state 1 is a 1, state 2 is a 0, and the third state is a Z, high impedance. So that's the 3 states. That's why it's called 3 states. All right. I prefer to say tri-state output, but anyway, 3-state outputs. Okay, so it's a D-type latch, transparent D-type latch. So what on earth does this mean? So of course, you're going to read this, and I'm going to talk about latches right here. All right, but what we want here is this does not have the logic diagram, so let's go get one. So let's go look at our, we'll look for 74 LVC 373. Let's see if that one pops up here. And we're just looking at this again. All right, so here's the LVC version of it. And we'll just find one here. Here's a Texas Instruments version. All right, and let's see here. Anything, also, take a look at these prices here. And what's nice about DigiKey also is it shows you budgetary pricing. Obviously, you've seen this 100 times at this point. But 1 is 60 cents, then 1,000 is 25 cents. So that's pretty good. So it gives you a curve. You can kind of extrapolate. And then, of course, if you really are going to buy 1,000 chips, just call DigiKey. They'll give you a better price. I guarantee it. No matter what, they'll always do a little bit better than what's on here. Or you can just put them in your cart and buy them. All right. Let's take a look at the data sheet. Let's zoom in a little bit here. Okay, so again, very modern chip. The data sheet was last updated in 2014. All right, and talking about different applications. These applications are just sometimes completely in left field. They're just completely random things, because you could apply this stuff to anything from, a control board, an F-16 fighter, to, a video game, to a calculator. So they just come up with random stuff. Network switches, TV set-top boxes, motor drives, PCs, and notebooks, right? What does that even mean? PCs and notebooks, all right? Anyway, here's showing one of these latches. And so we already know what a D-type flip-flop is. It's basically a few cross-coupled NAND or NOR gates, and by applying a signal and clocking it, you can get it to remember the data as it recirculates in a feedback loop, right? And so these things are set up so that there's no clock required, right? So there's no clock required, so it's continually latching. And so what happens is this. As you put data on this input right here, right? And then you turn this latch enable on. See, this latch kind of sits on this C1, this kind of clock pin. And as you leave this latch enable on, anything that you put on this D output input will then be sent to this output here, the Q output, 1Q. So it's called a transparent latch because the data transparently flows from input to output while this latch enable is asserted. And remember, asserted just means whether it's high or low, whichever way it turns the thing on. In this case, it's asserted high. There's no bar over it. All right. So as long as you put data on this input here, and you have this latch enabled, however you change this data, Q will follow it and change in real time. All right. Then when you turn the latch enable off, it will remember what the input was, and now it doesn't care what you do to D anymore. It's locked into the memory. So this is an actual memory bit. Now, this output enable here, we don't really care about this. This output enable just turns the actual output on, right? So there's our tri-state control. And again, it's asserted low. So you could just remove this whole little piece here if you wanted to. And all we really have is a flip-flop, an unclocked flip-flop that's or a level sensitive flip-flop, not edge sensitive. And this LE is latch enable. So the cool thing about these things is this. So let's say that you have a system and you have a bus and you hook it up to one of these D-type latches, then you clock the latch enable, right, while holding the bus stable. You clock it, right? It'll latch the data into the D-type flip-flops, and then you just release the latch enable, and then you don't have to drive that bus anymore. You can go do something else with it. Now the data is locked inside of there, okay? And then you can output it and do whatever. So it's like a buffer, except it's got memory. So why would we need that? Well, a lot of reasons, right? And let me show you. Let's draw something up here. All right. So let's say, for example, we want to drive a 16-bit device, okay? But we like little Arduinos, you know, and you're maybe a fan of the 8-bit Arduino, right? And of course, this class is about electronics, not microcontrollers. So sometimes I talk about them, and I'm assuming a little bit that you have a little bit experience. But so let's say that we're talking about an Arduino here. And the 8-bit Arduino, 8-bit, the very first one, the little Uno, uses a 328 processor, an Atmel ATmega 328, and the more modern ones use a 328P. It's just the pico power version of the processor, just a little bit more low power. And of course, there's 100 different variants of Arduinos, but this is kind of the Arduino Prime. Anyway, it's an 8-bit processor, and there's not a whole lot of GPIO, and there's no external bus. So if you want to output some bits, right, you have to use the GPIO pins. Okay, so now let's say that, for example, that we have some 16-bit device over here. So here is some kind of modern 16-bit device. All right, 16-bit, don't know what it is, don't care what it is. All I know is I've got 16 lines right here, all right, and I got to drive these things all at once. So here, this is a 16-bit bus here, okay? Okay, now over here on our little Arduino, we've only got some GPIOs. Maybe we got 8 GPIOs we can use here, right? And we can output 8-bit data. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. So here's our 8 data lines. Okay, so 8 lines right here. Okay, so now we got 16 bits here, we got 8 here, and somehow I got to get this data into this thing, but I got to get it 16 bits at a time. So what are we going to do? Okay, so check this out. This is what we're going to do. So what we're going to do is first we're going to find a color that we like. All right, so let's say that let's get 2 of these D-type latches. So here's one of them, and here's another one of them. Okay, so here's 2 of these D-type latches. Now let's go back and let's look at the logic diagram here. All right, and I want to show you, and again, sorry for the scrolling. Close your eyes. I know some people, it hurts their eyes. I wanted to show you a complete logic diagram, and good. This is sort of. All right, so what this is showing right here is there's only one output enable, and then here's 1D to 8D. So here's the inputs, the Ds and the Qs. Okay, the Ds and the Qs, and then we have that latch enable, right, which is going into this, like this clock signal. So if we look at the IC, here are the pins here, right? And so we've got 1Q to 8Q, so it doesn't start with 0, and then we've got 1D to 8D, okay? All right, and then we've got this latch enable pin right here. All right, so this LE pin. Okay, okay. So the latch enable is what latches the actual data, and then the output enable just turns the thing on. All right, so let's remember that. We know that. Okay, and let's go back here. Okay, so now what we're going to do is this. We are going to take the output of this first one here. So this is our 373, right? 373. All right, and why don't we say that this is bit 0, bit 1, down to bit 15. So the first 8 bits here is the low byte, and the upper 8 bits is the high byte. Okay, high byte. All right, so now what we're going to do is we're going to take these things here. We're going to call this the low byte, and we'll call this one the high byte, right? And we're going to take these 8 lines here, and we're going to just connect them right here, right? I'm just going to connect them. 1, 2, 3, right? Dot, 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 and down here someplace. So this represents 8 lines. Going to do the same thing here. There's that one. There's that one. All right, and then draw another little thing here to kind of squeeze that in here, and dot, 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 like this, and then there's 8 lines here. So now what we've done is we have a total of 16 lines here, right? So there's a total of 16 lines here, from here to here, 16 lines. And so now we're using each one of these latches to drive this device here. So now what happens is, so what we do is we first load the low byte, then we load the high byte. So now what do? Okay, so now what we need, here's our bus. So we take this whole bus right here, and we put that right into that guy. Take the same bus, put it right into that guy. All right. So now we got the same bus driving both. Now we're going to need a couple other lines here. So we're going to need a one line here to control the output enable of this stuff. All right. So here's that output enable. Here's that output enable. And maybe we're going to control that, maybe not, but let's assume we're going to control it. So we'll assume we have another GPIO to control that output enable line. All right. Now we have that latch enable. We have that latch enable. Let's use a different color here. We have the latch enable line right there. So there's that latch enable, and here's that latch enable line here. Let's bring these both out here. So here's this one, and here's this one. So now what we can do is we can call this latch enable low, so latch enable L, and then this one is latch enable high. All right, so we got these 2 inputs right here. All right, and then now we're going to have to, again, drive these with our processor here and connect that there. So we're going to have some lines to control this. Or we might be able to get away with doing what I did with the other thing is what we could do here is we could, put an inverter. Let me just erase these little things here. Can put an inverter here. So we could put an inverter on one of these like this, and then with the same signal, so we call this latch enable. So now when this latch enable is high, so let's make a little logic diagram here. So when this is high, so there's latch enable, and when the latch enable is 1 or 0, so when latch enable is 1, then we're going to get a 1 here, and we're going to get a 0 here. So this upper one is not going to get enabled, but the lower one is going to get enabled. So when we're putting a 1 in here, basically this latch enable high byte is going to get latched. So we could say that this is latch enable high. And then when we put a 0, this is latch enable low. So basically, if you want to write the top latch, right? If you want to write the low latch, then you go on here and you put a low on this. All right, you put a 0 on here, and that'll give you access to the low latch. Then just put data on the data bus, then flip the latch, and as you flip the latch, it'll latch the data in there. Now, go put data on the data bus. The latch is already high, and then that'll latch through onto the other bus. And then you just leave it high, and now you would have all 16 bits that would be able to go into your 16-bit device. Okay, so that is what you would use these kinds of devices for. So since they have memory, after I've written to one of these things, I can just stop writing to it. I'm done, and it holds the memory. So now I can create bigger data words by using these as basically little 8-bit memories. That's what they are, the little 8-bit memories, okay? And that's one use of doing something like that. So for example, say you wanted to interface, and again, I use these Arduino examples because I feel like the whole world knows what these things are at this point, or at least has heard of them. Say like we want to access a big memory. The Arduino has, what does it have, 2K of RAM and is it 16K of flash? You can Google it. But anyway, let's say that we wanted a big memory, right? Something big size, like 256K or a megabyte of flash, right? But we want it to be parallel, not serial. So we go on DigiKey, we find a 256K memory or a 1 megabyte memory. 256K maybe is a little bit easier, a little bit cheaper. 256K SRAM, and it's got an address bus and it's got an 8-bit data bus, right? But that address bus is a lot of bits, right? It's 256K. So you'd have to figure out what is that 2 to the 16th would be, that would be 64K, 17, 18, I think 19 bits. So the address bus would be 19 bits, I think, and then the data bus would be 8 bits. Either way, you're going to have to build up that address with some buffers like this because the little Arduino can't, output all that. So what you would do is you would put like 3 of these ICs, right? 3 of these things. And that would give you your like a 24-bit address space, and then you would write into those 3, and then you'd have another one for the data bus, right? And that data bus would be bidirectional because data would have to go in one direction, data would have to go in the other direction. So that would allow you to interface a SRAM chip to your Arduino and then have 256K of memory, right? Pretty cool. Okay, all right, let's go back. So that's what those buffer chips are for. All right, and the 373 is just an example, and like you saw, there's the LV version, LVC, HC, all kinds of variants of it, all kinds of logic families. All right, and I think, yeah. So here's the next thing that I want to talk about. So this is again, this is a workhorse IC that you're going to see always, which is the 245. All right, and this just happens to be the HC245. But this is a 3-state transceiver, all right? So it's octal, meaning there's 8 bits. So what's cool about this is it allows data to flow in both directions. So say like we wanted to buffer a data bus. Data bus goes in both directions. Address bus goes in one direction. But if we wanted to have data going out and in, some kind of data bus, a parallel data bus, we need what's called a transceiver, and that's what the word transceiver means. A driver means I drive in one direction. A transceiver means I can transmit and receive, transceiver, all right? And so instead of hooking up a couple of 244 chips or 373 chips back to back and flipping them around and doing that so you can go in both directions, obviously the designers at these companies in the 80s figured this out, and they're like, or in the 70s, said, hey, let's just make transceivers. All right, so it does exactly what we'd expect. Now take a look at it. So here's the schematic. So notice the driver only had half of this, only in one direction, but the transceiver has it in both directions, all right? So you've basically got an 8-bit data bus on one side, an 8-bit data bus on the other side. You've got maybe an enable, and then you've got a direction control that controls which way the data goes. So is the data going, this way, or is the data going this way? All right, and if you look at this schematic right here, we can see we've got power V sub CC, we've got ground, and then see this A1 through A8? That's not address, that's just data. So that's data 1 through 8, so that's bus A. And then over here we've got a bus B, B1 through B8. So we got bus B. And then we have this G here, which is this enable. All right, and then we have this direction. So this G is the tri-state enable here. All right, so now if you go look at the truth table here, look at G. When G is low, all right, and depending on the direction input, which is low or high, data will flow from B to A or A to B. If G is high, then it goes to tri-state. That's what that X means, right? So it doesn't matter what, doesn't matter what direction you're putting, doesn't matter. Now, when you got this high, you've disabled the tri-state output, and now you've got isolation or high impedance. So this is what you would use for a bidirectional bus of some kind. Very, very cool chip. This is one of my favorite chips. And in fact, if I need to buffer something, a lot of times, instead of having both transceivers and drivers, I'll just use all transceivers. They're a little bit more expensive, and I'm only going to use half of it in many cases, but I just like it because it gives me the option, if I need to send something the other direction, I can do it, right? Okay, and then here I talk about you could use multiple 74244s or 373s to create a transceiver, but why do that when you can just get a 245? All right, and then this is just showing what we just saw in the truth table. Let's go look for an actual IC. All right, and let's go. Let's look for a fast. So let's take a look at this. So LVC 245. All right, and here it is right here. Let's find the Texas Instrument version of it. All right, and let's go take a look at the data sheet. A couple things I want to bring your attention to. So this will work from 1.65 to 3.6 volts, but the LVC technology, the C technology, allows to have inputs up to 5.5 volts. So you can use TTL inputs on this and interface very easily to TTL logic or 5-volt logic. All right, so like your Arduino stuff. All right, and then it's just showing one gate here, and then there's 7 other channels, right? So they just do that to save space. Let me scroll down here. Let's find those switching characteristics. Let's see how fast this thing goes. And now there's 2 things. There's the propagation delay through the buffer, but then there's also another, and you'll see that also in the switching. When you switch directions, how long does it take for the direction to switch and the data to flow through? That's another concern if you do a lot of switching back and forth, right? If you're writing and reading, okay? So you can see here under switching characteristics, here it is from input A or B, right? And then it's saying how long does it take for output enable to work, right? And all these different things. So right now we just care about this propagation delay. We got all the different voltages. Let's say we're running at 3.3, and here's our temperature, 25 degrees C, which is our kind of room temperature. And it looks like a typical delay of 3.8 nanoseconds, a fast delay of 1.5, and worst case is 6.1. So again, very, very fast IC. At 3.8 nanoseconds on average, all right? So this thing's really going to scream. Let's go see, now say we needed something, so 3.8 nanoseconds, get on your calculator and you tell me how fast that is. So 3.8 to the minus 9th, we'll invert that. And how many megahertz is this? About 260 megahertz. Yeah, about 263 megahertz, right? 263 megahertz. But what if we need something faster, right? Is there anything faster? Now, there's what's called an F series of these ICs. Now, I don't know if there's a 74F245. There is, all right, and F is fast, all right? And let's go take a look here, and let's see what kind of speed we're talking about in this case, all right? So F is the kind of fast TTL version, and let's go down to the switching characteristics. Okay. And here we go. So T propagation from A to B or B to A is, and where's our voltage that we want? These are at 5 volts. So no love here really. So about the same. All right, that typical is about 3.8, so no real help there. But anyway, if you go look through some of the other logic families, the other advanced logic families, you can find something that's faster than that LVC. There's like, there's about 20 or 30 logic families at this point, and you can find something faster if you need it. Okay, so that's it. So now we've talked about buffers, drivers that drive signals and just amplify them. We've talked about latches, which are like memories. And you basically can put some data in there, you can latch the data and then release the data input and it will remember the data. So they can be used as like 8-bit memories to build up larger words. Then we have transceivers, which are, in the case when you want to send data in both directions, instead of building it up with a bunch of drivers, you can just get a transceiver, all right? And then, of course, we're just looking at 8-bit depth things here. If you look through Texas Instrument or DigiKey, you know, all the chips. You can find a 16-bit, and you could probably find 30. I think you can find 32-bit. I'm sure you can find 32-bit transceivers. They're probably very expensive, but you can find 16-bit transceivers. So if we were just to type in 16-bit transceiver here, we might just have to type in transceiver. But let's see. Let's look under logic buffers. All right. So, and let's see, what's this one right here? So number of elements 2. So like this guy right here, which is this 1622. This one has 2 elements, and each element has 8 bits. So if you go take a look at this, now this is very expensive. Things are $4 a pop. All right. And if we go down here, all right, so this is advanced low voltage, and also it's got termination resistors. This is so you don't get reflections, because you're talking about very high speed logic here. All right, and now you can see inside of the circuit, it's got 2 of these packages here. So you can either use this 8-bit for one thing and this 8-bit for another thing, but they're both transceivers, or you can tie them together and have a 16-bit. So if you wanted a 32-bit transceiver, you'd use 2 of these ICs. All right, so very cool. And then look at our speeds here. So now with advanced low voltage CMOS, look at what we got. So our propagation for high and low transitions, roughly the same here. But now at 3.3 volts, we are hanging around 2 nanoseconds. 2 nanoseconds. So we'll split the difference there. We'll split the difference and we'll call it, really what you want to do is you need to use the worst case propagation delay. This is from low to high and high to low. So let's use the worst case propagation delay of 2.3 volts here. Excuse me, 2.3 nanoseconds. 2.3 nanoseconds. And let's see how fast that is. If you can do that in your head, great. All right, so this is a nice number. So that's 434 megahertz. So this IC is going to get your job done if you're interfacing to an ARM processor, a Cortex processor, or a fast MPU that's running around that 200, 300, 400 megahertz range. You could use this for your transceivers to communicate to other things. All right. So anyway, that's a great little chip. Not cheap, right? So you look here, even if you're building 1,000 units, that's $2, you know, $2.40 a unit, right? So that's pretty expensive. That's why, you know, 32-bit, 64-bit computer architectures are expensive, because this stuff just starts adding up, all right? So anyway, we're done with that, and let's stop here. This has been a good lecture. Next, we're going to come back and we're going to talk a little bit about arithmetic functions and ALUs, arithmetic logic units. Now, these days you wouldn't build an ALU, you would just use a microcontroller. But sometimes you might want to compare a couple numbers, maybe you have a couple different sources of data, and I just want to compare a couple numbers. I want to see something greater than something or less than equal to whatever, and that's what an ALU or simple comparators are for, digital 4-bit comparators, which you could parallel up to make an 8-bit comparator. So we're going to talk about this stuff just so you know about it in the next lecture, just to be complete. Okay, so let's go ahead, let's stop here, and I will see you in the next lecture. Bye. All right, hello and welcome back. We are on the next lecture. We're continuing our discussion of various digital ICs that represent different kinds of classes, major classes of ICs that you would use, kind of your starter ICs, you know, used for digital building blocks. And the next section we are on now in the book is arithmetic functions and ALUs, which stands for arithmetic logic units. So this is section 635, and as usual, I want you to read this whole thing inside the book, and we're going to talk about 3 different things here, and we'll kind of break this up. We're going to talk about comparators, we're going to talk about adders again briefly, and then we're going to talk about ALUs, arithmetic logic units. And in each one of these things, well, probably just 2 of them, we're going to build some stuff on the bench and do some simulation. All right, so this is actually, so now we're getting to the point where we're getting out of the mud, and we've got some components that do something. And with these kind of components and some of the other things that we've looked at, we can actually start to build a little computer. And so this is kind of exciting. So with what you're going to learn just in this chapter, what we're going to talk about in the next few lectures here, you could build a very, very simple microprocessor, microcontroller kind of thing. And I'm going to show you how you would do that. All right, so anyway, so let's start off with the first class of IC. And this is a comparator we're going to talk about, all right? And again, whenever I show you anything here, there's many, many dozens or hundreds of different ICs that perform the same kind of function. We're just looking at kind of some of the older root ICs that do this, and then you can always go from there and find other things. But these are good representative ICs. So the 74 HC or LS85, and there's many families again of the same IC. So the 74 HC85 that you're looking at right here, and this is a Texas Instruments version, and this data sheet happens to be from 2003. We'll go look online as well. So let's take a look at this and what this thing does. So what this thing does is, if you take a look at the pinout here, it's a comparator. And it's a 4-bit comparator, magnitude comparator. So you basically put two 4-bit numbers, and one of the numbers comes in on A0 through A3. Here we go. Here's A0, A1, A2, A3, and then B0, B1, B2, B3. So A0 through A3 and B0 through B3. So A and B are your two numbers that you want to compare. And then the IC compares these numbers, and then on these digital outputs 5, 6, and 7, these will be high or low depending on if A is greater than B, magnitude only, if A is equal to B, or A is less than B. Now, there's these inputs here on 2, 3, and 4, and what these are cascade in inputs. In other words, if you want to compare 8-bit numbers, 12-bit numbers, 16-bit numbers, you could take these chips, put them in parallel, then you have to cascade these outputs to these inputs, so that if you're going to compare say an 8-bit number, you compare the lower nibble first, then the upper nibble, so then whatever happens with the lower nibble has to be cascaded to the upper nibble. So it's A equal, less than, greater, its output goes into the input of the next nibble. So anyway, we'll take a look at that as well. All right, and let's see, I think, yeah, so the next thing is talking about the adder. So let's go ahead and let's go find the data sheet here for this guy. And I think I have it open here someplace. Yeah, so 74LS. Here we go here. So here's the 74HC85 that we were just looking at. Same exact thing. And in fact, yeah, it's the exact same data sheet that I had in my book. So this hasn't been updated since 2003. All right, and what I want you, so this is the truth table. This is a little bit gnarly to look at, a little bit complicated. But what it's showing is for all the different inputs, here's all the different situations that you have. And then this is like when you're talking about a single device, if A3 equals B3 or A2 is greater than B2, and here's what these inputs are, here's what the cascaded inputs, they don't matter, here's what you got as outputs. So it just shows all these different combinations, a little bit hard to read through, not too important to look at that, but what I want to look at, I think it's inside this. Let's take a look. There's a nice little picture of, yeah, here we go. So here's how you would cascade these together if you wanted to do that. So this is a 12-bit cascade. So here, these are the least significant 4-bit word, and then here's the next significant, or the next 4 bits, and then there's the next 4 bits. So this is low to high, right? So low to high. And so basically, say if we forget this bottom one, let's just say we wanted to compare two 8-bit words. So here's where we put the first 4 bits of the first word. Here's the first 4 bits of the other word. Here's the next 4 bits of the first word, and the next 4 bits of the other word. So this does the total comparison of 8 bits. And then you'll notice we take, and this actually should have said A greater than B out, A equal to B out, A less than B out. So these are those outputs right there. They didn't label them. Those go to the inputs of the next chip. So you have to kind of cascade and carry this information through so the next chip knows what to do, what happened in the previous IC. And then finally, here are the outputs right here. So they're labeled here. You can see they just missed the labels. And here's A greater than B, A equal to B, A less than B. And if we didn't want to do 12 bits, which would be silly, just remove this IC and we just take these 3 outputs. And here we have an 8-bit comparator. And if we just use one of these, we have a 4-bit comparator. All right. Okay, now if we are not going to use and cascade these things together, then we need to set up the very first one like this always, no matter what. So A greater than B has to be ground, A equal to B is high, and A less than B is ground. So that's kind of the setup for the very first one uh, uh, that you have in your cascade chain. So it's 1 or n. If you have more of them, then you're going to take the outputs and put them into the inputs. But if you only have one comparator, you need to set the first one up like this, all right? And then you just put your A and B inputs here, highs and lows, and then you just take your outputs and do whatever you want to do with them. Now, a couple interesting things here. I think there's a schematic of the ICs, excuse me, I think there's a schematic of what's in, too bad. So it's not showing what the actual logic is inside of it, but this is a completely combinatorial IC. And so it's not clocked, there's no clocking, it just does the comparison. We have to wait for the comparison to happen, right? And we have to wait and make sure the comparison is complete. And that can be a little problematic, all right? Because since there's no clock, right, this is happening asynchronously. And the question is, how do we know when this thing is done, right? So that's an issue with unclocked combinatorial logic. And then here's another another kind of block diagram that makes it a little bit easier to see what's going on. You got A, you got B, you got your inputs, and then you got your outputs, and then these pins are just kind of all over the place. Now let's take a look at some of the switching characteristics here. And what do we want to look at? We want to look at switching characteristics, not DC, but switching. Here we go. Switching specifications. So this is an HC device, so remember we're talking about CMOS, so talking about field effect transistors. So in this case, what we care about is what the capacitive load is on each one of the outputs, right? You know, typically each one of these can load, you know, drive 5 to 10 other IC inputs. But anyway, so let's take a look here. So HC types, and it says propagation delay, high to low, low to high of, you know, AN, BN to A greater than B, A less than B, and then A equals B. So what this is talking about is there's a couple different paths here. So the A greater than B path, that's one logic path, and the A less than B is another path, but then the A equal B path is another path as well. It's got slightly different timing. That's what all this is about. Then depending on what voltage we run this at, say we're going to run it at 5 volts in both cases. So we're kind of interested in this row right here. All right, we're kind of interested in this row right here. All right, and if we're running this thing at 25 degrees Celsius, which is kind of the average room temperature, then what it's saying is at 5 volts, typical, we're going to get a 16 nanosecond delay time. All right, if we run it at a lower voltage, like 2 volts, it goes way up to 195, 39. But at 5 volts, it's consistent about 16 nanoseconds. And that's why the max and the min are not even in there. It's just more or less always 16 nanoseconds. All right. Then if we go look at what the A equal B path is, it's 14 nanoseconds, right here. All right. So what this means is if you want to use this chip at 5 volts, you can be guaranteed that when it does the comparison, the greater or less than, the result will come out in 16 nanoseconds, but the equal will come out in 14 nanoseconds. So that means we have to use the kind of the weakest link in the chain here, which is the 16 nanosecond for our timing. So if we were going to build this into something, we'd give ourselves a little bit of extra buffer. So we might have to say, let's call it 18 nanoseconds or even 20 nanoseconds. So we would say we're never going to assume that we have a result faster than 20 nanoseconds, all right? So let's see, how fast is 20 nanoseconds? How many megahertz is that? Let's do it. Do it on your calculator. So we put in 20 nanoseconds. Right, 20 times 10 to the negative ninth. Invert that. That's going to give us the clock rate. And of course, that is 50 megahertz. 50 megahertz right there. All right, so that's not bad. So we can do this comparison at a rate of 50 megahertz conservatively, and we go a little bit faster, you know, if we want to pump it up a little bit and get closer to those delays. Okay, so what we're going to do is we're going to actually build something that just takes some dip switches, A and B, compares whatever number we put on there, and then just has 3 LEDs, one for greater than, one for less than, and one for equal to. Real simple, all right? So let's take a look at the, I've already built a simulation for you. So up here, this is called Crash Course EE, serial comparator. Let's see here. Oh, actually, let's see here. Serial comparator. I don't think we want the word serial in there. No, we don't. So that was from the serial registers that we were messing with. So there we go. Let's just put that. So let's rename that. Okay. So Crash Course EE comparator 74HC05, and then this is version 01. All right. So let's look what we have here. So what do we got? We've got the 74HC85. We're running it at 5 volts. All right. And those pins are not shown. Then we've got a few things going on here. One, we've got our bypass capacitor always. All right, and then we have the cascade in inputs, which is the A less than B, A greater than B, A equal to B. We've got those set properly. So A equals B has to be set high, and then A less than B, A greater than B, those are set low. When this is the first 4 bits in your cascade, or the only 4 bits, that's how you need to set those, okay? And they're set correctly. All right, now we want to have 4 numbers here, so I'm going to call this input A as a 4-bit dip switch, and then input B is another 4-bit dip switch. Now, when we turn the dip switch on, we want to get a 1. So that means we need to put pull downs on all these inputs, and we're putting 1K pull downs right here. And now typically we can get away with a 10K pull down on CMOS logic and it'll still work, but on the bench over there, the only IC that I was able to find easily was an LS version of this, which is the 74LS85. And because it's a TTL chip, right, it requires more current to drive those inputs, high and low, whereas the CMOS requires very, very little current, technically no current, but the LS inputs require current, and these pull downs need to be much, much stronger, or the resistor value is much lower. We're going to take a look at that, the actual values of that, and confirm that just in a moment, but let's hold on here and continue with this. We'll put a pin in that and come back to that. All right, so we've got our inputs here, we got our pull down, so we'll always get weak zeros on here, and then we can put this bit pattern to anything we want. Then we have the outputs. Q, and this is called QA less than B, QA equals B, QA greater than B. So what's this Q thing about? It's just Q means output. It just means output, and then so they concatenate Q with A less than B. So it's the Q, A less than B, Q, A equal to B, Q, A greater than B, whatever. And that's why I say you got to be careful, because different tools, different data sheets, different people. This tool is made in the United Kingdom. Right? This is the place where color is spelled C-O-L-O-U-R, right? In the United States, we spell it C-O-L-O-R, right? So there's a lot of weirdness. Their date and time is different than our date and time, and the way that they orient the day and month and that kind of thing. So, and a lot of things are a little bit quirky in this Proteus tool because it's a little bit English. So anyway, you got to be careful of that, and some of these chips just have some namings that are a little bit different than you would expect. Okay, so now we have each one of those outputs. These are positive logic outputs, so when it's asserted, it will be high. So we're going to put a little current limiting resistor in there, and then we're going to put 3 LEDs. So this is LED for less than, so D for diode less than, diode equal, and diode greater than. I'm using red, blue, and green. Red to me feels like it's less than, it's small maybe. Equal is blue, and then a green was greater than. All right, G for greater than, so that kind of worked out. All right, so that's it. It's very simple. Notice there's no clock, right? Let's run the simulation. Here we go. Simulation's running. All right, so right now, and remember visually, wherever the black is, that is where the switch is. So this is off, 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 which means we've got 0, 0, 0, 0, 0, 0, 0, 0 for both of these nibbles. And you can see that here because blue means 0 and red means 1. So here's a red 1 and a red 1. So both the numbers are the same for A and B, therefore they're equal. If they're equal, then QA equals B should be high, and it is, and the blue LED is on. Okay, let's make the lower bit, let's make it 1000, which would be 1. All right, so now A is greater than B. A is greater than B. And sure enough, there it is. A is greater than B is on. Okay, now let's make B greater than A. So let's turn on the 2-bit here, right? So now that's 2. So now B is greater than A, right? Or A is less than B. And there we go, right there. So we got that A less than B. All right, and let's turn on this upper bit here. So now I've got 10 on B. We got 10 on B. All right, and now we've got 9 on A. Still, it's going to be, A is still smaller. Now let's throw another 2 on there and make it 11. Oh, and there you go. Now A is greater than B, so that bit turns on. LED turns on. And now let's make them the same. And there we go. And I'm trying to make it the same. There. And I made both of them the same. And so what are these numbers here? We've got 1, 1, 0, 1, so 1, 1, 0, 1, so that's 3 and 8. So each one of these is 11, right? 11 in decimal for 1, 1, 0, 1. And they are equal no matter what, and so we have the equal. All right, and that's it. And so that is a comparator. All right, and we can use these to compare binary numbers or some data. So for example, we may have brought some data in over a serial line. We may have deserialized it. Now we have it in parallel. Maybe it's parallel 4-bit, maybe it's parallel 8-bit, right? And maybe we want to compare that and look for a sentinel. So maybe we don't want to use a microcontroller. Maybe we just want to have some hardware that as the data streams by, we're looking for a 26. I don't know, right? Some number that represents something. Or maybe a carriage return or a line feed, right? To do that, we would have a couple comparators and we would set the code that we're looking for. And when we found that, then the comparator would output something and then we could do something and take an action based on that. So you can see how you build these blocks with hardware. Very cool. All right. And then if we wanted to compare 8 bits, we just put a couple of these in parallel. You know, boom, done. Okay. So now what we're going to do is we're going to go over to the bench and we are going to build. I've already actually built it. Because it's fairly complicated, and I think you're pretty good at building things now. You don't need to see me put all the wires in. All right, so let's go over to the bench, and we're going to see the hardware implementation of this, which is almost identical. All right, so let's go over to the bench and let's take a look at that. Okay, so we're here on the bench, and as you can see, I've already got this kind of put together here. All right, so what I'd like to do now is looking at the data sheet. You can put the data sheet yourself up for the 74 LS85 or 74 HC85 and kind of follow along, but I've broken this up and it should be fairly easy to follow. So also, here's my logic probe. This is a little WaveTech Meterman LP10A. And this is a nice little tool. You hook it up to power +5 and ground, and then you can put it on CMOS or TTL, and then you can probe with the tip of it, and the little LED here will turn high or low. It's also nice because it's got a really sharp little pointer that I can move things with. All right, so that's all that is. Okay, so let's go through here and let's see what we got. All right, so now we are getting to be pretty consummate electrical embedded engineers, and so we know what we're doing. So the first thing, let's start off. We've got our 74 LS. Here we got an 85. So this is an LS version of it. All right. And we've got power. So where's the power going? So here's the pin 8. So this is a 16 pin. So it's 1 through 8 and 9 through 16. And so power comes here. We've got ground on pin 8 going to ground, all right, which is expected. And then on pin 16 up here, we've got pin 16 is going to power right here. Then we've got our bypass to ground. We've got our bypass of 0.1 microfarad to ground. All right. Here are our outputs. All right. So over here on pin 5, 6, and 7. 5, 6, and 7. And notice I've color coded these. So green is for greater than, and then blue is equal, and red is less than. So each one of those is going through a 100 ohm resistor. Right. What's a 100 ohm? Brown, black, brown, brown, black, brown. And then right to a red, a blue, and a green LED. And this is blue. It's just completely clear. It'll turn blue, and you're going to see that. And it's a real bright LED. Okay, let's see what else we have. Here's our cascaded inputs in. All right, so we got A less than B, A greater than B, and then we've got A equal to B. And we got to set those to ground, ground, and high on the very first comparator. And since we've only got one comparator, that's how those go. All right, now, what else? Here's our input switches, okay? And then what I've done is I've just, so this is an 8-pin dip switch, and I've just using a permanent marker, I've marked these blue and these green, just so you can see there's, you know, 2 4-bit values here, right? And that's to signify that. So you can kind of see these things moving up and down, right? Okay, now when we turn these on is up, we want to connect these. These are going to be connected to 1, so this is going to go high, which is to our +5 rail. On the other end, we've got to have pull-down resistors. So we got pull-downs here, and these are all 1K ohm resistors, 1K ohm resistors, all right? And those are going to ground. So those are going to give us zeros in normally when we don't have this switch switched, any of these dip switches switched, all right? Now, One thing I want to bring your attention to, which I just talked about a second ago, not a second ago, but a few minutes ago, was this is an LS version. And so this means this is TTL logic, not CMOS. And these pull down resistors or pull up, they need to be larger, not larger, they need to be a smaller value, but a larger current, because we need to drive current to get ones and zeros in TTL logic. So these are 1K. When we use CMOS, typically you see me use 10K because we don't need any current, we just need some voltage, all right? So just real briefly, let's go back to the computer for a second, and I just want to show you the data sheets and show you this real quick and why this has to be done. So we're back here on the computer, and let me show you something just that'll kind of bring this home. So here's the HC version, right? So here's the HC data sheet. Data sheet, okay? Now, if we look at the HC data sheet, all right, one thing that we'll have here, all right, and if I want to show it to you in kind of the DC specifications, is in DC specifications, there is no I input low and I input high. There is no current required in CMOS circuits, right? There's just these leakage currents, and you can see they're 1 microampere. 1 microampere here, all right? And then here you'll see this 1 microampere. What matters is the voltage, and what matters is the capacitance, all right, for these outputs and inputs. So in other words, to drive a CMOS input high or low, we don't need any current, we just need the voltage. So if we put a 10K ohm resistor or even a 100K resistor as a pull up or pull down, we'll get a 1 or we'll get a 0. We need that leakage current though. So for example, let's say that we put a 100K resistor as a pull up or pull down. We need at least 1 microamp here. We need 1 microamp of this leakage current to turn this thing on here, all right? 1 microamp, right? So let's see, 100 k ohms, okay? And let's figure out the current here. So we've got 5 volts divided by 100, 10 to the third, okay? And that's 50 microamperes, 50 microamperes. So at 5 volts, with a 100K pull up or pull down, we'd have a total possible current of 50 microamperes, and all we need is 1 microampere for the leakage current to happen. So bottom line is we can have really big pull up and pull down resistors, but if we're going to use an LS logic, let's find that LS version. So here's the LS version. Here's where we get in trouble. And this is what you got to be careful of. Now, oh, good. Here's the LS version, and notice the LS version shows the schematic diagram. And remember, they had slightly different timings for A greater than B and A less than B and A equal to B. Let's see, can we visually see that? Sure. Look at here. Here's the A greater than B. Here's the A equal to B. And here's the A less than B. All right? So the equal to B has less, logic layers. The A greater and A less than has more logic layers, right? You can see it right there and right there. So the A equals the simpler one, so it should be the faster, I think, by looking at this, unless I'm looking at it wrong. So let's make sure to look at that. And now let's also go down and let's look at the switch, the DC characteristics for I input low and I input high. All right, so here we go. So I input high, I input low. And so this says for A less than B, A greater than B, or all other inputs. That's what we're talking about, all other inputs. That's the A and B data. These are the cascading inputs. Again, here's all other inputs. Okay, so I input high, I input low. What we're looking for is this 120. We need 120 microamperes there. And then here's the problem. I input low, we need 4.8 milliamperes. Okay, so if we had a 10K resistor for that pull down, 10K resistor. So let's take 5 volts divided by 10K, and that gives us, and go to engineering so we can see this. Oops, engineering. All right, that gives us 500 microamperes. 500 microamperes. Can you see that? Or basically half a milliampere. All right, so the 500 to get it done for an input high, all right, a pull up, but not for a pull down. We're going to need 4.8, so we're going to need basically 8 times that, so that's not going to do. That's why we need to go to that 1K pull down to get the job done. So 5 volts divided by 1K pull down equals, you go to engineering, now look at that. That's 5 milliamperes. So that gets it done. So that's why we have those 1K pull downs over there. Now, last thing, let's look at the propagation delays here. So here are the propagation delays, and I submit that when I looked at this, and I'm wrong, so I counted wrong. So if you look here, T propagation high, so A less than B, A greater than B, it's saying number of gate levels, all right, number of gate levels. The A equal B is always 4, all right, A equals B is always 4, all right, and so A less than or greater can have different gate levels depending on what happens. So we just didn't really see that when we were looking at it, and that's why you got to look at this to make sure. So sometimes you're wrong. So the A less than B can be from 7 nanoseconds to 26 nanoseconds, but the A equal to B is always, a typical is like 23 and a maximum of 35, right? So looking back up here, I'd have to go through this better, but it's saying there's always 4 levels. 1, 2, 1, 2, 3, 4. Yeah, so you just have to go through this and figure out, how many levels there are. But it looks like there's always 4 in the A equals B path, all right? So anyway, so that's that, and let's get back to the bench now. And now that we have this little issue over currents required for pull-ups and pull-downs on HC or CMOS logic versus TTL logic. Bottom line, TTL logic, you need current. You need some current, so you make sure you make those pull-ups and pull-downs 1 to 2K. I usually use 1K or 2.2K. That'll get it done. But on the HC logic or CMOS logic, I'll usually use a 10K. I don't like using big resistors like 47 or 50 or 100K because there's like no signal there. If you touch the thing, something happens. So I like to put a little bit of power there. So 10K is kind of what I use. All right, let's get back to the bench. Okay, so we're back here on the bench. We have gone through the circuit here. The only other thing to look at is we've got the lower bits. So I believe, let's see here. I'm trying to figure out, so I think this is A and this is B. Let's figure it out. Pin 1 here has got this purple line. It's going into this guy right here. So pin 1 has got this guy right here. Let's see what pin 1 is going to. So pin 1, and I'm looking on the chip, the IC, that's B. So that's B3. So this is B3. So this is B and this is A. So whatever number we put here A and whatever number we put here B in 4 bits, and the bits are, this is the 0 bit, the 1 bit, the 2 bit, the 3. So they're in that order, 0, 1, 2, 3. This is A, this is B. Then these LEDs will light up accordingly. This is if A is less than B, if A is equal to B, if A is greater than B. So it's always A compared to B, and this is A and this is B. All right? Everybody with me? Let's power this thing up and hope it doesn't explode. Okay, so we've got our little LED here representing there's power. The blue LED is on. You can see how bright that is. Let me turn that to the side. It's very bright. It looks almost white on the video. A is equal to B. Is it? Well, sure. They're all the same, whatever they are. So they're all off. So this is 0 compared to 0, right? So it's 0, 0, 0, 0 binary compared to 0, 0, 0, 0 binary. Okay, let's make A greater than B. So let's just make A the binary number 8. So that would mean 1, 2, 4, 8. This bit right here would be high. So we got 8 compared to 0, right? And sure enough, we got the green on, means it's greater. All right. So let's make let's make B also 8. They're equal again. But now let's make B 9. So now A is less than B because A is 8. It's just got a 1 up in the 8 position. And B is 8 and 1, which is 9. So it's less than. All right. And again, we can make them equal. And then we can make A a little bit greater. And then we can make B a little bit greater. And you can just sit here and play with this. And I assure you it all works. And now they're all 1. So this is 15 versus 15, right, in binary. And they, of course, are equal, right? And 15, right? 1 plus 2 plus 4 plus 8 is 15. Right? And then, oh, here's our little logic probe, right? So we can just sit here and probe anything and take a look. You'll be able to see this high and low here. All right, so if I just put it on here, let's see, can you see that? Yeah, you can see that. See that? Do it again. Careful not to short out the whole thing. So there's a high, and oops, I'm shorting things out. There is a low, right? And you can see the little green light. So green light is low, red light is high. I'd prefer it the other way around, actually. And these are really easy to make. I made one of these when I was a little kid. It was one of my first projects. I basically took a pen. I took a big pen, and then I put an inverter chip and a buffer chip and a couple other things and a couple LEDs, power, a couple, and then a resistor, to this lead right here, so I didn't pull too much current. And then I just made one. And you know what? I think I have it someplace around. I kept it because I was like 12 when I made it, so it's kind of a an heirloom. So anyway, this is a handy little device. They're about $20, WaveTech MeterMan, and this one also can, it does pulsing, it'll pulse, and they have ones that are very complicated. Some of them have LCD displays on them and all kinds of cool stuff. So you can do worse things than buy yourself a little logic probe. All right, so that is about it, and that's it. And then what's another little fun thing we could do? If we really wanted to get crazy, what we could do is this. We could go get an Arduino or something, get some kind of Arduino, Raspberry Pi. Here's a Raspberry Pi. We could then, what we could do is we could stream out 4-bit values, right? And then basically say we want to count how many 4-bit values are equal. And then every time they're equal, we could take the output, this equal output, right? And we could put it into a counter. And then every time it counts up, we'd have to clock it though, right? So we'd have to clock the whole system so it's synchronous. And then we could count how many times those values were equal, or whatever. All right, now, if we were to take out the 74LS85 and put in an HC, would it still work? The answer is yes. And the reason why is the HC will definitely work because these pull-down resistors are lower, so they would supply more current if needed, but the HC doesn't need any current. So we could just supply an HC in there and it would work just the same. The timings would be a little bit different. We'd have to go look at the data sheet to see how fast, if the HC was faster than the LS, and check on that. Or we could use a different IC, an LV or an LVC, if we could find one for the 85 comparator. But anyway, so that is it. And so that is the 74 HC or LS or XX 85 comparator. Okay, so cool. All right, so let's finish up here, and then we'll come back in the next lecture and we'll talk about, we're going to talk about adders. All right, bye. All right, welcome back, and we're on the next lecture here. So what are we doing? We are doing adders today, so let's take a look at the text. All right, so we just finished comparators, right? And yeah, comparators were the last thing we did, and we built something on the bench. We kind of did that. Now, we've already talked about adders in a previous lecture, a couple lectures on doing 1-bit adders. And in the next lecture, we're going to do a full arithmetic logic unit, or ALU. So we're not going to build anything with the adder on the bench because it's going to be kind of redundant, but we're going to talk about it. So if you take a look at the book here, we've got what figure 635 shows: a Motorola 74LS83A 4-bit binary full adder with fast carry. All right, so this is section, what is this, 6352 in the book that starts talking about adders. So I want you to read all that, of course. Now, let's talk about some of this language here. So 4-bit binary, obviously binary means binary. 4-bit means the operands are 4-bit. Full adder, right, do we remember what that means? Remember, there's a half adder and a full adder. The half adder, it doesn't add half of something. It just means it doesn't take a carry in. All right, so it doesn't take a carry in, it just adds the bits. A full adder also takes the carry in and the operands, all right? So we're going to have an operand A, an operand B, and a carry in. And then the fast carry, so that's interesting. So what this fast carry is, the computation of a carry and the computation of the sum can be done in parallel. In other words, you don't have to wait for the sum to figure out if there's a carry. You can actually figure out if there's a carry before you finish doing the sum. So because this is hardware, you can use 2 different logic paths and compute what that carry is ahead of time, and not wait for the sum to compute. Why that is helpful is, say that you want to have a bunch of different adder blocks to add up a large number, a larger binary number. You don't have to wait for each one of the blocks to get the carry. You can add everything in parallel, and then the look ahead or the fast carries are computing the carry fast, so that you can push that into your next stage, all right? So if we were to go through, so here's the schematic here, and if you were to go through this thing and kind of look at it, what you can see is, let's just zoom in here a little bit because this is kind of interesting. So we have our operands here. So we've got our A1, A2, A3, A4. So that's a low bit. It's, A0, B0 would be more appropriate. But anyway, so this is a low bit, the next bit, and the most significant bit. So here's where the 2 operands go in. Here's where our carry comes in. Here's that C naught. They call it C naught. All right, and then here's the sum. So here's the sum of the lower bits, least significant bit to highest significant bit. All right, now, but take a look at this over here. So here, this is doing the calculation of just the carry. So basically it's saying in what conditions will we get a carry out? All possible conditions we're going to get a carry out, and then there's combinatorial logic for that, and then this final NOR, and then we've got this carry out. So that's what that means. So that's a full adder takes the carry in, and then we've got a fast carry look ahead here. So this is what this is all about over here. And that's the beauty of hardware. You can do things in parallel, right? Okay, logic symbol for this is this right here. So we got these B's and these A's, we got the carry in, we got the carry out, and then we have these summation symbols to show the outputs, all right? Obviously, there's many adders that you can find. So 74LS83 is a good basic adder, but if we were to go to DigiKey or Mouser or Octopart or whatever we like, if we type in adder, we'll go through here and kind of figure out where we need to click, but logic specialty logic probably would do the trick. All right, and then we'll look at active parts only, in stock parts. All right, and showing there are 19 parts. So there's this 283, 283. Looks like we're getting a lot of 283 parts for the adders. All right, 283, 283, 283. There's a fast version right there, an advanced version right there. There's just a plain Schottky version right there. So anyway, we can go through here and just pick one of these off, and let's just grab this fast one. All right, so this is a little bit more modern than what we're looking at here, right? So if we look at this one here, so what's this say? The F283 is a full adder that performs the addition of 2 full-bit binary words. Carry out. So looks like it's roughly the same. Here's our input operand A, input operand B, there's our carry in, there's our carry out, and there is our summation bits. And then if we look at the logic diagram here, all right, we look at the logic diagram. Again, it's very similar. So we'd have to read through this and see what the difference is with the 283 as compared to just the 83, all right? But there are other adders. There's not a lot of them because this kind of time is past. Typically, if you're going to do any math, you're going to do it with a microcontroller or maybe a field programmable gate array. You're not going to have to do it with discrete logic, right, with TTL chips. But it's important to know how to do it so that you can understand. All right, let's get back here. All right, so looking at our 74LS83, now what we're going to do is we're going to take this IC and we're going to put it into a simulation. And let's see if there's anything else here interesting. This is going to talk about the ALU next. So let's come back here. All right, so we're going to take this chip and we're going to build something out of it that adds A plus B and shows the output. We're not going to do it on the bench because, like I said, right in the next section, we're going to do more complex arithmetic logic units, which are actually really cool. So we're only going to do a simulation. All right, so let's go over to that. So I've already built this. Again, this is in Proteus, and this is called Crash Course EE Adder 74LS83_01. It'll be in the materials for this lecture, so don't worry about that. Again, if you're skipping all around, this is a Lab Center Proteus. It's a CAD CAM program for PCB circuit design, so it's got schematic capture and layout, and it has simulation, and that's why we like it. It's got full SPICE and a full digital simulation system that allows you to simulate ICs and processors as well. You can ARM processors, PIC processors, AVAR processors, Arduino. It's very cool. Circuit maker that we're going to use at the end of the course to design circuits and lay them out does not have simulation as of yet. So that's why we're using a Proteus, and I just like Proteus. So you can get a free version of this to follow along, and you just can't save and do other things, but you can definitely load these in and play with them. Anyway, so let's dig in and see what's going on here. So the first thing is I found the 74LS83 in the library for this tool, and you can see here it is right here. It looks like what we expect. So we've got our input A, we got our input B, which are 4 bits each. We got our carry in. We're just going to put that to 0. All right, we're going to have no carry coming in. We've got our carry going out here, and I believe carry out, it's positive logic, so it's active high. So when we get a carry out, we should see this LED turn on, all right? Okay, what else do we have? So now let's get some inputs. So again, from the previous comparator example, I just took the same logic, I copied it, and that's what's nice. Once you start designing hardware, you can just kind of copy and paste big chunks. It's like coding, copying and pasting, but it's a lot easier because the side effects you can, at a glance, you can see the whole circuit, right? So there's not a lot of side effects. When you copy and paste software, you know, there's variables that are getting initialized, constructors, destructors getting called, all kinds of crazy things that you can't follow that whole flow. But with hardware, it's what you see is what you get. So I copied this section right here, which is just 2 switches with a bunch of pull down resistors. Since we're using LS logic, we got a little stronger pull downs, 1K. When we're doing the HC logic, we can get away with 10K, but for LS, we use the 1K. And then we've got the dip switches that are going to give us our 2 binary numbers. Now, what are we doing here? I want to see these numbers. We could just put them in like we did with the comparator, but instead I've got drivers up here. So I've got the 4 bits here and the 4 bits here for the input A and the input B. These are going into our 7447 decoders. So these are our 7-segment decoders. Now you can start to see we're putting all these things together, right? So 74LS47, again, let's take a look at the design. What do we have here? And of course, with, well, we really haven't got to that yet, but let's get back here. So we've got our IC, we've got our bypass capacitor right here. I've just rotated it just to make things a little bit shorter vertically. So bypass capacitor goes from a power capacitor to ground, and just make sure that goes close to this IC. And ideally, the capacitor should connect right to the V sub CC pin to ground, be very close to it. All right. Then we have this IC here. We hook up the power leads on it, which are not shown in this particular footprint. V sub CC and ground, those are going to the 5 volts and ground. They're just not shown here. All right. And then we hook this thing up. Now, if you recall, the input, the binary input is ABCD, which is low bit to high bit, least significant to most significant. So that's where we put the input. Then we've got all these tricky inputs here, and these are blanking inputs. Remember, this is blanking in and doing different things so you can turn off the digits. If you like have a 0, you don't want to show 0, you just want it to be blanked. And then remember, this LT was a lamp test. They're all active low. So we're just going to tie all those together and tie those directly to high. Remember, when you're dealing with LS type logic, TTL logic, these are current devices, and typically if we're going to pull something high, I prefer to put a resistor just to minimize the current a little bit. So you might put a 1K pull-up resistor instead of tying it directly. With HC or CMOS logic, you can tie things directly high, and that's fine because you're not going to drag any current. But it never hurts to put a little bit of a current limiting resistor. So I really would put a 1K. If I were going to design this, I'd probably put a 1K pull-up here instead of pulling it directly to 5V sub CC. But I'm just trying to save some space here. So here's A and here's B, right? So these are the 2 A and B. So this is going to show us what we've entered in on these dip switches. Now, all right, that's all they do. Now here is the magic part. Here is our adder. So here's our 74LS83 adder. And again, we got a bypass capacitor right here. All right, in fact, let's just bring that a little bit closer. Right, remember, we just kind of put them off the design technique or convention. Is kind of put it just near the IC so you know it goes to that IC. And we might have more than one of these. We might have 2, 3, 4. We might have 100. If you're going to build something with a modern processor, you'll have about 100 bypass capacitors, believe it or not. And a modern processor might have 1,000 pins on it, if you can believe that, or 2,000 pins. Okay, now, so we've got input A, we've got input B. In binary order, least significant bit to most significant bit, least significant bit to most significant bit. We got the carry in is 0. We got our carry out going to our light here. Then we have our sum, and our sum, low bit to high bit, is going into another decoder right here, and again hooked up the exact same way, and to another 7-segment display. And QA through QG just goes right out there, and then that's that. Now, notice I have a bypass capacitor on the power here. This isn't so much for noise as it is for a power source. So that we've got larger 10 microfarad capacitors on here so that when this thing draws a bunch of current, each one of these segments turn on and off, on and off, on and off real quickly potentially. There's 7 segments, each one might pull 10 to 20 milliamperes. That's a good amount of current, and it'll pull on the power supply. So just a good design tactic is put a capacitor there, a bulk capacitor as it's called, and like a 10 microfarad, 22, 47, 100, depending on how much current you're going to pull. All right. So anyway, so that is the design. So when I turn this thing on and we start putting numbers here, we'll see the numbers here, and it'll be this plus this equals that. Simple as that. Remember, these decoders, the 7447 decoder, only decodes 0 through 9, and then 10 through 15, it has funky symbols. It doesn't have hex, which is unfortunate. So it'd be nice if we had a hex decoder, because then we could see A is 10, B is 11, C is 12, D is 13, E is 14, F is 15. But we're not going to see that. We're going to see the funky symbols. So we'll keep paying attention to that. All right, so I want to get this all on the screen at once. There it is. Let's run the simulation. Simulation is running. All right, so let's look at our dip switches here. Here's A, here's B, and remember, this is a little bit tricky. Where it's black, that means the switch position, okay? So, you know, I always think it's where it's white it is, but this is all off, 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 off. So since they're all off, we're getting all the pull downs, we're getting all these blue low voltages, so we're getting 0 and 0. Let's put a 1 into the top A. So here's A, so if we switch the lower bit, that'll give us a 1. Sure enough, 1 plus 0 is 1, so it's adding. Okay, let's turn that into 3. All right, there we go. 3 plus 0 equals 3, sure does. Let's add a 4 to the mix. All right, so we should get a 7. 3 plus 4 is 7, yep. Let's make that 4 a 5 with this lower bit. 3 plus 5 is 8, sure is. And let's see here, let's turn on, what else can we turn on here? Let's turn on this. 3 plus 7 equals 10, and this is the symbol for 10, all right? So now let's drop down, we'll make this a 2. So drop this, take the 1 bit off this, and 2 plus 7 equals 9, it sure does. All right, so our adder works perfectly. How cool is that? And that's it. So that is a adder. And we basically just made the world's most primitive, simplistic calculator. But hey, this is pretty cool. If you're in high school, right, and you were to, you know, do this for a project for electronics or something like that, that would be a really respectable project. Make it nice, put it in a box, and then if you could even do better, if you could figure out a way to input these numbers by pressing a keypad, that would be even cooler, right? But we're going to do even better. We are going to make a little computer or calculator in the next lecture using a full arithmetic logic unit. So before we do that, let's go back to DigiKey and all this. So again, the links for this stuff will be inside the lecture, so you can search for them. But you know, 74F283, there's that 283 that we were just looking at, and then I believe, yeah. So let's see, yeah. So here's a 74LS83. Adder, which is more or less what we're using right now. Just another data sheet from another company, Fairchild. But what the interesting thing is, take a look here. So see this in features, typical add times, 2 8-bit words, 25 nanoseconds. 2 8-bit words. So what that's talking about is, if you were to take 2 of these and cascade them together, by the time the carries got through everything, you could do the add in 25 nanoseconds, right? Now, if we go back to, let's see here, and I'm trying to find, oops, didn't want to do that. Let's go back to this 283, and let's see what some of its timings are. So if we go down here, and we're looking for switching characteristics, there we go. So, so basically, from the carry to the sum, or from A to B to the sum, or from the carry in to the carry out, all these different timings here are all over here, and then it's showing for these different you know, variations of IC and type and voltage and all that, right? So at 25 degrees Celsius, which is what we normally deal with, here are the propagation delays. So the worst propagation delay is about 10 nanoseconds, and on average it's about, you know, 6.5, 6.6 nanoseconds. So this is pretty fast. So this guy is very, very fast right here. So this 74F283, right, is doing the addition in about you know, 7 nanoseconds, and then a maximum of 10 nanoseconds. So if you were to cascade these together to get 8 bits, as in the previous example that we were just looking at, then on average it'd take about 12, 13 nanoseconds, and in worst case about 20 nanoseconds. So this F is pretty fast. So let's say that we can add 2 8-bit words in about 20 nanoseconds if we were to use this F. So 20 nanoseconds, so that's 20 x minus 9th. We'll invert this. Got my new calculator here, trying to figure it out. So 50 megahertz, can you see that? 50 megahertz. So this would get math done at 50 megahertz. That's pretty respectable, right? So anyway, not bad at all. All right. Okay, so now what I want to do is I want to go back to the document here. So we're back to the my book here, and we're talking about adders. And again, I want you to read through this. Now what we're going to talk about are 4-bit arithmetic logic units, all right, and or ALUs, all right. And so what we're going to do is we're going to stop the lecture right here, and then just as a nice little cutoff point, and then we're going to come back and we'll talk about 4-bit ALUs, and we're going to actually build something on the bench. We're not going to build a simulation of it because we can't, because I don't have this IC in the simulator, so we're stuck. We're going to have to build something. So this will be the biggest thing I think that we've built so far, maybe. And you know, like a little teeny tiny calculator. So anyway, let's stop the lecture right here, and I will meet you back in the next lecture, and we'll talk about this. All right, bye for now. All right, everybody, welcome back. We are on the next section here, next lecture, and now we're talking about ALUs, or arithmetic logic units, in section 6353 of my book here. And so basically, the ALU is a functional unit that typically does math and logical operations in a microcontroller or a microprocessor. So for example, say if you wanted to design a discrete little microprocessor or microcontroller out of TTL or CMOS chips, you might use an ALU to do the math and logical operations. So you could actually build one yourself to do it. Now, like with the previous lecture when we talked about the adder, the ALU is like the adder, except it obviously it has many more functions. Now, a real ALU would have many functions in a microcontroller or microprocessor, but you know, obviously based on price and the number of pins and so forth, these ALUs are fairly constrained in what they can do. And then also remember the time that these things were made, the 80s, the 90s, etc. Back in that time frame, they actually were quite powerful. So anyway, read through the chapter, the section as usual. And so so what we're going to do is we're going to look at two ICs. We're going to look at the 181, and then we're going to look at, I believe it's a 382 chip. The 181 is here in the book, and it's a good example. And I told you that the simulator wouldn't simulate it, and I was wrong. I actually found the ICs in the simulator. I don't know what was happening. Maybe the search wasn't working, but I found the 181 in the simulator, but not the 382. But I do have a 382, but I don't have a 181, so we're going to simulate the 181, which is in the book, so that's good. Then we're going to build something with the 382, and I'm going to show you a design that you could simulate if the IC had a simulation model. But anyway, so let's just talk about what is an ALU. So let's just get down to business here. So first thing, let's take a look at this data sheet here. 4-bit arithmetic logic unit, and you could read through this stuff, and we're going to look at the data sheet on DigiKey in a moment here. All right, but in a nutshell, and let's see if I don't think, yeah, so this gets really into software stuff immediately. So let's go to the data sheet here, and let's find this 181 data sheet, and this is it right here, I believe. Yeah. All right, so this was you know, found here at Philips, has this 181, and they still manufacture this chip, so you can buy this. Anybody who supplies Philips ICs, you can get this, which is cool. All right, and last time this particular document was updated was 1998, about 18 years ago. All right, and so you read through this whole thing, and at the end of the day, what we really care about are the pinouts of the IC and what the thing does. So from an abstract level, it's got, we can take a look at a couple different things here, but it's got inputs for operand A, it's got inputs for operand B, then it's got the output, which is whatever the result is of the mathematical operation. So that is called the F output. I think over here is probably the best thing to look at it. So here is the input A, here is part of, so there's A and B, A, B, A, B, A, B here. So there's A and B kind of together there. And then here is the output here, which is F. All right, and then here's the carry in, which is Cn, and then here's the carry out, which is Cn plus 4. Here's an extra little pin, which is a comparator.